to eliminate highly polluted land, and to revive the extraordinary natural wealth of the coastline, put an end to a mining industry that poisons, and permanently stop the flow of polluted water and toxic waste. The mobilization reached a national scale. 800 academics from across the country traveled to Ashio to support the protest. Opposition to the mine increased after the Russo-Japanese War, which temporarily muted the protest. In 1907, a riot broke out. For 3 days, the workers dynamited and torched the industrial complex, and were severely repressed by the military. As in many cases, the productive imperative of modernizing the country outweighed any other considerations. Despite their resistance, most local victims were forced to leave their polluted homes. Between fatalism, resignation, complaints, and insurrections, pollutions were hardly accepted in tacit silence and the general denial of hazards that sometimes received mention. A body of knowledge and practical application was gradually and unmistakably being put in place, even if it did little to interrupt or even slow the increase in pollution. Over the course of the 19th century, the negative impacts of industry on the environment became increasingly well known. The word and modern meaning of pollution entered the popular lexicon during this period, but a political process of acculturation was also established. If the learned and intellectual elites, engineers and industrialists, chemists and economists tended to diminish the hazards and accommodate pollution so as not to slow down the advances of progress, which came to be exclusively identified with big industry, other segments of society saw in the phenomenon of pollutions the manifestation of the ambivalence of a development fraught with hazard. Between these deeply ambivalent and antagonistic interests, the state and local authorities tried to reconcile differences and pacify the deployment of large-scale industry and neighboring populations. 6. Regulating and governing pollution. The tragic events at the Ashio and Rio Tinto mines revealed just how difficult it was to effectively manage pollution and its consequences. Copper's extraction and production are particularly illustrative. Thanks to its physical and chemical properties, most notably its resistance and good thermal and electrical conductivity, pure copper and its alloys enjoyed multiple applications. Its production grew exponentially. At the beginning of the 1840s, Europe produced 35,000 metric tons of copper per year. Most of it came from Great Britain, 25,000 metric tons. Wales was the center of the copper industry. It accounted for 90% of all British copper. On the eve of World War I, production changed scale. With even more applications, particularly in the electrical sector, demand grew, leading to the development of mines and foundries in Spain, Chile, Japan, North America and, later, the Congo. Worldwide copper production in 1890 reached 280,000 metric tons. It rose to 500,000 metric tons 10 years later and surpassed 1 million metric tons in 1914, the same year production ceased in Great Britain. Copper ore needed to be cast and refined, usually in reverberatory furnaces. These complex techniques were energy-intensive and polluting. After 1850, copper foundries worked closely with sulfuric acid factories, from which they obtained critical supplies. In Wales, Swansea, nicknamed Copperopolis, provides an example of how difficult it was to reduce the environmental impact of these processes, and the panoply of available regulations. Up until the 1880s, 75% of the world's copper was refined in Swansea, including ore that came from Chile and the United States. Its factories released 92,000 metric tons of sulfuric acid into the air every year. Very early on, this situation caused residents to complain, forcing authorities to intervene and manufacturers to search for technical solutions to limit discharges and avoid government intervention. Faced with mounting pollution, numerous legal, regulatory, and legislative responses emerged: lawsuits, municipal bylaws, and state intervention. Blackmail, to enforce work and competitiveness, was the authorities' credo, designed to legitimize the sacrifice of certain zones and people in the name of public advancement and national need. Fundamentally liberal and industrialist, the regulatory regime was regularly subject to various modifications in response to the political and economic changes of the period and the construction of nation-states and empires, as well as differences in legal traditions. The first point of contention was the relative importance accorded to justice, which always dominated in common law countries, while administrative intervention was preferred on the European continent. Whatever the elements of law, controlling pollution had to happen on a national scale. Given the vague interventionist hopes of the authorities, specialized solutions took hold in the form of recycling, calls for innovation, and improvements in manufacturing processes. In all cases, a veritable naturalization of pollution was taking place. As and when pollutions became unbearable, the ultimate solution was to banish them into the atmosphere through tall chimneys, into the sea, or into unpopulated areas. Common law regimes. After 1830, industrialization continued to shake up the rules of law. In the Anglo-American world, common law remained the principal method of recourse to protect citizens, property owners, and their neighbors against industry's nuisances. It is easy to explain how this judicial system worked in Great Britain and the United States. According to the liberals, pollution was simply a collection of negative externalities created by some and tolerated by others, with the invisible hand of the market ready to amicably restore equilibrium between polluters and victims through compensation or litigation. But as industrialization became a fundamental part of society over the course of the century, case law had to develop in tandem with industry. Judges' decisions varied depending on complex socio-political power relations. In litigation cases, if the defendant was an industrialist of moderate standing from a non-strategic sector, with a small workforce and low capital investment, he would most likely lose to larger property owners. On the other hand, a powerful industrialist with significant capital, confronted by a more popular and poorly organized complaint, could generally expect to win. This logic was demonstrated by a comparative study of the American states of New York, New Jersey, and Pennsylvania. In Pennsylvania, where heavy industry based around coal and steel dominated in Pittsburgh, judgments rendered between 1840 and 1906 found predominantly in favor of industrialists, in spite of significant pollutions. Conversely, in the other two states, where industry was more fragmented and less powerful, rulings were more varied and more in step with the traditional doctrine of common law, sometimes finding for the plaintiff, despite less intense pollution. Therefore, after the Civil War, northern industrial regions, where the pro-business Republican Party held sway, tended to find in favor of advancing heavy industry. The majority of judges were affiliated with the party. Thus, when New York became a Republican state in 1893, rulings there suddenly mirrored those in Pennsylvania. Elsewhere in the United States, judicial decisions depended upon the pollutants in question and the types of industry under examination. If judges were severe in cases of ancient artisanal nuisances relating to putrefaction techniques, tanneries, animal fat foundries, and the like, they proved to be more lenient toward pollutions emanating from modern industrial practices and those sectors, such as steel or chemistry, that symbolized the new economic preeminence of the young country. A similar trend of partiality toward significant economic interests was also common in Great Britain. Influenced by American jurisprudence, English civil law abandoned the principle of precedence for property owners in favor of a reasonable use policy, particularly in relation to running water. In other words, in the case of pollutions, a waterside resident would no longer have recourse to historic rights, but would have to instead prove unreasonable use of the water by an outsider. The Barlow judgment, passed in 1858 following a court case near Birmingham, precipitated this pivotal change. However, as in the United States, it had less to do with the internal evolution of the law, or the application of a particular doctrine. Rather, the primary impetus for change rested with how a particular judge interpreted and understood the social and cultural contexts in which these environmental disputes took place, and from which they were brought before him. Many debates were raised amongst legal scholars to discuss whether or not industrialization had altered the course of common law's adaptation and evolution. That is to say, disagreement abounded whether common law was a hindrance to industrial progress, and whether it was capable of solving pollution problems, or if it needed bolstering with legislative and regulatory acts. Many thought pollution law should be based on some kind of cost-benefit analysis, the balancing doctrine, in order to manage the nuisances and disagreements that industrialization provoked, and that, from this point of view, it corresponded to the general interest. But as it was practically impossible for judges to calculate real costs and benefits, this was never actually done in the 19th century. Judicial decisions had more to do with social power struggles. This explained why, from a certain mistrust with regard to industry and its nuisances, the law turned progressively, albeit in fits and starts, toward a judicial system that became much more tolerant of polluters. Judicial regulations depended on such diverse reasoning and circumstances that complete generalization was evidently difficult. In Great Britain, industrialization was grafted onto a traditional, urban, and aristocratic society. By contrast, in the United States, it constituted more of a pioneering occupation. As a result, judicial treatments varied widely. In cities built as a result of, or specifically for industry, there existed little regulation. Conversely, in cities that permitted only certain types and sizes of factories, and zoned their activities outside of the city limits so as not to upset the vacationing bourgeoisie, disputes and litigation were more commonplace. Thus, in spite of an overall movement to create case law that would favor industrialists, common law, up until the early 1900s, still played a role in safeguarding neighborhoods. Judgments were on occasion severe with regard to industrial polluters, some even included prison sentences. Common law's incapacity to fight pollution on a global scale can be explained by factors linked to the practice and organization of differing justice systems. First, in the Anglo-American world it was costly to go to court, and so preferable for the ordinary citizen to come to some sort of an arrangement with the industrialists, either by mutually agreed upon private contracts or clauses to compensate for damages or inconveniences, or purchase of properties, or some other measure. Second, fines were always minimal and thus had no impact whatsoever. Finally, judges struggled with attributing blame. In the case of smoke, for example, how could they decipher the guilty party when tens, or even hundreds of factories were in operation? Justice could only rule on more specific cases and rights. But even then it was still difficult to calculate damages, or to adjust them according to the number of guilty parties and victims to compensate. Regulation or legislation. Faced with such legal impasses and a continual rise in pollutions, the justice system became ineffective and incapable of managing these new troubles. More and more frequently, the search for solutions turned to public authorities and the development of local or national regulatory controls. This phenomenon was common in Great Britain from the beginning of the 19th century, but only became an issue in the United States at the end of that century. Even if liberalism slowed the process and favored local over national initiatives, the move towards state administration was evident. As such, from the beginning of the 1840s, industrial smoke reached such unbearable levels in Great Britain that particular cities took matters into their own hands. The Municipal Corporation Reform Act of 1835 reorganized and standardized municipalities' powers. Heretofore each municipality had functioned independently. Amongst the newly laid prerogatives was the guarantee of public health and safety for all citizens, street sanitation, fire prevention, provision of drinking water, and waste management. In Manchester, the best-known case, local courts of justice, the court leet, deteriorated, inflicting fewer and fewer fines and, through collusion of interests, proved especially lenient toward one industry considered a pillar of local identity. The court leet was abolished in 1846 and replaced by municipal regulations, overseen by police commissioners. Nuisance inspectors were employed from the beginning of the century, and Manchester experimented prematurely with a local policy to regulate pollution without judicial oversight. It was no success. The Manchester Association for the Prevention of Smoke, 1842, pushed the city to pass the Manchester Police Act in 1844, which enforced fines for industrialists, and in 1847 the municipality created a smoke inspector position to collaborate with manufacturers to improve the situation. Other improvement acts, intent on reducing the level of smoke, were adopted during the 1850s in Birmingham and Sunderland, 1851, Newcastle, 1853, Leeds, 1856, and eventually by most other large cities in Britain. In 1846, and again in 1854, Liverpool passed a Sanitary Amendment Act, which hardened the fight against smoke. A health council was formed to monitor the measures put in place to control industrial pollutants. A nuisance inspector gave out 653 fines between 1854 and 1866. In Birmingham 360 were issued, and 445 in Sheffield in the same time period. In London the situation was particularly complex due to the convolutedness of metropolitan jurisdictions. In 1841, the Common Council requested a report on industrial smoke which led to a parliamentary interrogation. The idea to regulate smoke emissions took shape and, in 1851, the City of London was granted the right to fine manufacturers for smoke emissions, but only within its local districts, which excluded a large part of the metropolitan area. The 1853 Smoke Nuisance Abatement Metropolis Act ordered all owners of industrial furnaces, and not just those run by steam engines, to burn their smoke. By 1887, some 30 inspectors were employed full-time to oversee compliance with the 1853 Act. In 1857, the metropolitan area also created the Thames Conservatory Board, charged with monitoring the purity of the river. In 1870, the Metropolitan Board of Works ordered all offending manufacturers to move their businesses outside of city limits. In spite of all of these efforts, municipal policies were often limited in their effectiveness due to a lack of means for in-depth investigation or intervention. Typically, fines were set so low that they hardly acted as discouragement. There was a £5 maximum in Liverpool, even less in Manchester. Authorities were reluctant to hinder industry. Rather, they practiced persuasion and encouraged technical changes. In London, after a few months of zealous enforcement of the 1853 Act, during which 124 convictions were handed out, industrialists succeeded in reinterpreting the ruling to benefit themselves. After 3 decades of experimentation, one can only remark on the failure of local regulations. By 1860, pollution levels had reached unprecedented highs. These local failures forced the state to intervene. If the state intervened early in overseeing labor in Great Britain, with the creation of the post of inspectors of manufactures in 1833 and the vote of several factory acts regulating the dangerous activities like the mines or the railways, environmental regulation came later. The Smoke Prohibition Act of 1821 for smoke emitted by steam engines rapidly fell by the wayside. However, with pressure from various associations and members of Parliament, a Parliamentary Select Committee on Smoke Prevention was finally created in 1843. Upon investigating pollutions in Manchester, Birmingham, and Liverpool, its members agreed on the necessity of national legislation, without actually referring to the French model. Drawing on the works of Chadwick, and with the creation of the General Board of Health, several laws gave local authorities increased power to control pollution, such as the Health of Town Act, 1847, the Public Health Act, 1848, or even the Nuisance Removal Acts, 1846, 1848, 1855. Above all, the 1875 Public Health Act, from which London was excluded, put imperative structures in place, such as health officials, which allowed private individuals to have access to a justice of the peace. But, despite these unifying sanitary measures, these laws did not directly address the problem of industrial pollutions, and thus did nothing to lessen growing anxieties. After the 1858 Great Stink of London, royal commissions were put in place to improve the river's water quality. Virulent gas emissions from the chemical industry added to the black coal smoke. In 1862, at the request of Lord Derby, a Conservative parliamentarian, two-time Prime Minister in the 1850s, and property owner near Liverpool, the House of Lords established a select committee charged with investigating caustic soda factory pollution and ways to reduce it. Evidence collected by the Upper House, a space where landed property owners addressed their concerns, revealed the extent of the problem. Raw waste, burned fields, and sullied waters, most notably around Widnes and St Helens, near Liverpool. Caustic soda manufacturers were accused of harming the country's agriculture and menacing private property. Public authorities could not ignore these results and passed an Alkali Work Act in 1863, which would endure for 5 years and be the first British law to specifically target industrial pollutions. Certainly audacious in a country where the new elite class was largely liberal, this law only applied to the manufacturing of caustic soda. It severely limited toxic emissions. 95% of hydrochloric acid was required to be condensed, and for the first time ever a body of state inspectors, under the direction of the Home Office, was mobilized to monitor its application. Under the direction of Robert Angus Smith, 4 inspectors were charged with inspecting factories in order to enforce the new rules. Smith's approach was more preemptive than punitive, which might explain why British soda manufacturers ultimately chose to obey the law, rather than not. They saw some advantages to this legislation as a means of protection from lawsuits and mounting pressure by locals. Manufacturers were all placed on an equal footing thanks to emission standards that applied to everyone and went beyond local regulations. Moreover, this legislation, much like the 1810 law in France, protected industrialists from being accused of public nuisance, which kept them out of the penal justice system. After the Alkali Act, there was a shift toward technical improvement in the fight against pollutions. This approach, even with limited resources, was successful and in 1868 resulted in the renewal of the law for an unspecified amount of time. In 1874, its scope was broadened to include other noxious gases as well as other industrial sectors that emitted acids and sulfur. However, after the emphasis on technical modifications had been in operation for several years, Smith noticed some adverse effects. The condensed gases had been emptied into rivers around caustic soda factories instead of into the atmosphere, and leftover sulfur from chemical factories had amassed. For each metric ton of soda produced, 1.5 metric tons of waste heavily laden with sulfur was generated. Smith expressed concern over porcelain manufacturing, cement factories, gas lighting works, salt manufacturing, and copper metallurgy, all of which emitted a great many toxic composites, including acids, arsenic, and antimony. In 1859, particularly concerned with copper factories' pollution, Smith coined the term acid rain. The copper industry's powerful magnates resisted accusations about its deleterious effects, all the while paying compensation to their neighbors. In 1878, members of a royal commission created to report on the subject said that, although the amount of acidic gas emissions from copper factories was impressive, there is no need to impose overly stringent measures which would negatively impact the future of these factories, and harm numerous people. In 1881, the Alkali Act encompassed 17 different types of industry for inspection. Subsequent Alkali Acts in 1891 and 1906 expanded its reach. Within the scope of half a century, under Smith's direction, he was chief inspector between 1863 and 1884, and that of his successors Alfred Fletcher, 1884-1895, and R.F. Carpenter. National legislation gradually replaced legal precedents of common law and municipal regulations, thereby demonstrating a change in scale of pollution. For a long time, water pollution was not regulated under national legislation. Indeed, the Public Health Act of 1848 encouraged cities and industrialists to dump their waste into rivers or the sea. Chadwick's famed sanitation system also encouraged this means of disposal. Moreover, the Alkali Act and its call for industry to condense acids before disposing of them further aggravated the problem. In 1876, however, the Rivers Pollution Prevention Act put the project of finding a resolution squarely in the hands of the justice system and local authorities. It also confirmed that residents had the right to pursue upstream polluters in a court of law, reinforcing common law and ensuring undeniable recourse. But its results were limited. The law failed to appoint competent authorities to police sources of pollution at the level of local watersheds, which consequently left authorities powerless. In 1893, a committee was appointed to examine the pollution of the Mersey and Irwell rivers near Liverpool. The commissioners could only attest to the deplorable state of both. State intervention in Britain, the most polluted country of the 19th century, had little influence on non-intervention policies in the United States. From the 1880s through the Progressive Era, 1890-1920, municipal laws began to dictate acceptable atmospheric pollution levels and fines in larger cities. Unlike the various groups in Great Britain who battled against smoke pollution, similar associations in the United States seemed to work with more gusto and intent. Each city had its own institution to address the smoke problem. In Baltimore, Boston, and Chicago, the health department took charge, while the Department of Public Works handled that responsibility in Pittsburgh. Philadelphia had its steam engine inspector do the job, Cleveland its police department, the construction inspector in Milwaukee, the public health commissioner in Rochester, and the fire department inspector in Cincinnati. The one fundamental principle shared by these various public health officials was an adherence to non-intervention. As such, when St. Louis introduced a stringent anti-smoke measure in 1893, the Supreme Court of the state of Missouri declared it illegal and unconstitutional. The city could only intervene against emissions that caused actual damage to inhabitants or property. In 1899, however, two acts of Congress on waste and smoke reinforced municipalities' authority in their fight against pollution. This new framework favored conciliation, with Chicago proving to be a model in the matter. In 1905, a federal Supreme Court judgment rejected a plea by sugar refiners, one of the biggest industrial polluters, against municipal police proceedings. In 1907, the mayor, Fred Busser, a coal merchant elected with the support of the business sector, created a smoke inspection service for the city, not only to reprimand, but also to counsel manufacturers on how to reduce pollution by improving their technical installations. Between October 1, 1909, and September 30, 1910, no less than 1,040 proceedings were filed against industrialists for smoke infractions, and fines increased to unprecedented amounts of up to $500. This new framework fostered collaboration among engineers, public services, and municipal associations, in order to encourage technical improvement. In 1907, the International Association for the Prevention of Smoke was founded in Pittsburgh. It became the Smoke Prevention Association in 1915. And in 1916, 75 American cities adopted anti-smoke ordinances. In 1917, the Smoke Abatement League in Cincinnati confirmed that the city's industrial emissions had been reduced by 75%. The combination of militant actions, municipal arbitration, and cooperation between the engineering and business worlds resulted in a notable reduction in atmospheric pollution in American cities before the Great War, at least in more affluent parts of these cities. Law and regulation. On the European continent, regulation models differed greatly from those in Britain and the United States. Generally, regulatory bodies had more power. The justice system's only task was to set the amount of potential compensation for damages to property. Against a backdrop of latent nationalism, legal experts in France exacerbated the contradiction between British common law and specific legislation on industrial pollution, like the 1810 law. In 1854, the jurist Désiré Dalloz, a great admirer of French administrative organization, criticized the blatant injustices of the common law model. He who wishes to found an industrial establishment usually makes an informal request in the neighborhood where he wishes to build, and rarely is the result of this request unfavorable. Confident in this result, he builds his factory, installs its machines, and commences work, but soon demands for damages are made by numerous parties. Neighboring property owners speculate for the most part on the sort of damages they can claim, work to make a case, and pursue it on behalf of one amongst them before the courts. If he is rich, and if his establishment is productive, he may emerge the winner of this clash. Conversely, if the case is more expensive, he may be ruined by legal fees and high damage costs, forcing the closure of his enterprise. The abuse is no less serious if an industrialist, with large amounts of capital, opens a factory in a poorer district, and therefore need not fear any legal proceedings being brought against him. During the 19th century, the administrative and preventive logic of France's 1810 imperial decree, to control installations that were sources of nuisances and risks, was used as the benchmark for the majority of European countries. In France, regulations were not altered until 1917. Regional prefects and the Minister for the Interior, sometimes the Minister for Commerce, retained full authority, and preserved the integrity of the law based on the industrial circumstances which had presided at its creation. As a result of changing times, its application adapted through legal precedent at the discretion of those involved, through industrial changes, and as a result of new industrial sectors. But the premise of the three classes of factories and workshops remained unaltered. In this way, the nomenclature attached to the law was always expanding. It was completely rewritten in 1866 and 1886, with additional tables added in 1872, 1879, and 1881. This system of updating the law meant two things. First, French pollution regulation was constantly out of date, and reacting to change. Industrial innovations and emerging sectors were up and running long before they were documented on paper, often leaving public authorities to hastily scramble to resolve new sources of pollution. It also meant that industrialists often sought to use machinery that would classify their factory as a level 2 or 3, rather than 1, because public officials' surveillance of the former classes was less stringent. The decree therefore implicitly favored technical improvement, but nonetheless was rarely coercive. Once a polluting establishment was authorized, there was rarely an issue with authorization. It was practically impossible to shut it down, save in a few exceptional cases where a change in the nature of the enterprise was duly noted. But procedures in this particular instance took so long and were so complex, going as far as the Council of State, and industrial strategies and pressures to preserve their practices were so strong, that this rarely happened. In this way, permission to open a factory essentially equated with permission to pollute. In addition, many industrialists avoided the required authorization procedures and drew up mutual agreements with their neighbors. Local mayors possessed little power in the face of this complex administrative machine. Initially hesitant to have their staff get involved in the process, they rarely objected to polluting industries establishing themselves in their communes, even toward the end of the century when growing worries about health led, on occasion, to contemplating a form of urban planning. Figure 6.1. The nomenclature for polluting industries classed in the first order. Source: Henry, Naples, Manuel de Hygiene Industrielle, Paris, Masson, 1882, 34. But was the French public regulation system totally powerless to protect the population from industrial pollutions? The answer depended upon context, in particular reactions from neighbors, often property owners, and those of public health boards. In certain instances, the plaintiffs found sufficient resources to rally and force the administration and industrialists to reduce pollution levels, by moving installations, introducing filtration and condensing equipment, or reducing production volume. Some health councils could be quite averse to and harsh on polluting industry, and property rights were, in some circumstances, sufficient to protect property income not involved in industry. Overall, however, the law did not aid in drastically reducing pollution. The means to do so were ignored, leaving civil justice to regulate any financial damages owing. Established under Napoleon and the First Empire, the basis of France's legal system was adopted in many European countries, although incompletely and with very different national nuances. After Belgian independence in 1830, the Royal Decree of 1824 was confirmed. The decree was heavily influenced by the French Decree of 1810, although for a time the judicial courts regained importance. In 1847, for example, the Court of First Instance in Liege declared itself competent to judge the request for the closure of the zinc factory at Vieille-Montagne. The following year, the Court of Appeal in Anvers ordered the closure of a brickworks because of damages it had caused to locals. Thereafter, case law took a different direction and the Court of Cassation finally reaffirmed the primacy of administrative authorization for judicial decisions. Under the guidance of new liberal powers who expressed confidence in science and industry's capacities to resolve its problems, the law was reformed in 1849, and again in 1863, much to the benefit of industrialists. The state's attitude demonstrated a certain pragmatism, and the system evolved in conjunction with the political balance of power. To wit, in 1886 and 1888, the Belgian Socialist Party gained enough ground that it succeeded in bending the legislation to protect the health of factory workers. In the Netherlands after 1830, the 1824 decree was also passed there by the Supreme Court in 1846. The state's role was also altered, and municipal administrations were given the power to retract establishments' authorization and, in time, to order the closure of manufacturing plants and workshops. The power to grant permission to set up establishments was completely given over to municipalities under the nuisance laws, Hinderwit, of 1875 and 1896, with recourse reserved for the State Council. There as elsewhere, the law favored industrialists, who often circumvented the regulations by setting up establishments without permits and operating with an air of fait accompli. In the German states, pollution legislation remained marginal. In Prussia, for example, the 1832 and 1848 ordinances for steam engines were supposed to bring them into line with technical standards designed to limit smoke emissions. These were hardly enforced. From 1845, if insalubrious establishments required state authorization, authorities seemed less inclined to obstruct industrial development there than in France. Following the formation of the Reich in 1871, Prussian administrative services spread throughout the German Empire, and commercial law ordered that no factory could be a nuisance to neighboring properties. With no real central administration to which to turn, cities and the Länder were the first to take action. Anti-smoke municipal ordinances were thus adopted in Breslau, 1874, Nuremberg, 1876, Brunswick, 1883, Stuttgart, 1884, Dresden, 1887, Heidelberg, 1890, and Munich and Freiburg, 1891. Berlin remained under state control. Unlike in the United States, the civic movement in the German Empire was loosely organized, although in Austria an association to combat smoke and dust did exist. Municipal regulations remained fragmented with little coherence. The few cities that did adopt ambitious solutions, such as Hamburg with its Association for Fuel Economics and the Reduction of Smoke, were anomalies. Overall, legislative application proved to be indecisive, despite a concerted effort by engineers. Even a national scientific journal, 1910, Roux und Staub, Smoke and Dust, was dedicated to the subject. In particular regions, the Ruhr Basin for example, or in strategic sectors like chemistry, regulatory policy throughout the century seemed to lean toward the assumed protection of industry. In other, less industrialized and less polluted European countries, similar trends unfolded. For example, after Italian unification in 1860, a piece of legislation on insalubrious establishments was adopted in 1888. It focused on the location of factories, where they could pollute without restriction, and was largely ineffective. The fight against pollution ultimately lay with local authorities, who were prompt to aid any activities likely to boost the country's industrialization and spur its economic growth. Outside of Europe and North America, industrialization was less advanced and there is painfully little accessible documentation, apart from some on European colonies. Japan is one focal point we can use to learn a little about regulations in Asia. The beginning of the Meiji period saw the introduction of mercantilism and economic nationalism, which promised a modern industrialization whose goal was to ensure independence and power for Japan. Abolishing its pre-industrial regime, Japan underwent an institutional metamorphosis that would shake up pollution regulations, similar to what happened in Europe and North America at the end of the 18th century. At the majority of industrial sites, as with the tragic case of the Ashio mines, pollution was managed through the payment of compensation for damages. No other controls were instituted before 1896, at which point a law dealing with rivers was adopted to protect local residents. In 1897, a ministerial inquest provoked the Pollution Prevention Decree, which launched the state's involvement in environmental matters. But this decree, which sought to bring parity between property owners and included technical provisions, was almost never applied. As a result, a new ministerial commission led by scientists was put in place in 1902. In its report, the link between pollution and industry was clearly established, but it suggested using the Western world's model to minimize negative repercussions on health, and stated that pollutions dispersed into the environment were acceptable. The solution to the problem was found in reconfiguring the waterways. Rather than closing the mines responsible for polluting the rivers, a regulation that pre-existed the Meiji period, the new quick fix was to reconstruct nature with the help of engineers, in step with industrialization. This, according to Robert Stoltz, marked the beginning of state-controlled nature, indeed, the control of nature, in Japan. In India, as industrialization took hold in cities such as Bombay, Cotton, Calcutta, Jute, and New Delhi, the measures put in place echoed those in Europe. Weak laws, prejudiced against older putrefying artisanal crafts in favor of the newer, high-capital industries that enjoyed greater access to power. Varying inspection methods were set up, notably in the fight against smoke. But all lacked sufficient means or enforcement. Bombay got as far as relocating all abattoirs to the outskirts of the city in 1867, but in Bengal a Smoke Abatement Act, 1863, fell into disuse. In this same region in 1905, after the Bengal Smoke Nuisances Act had been passed, only 16 of the 10,000 cases of excessive smoke reported by inspectors were brought before the courts. In 1915, industrialists pressured to have the act abolished, arguing predominantly for more open markets for business, employment, and technical improvement, as was the case in Europe. Can we then conclude from this overview that national regulatory systems for industrial pollutions existed in the 19th century? We must take into account that social, economic, and political contexts created very different situations. However, beyond the scope of judicial and institutional choices, certain common tendencies emerged. In the first place, state intervention occurred in all countries because pollution grew to be problematic at a national level and therefore could not be dealt with solely under municipal jurisdiction, as had been the hope. The fact that the sovereign public power intervened in these countries where industrialization was revered meant that pollutions from industry evaded criminal proceedings more often than not. In countries with common law, it had long since been possible to pursue a polluter through public nuisance proceedings, and this had had the potential of resulting in prison time. But with the preventive intervention methods of local and national administrations, recourse to criminal justice became gradually less accessible, leaving civil justice as the only acceptable means for compensation. The changeover was even more apparent in countries with Roman law, in which the administration issued authorization, where the state had decided that there was no risk to public health. In this case, an authorization could not be withdrawn and thus it was up to civil justice to decide on compensation to third parties. Naturally, the system had its flaws, but in general the administration worked to avoid criminal proceedings. For example, in France, a fishing law from 1829 gave criminal courts the right to pursue an industrialist for pollution in the case of fish mortality. This possibility was used very infrequently and, although a judgment by the Court of Cassation in 1859 confirmed the content, a decree in 1870 added the possibility for a settlement between disputing parties before criminal proceedings might ensue. These legal compromises and accommodations bore witness to the industrialist spirit of the central administration. Industrialists could no longer be considered delinquent or criminal in the century of all-conquering industrialization. Where industrialists eluded penalties for environmental damage, compensation to injured third parties did increase. Apart from notarized, mutual, and private agreements, about which we know very little, industrial polluters managed to assuage the deleterious effects of their establishments by way of paying compensation to plaintiffs. Soda and aluminum manufacturers in the Maurienne province and producers of sulfuric acid in Bauches-du-Rhône, Gard, Alsace, Lorraine, and the Namur province in Belgium all managed to appease complaints with monetary payments, hardly onerous for them but substantial for their poorer plaintiffs. Similarly, zinc manufacturers in Liege, in Belgium, and in Vives, in the Aveyron department in France, included financing for private contracts and legal fees linked to pollution in their company's budget. This generally accounted for 1% of their operational costs. Apart from this negotiated tax, another strategy industrialists like to use involved buying up neighboring properties, which would create a larger nuisance buffer, remove prospective plaintiffs, and hopefully reduce or avoid compensation payments. Inasmuch as this constituted a remarkable adaptation to the new industrial landscape, in hindsight it affords the historian an opportunity to reflect on a real commodification of nature. It is hardly surprising that in the end the results were the same, regardless of whether pollutions were governed by a liberal system or an administrative one. Apart from the law, two things counted above all else: the industrialist project, and thus the law's ability to adapt to the economy, and the pace of innovation, both of which served to prioritize industrial interests and activities. Public action was often content to aid the process in adapting the law to meet the necessities of production. The dominant course of action was definitely that of sacrifice, targeting particular areas and populations in the name of public interest, as it related to industrialization. If the law seemed inadequately equipped to deal with nuisances, this might have been because other means had the upper hand in the battle against pollutions: technical progress, recycling, and dilution. The best practical means. Initially, industrialists did not view the intervention of public powers as a positive move. With systematic opposition and lobbying, they argued that as a result of restrictive regulations they were incurring extra costs that impacted their accounts. Added to labor blackmail was the worry about a national legislation that would negatively impact international competition, which was becoming ever more prevalent. In order to avoid any regulatory interference, industrialists employed a preemptive practice of technically improving their establishments to reduce pollution, a system already employed in Europe since the beginning of the 19th century, and which became widespread, reaching as far as Japan. Confidence in industry's capacity to regulate and solve its own problems became ever stronger. Improving technical know-how was the perfect way to appease the critics. Even if industrialists were not inclined to research new methods for pollution reduction of their own volition, they were encouraged to do so under pressure from local residents and public powers, or because they needed to make the byproducts of their industry more profitable. By mid-century, a frenzy of technical innovations was underway in response to regulations by authorities to reduce industrial smoke pollution. Countless innovations were legitimized in the name of public health and well-being, as every polluting sector made some attempt to adapt its manufacturing processes. Thousands of cleanup operation agreements and technical reviews, published around the world, took charge of sharing the details. It is worth examining two representative production methods typical of the time. The first example drew on traditional artisanal practices while the other exemplified the habits of more technologically advanced industries. Plant textile retting was tolerated less and less, but its prohibition was difficult in part because of its importance and also because its establishments were widely scattered. In the latter half of the century, in France, Belgium, Great Britain, and the United States, multiple new innovations mechanized the insalubrious retting process. Retting was moved into more controlled settings in factories, carried out in vats filled with artificially heated water, using mechanical and then chemical methods. The so-called Schenck, or American process, was tried out in Ireland in 1847 with the support of the Flax Society in Belfast, which had been created to encourage plant textile development after the Great Famine had ravaged the country. In 1850, the French Minister for Agriculture sent the chemist Payen to investigate the salubrity of this new process. Prussian engineers soon followed. Amongst the new innovations was fairy electricity, celebrated continuously after 1880 for its capacity to render coal burning and gas lighting unnecessary. When electric lighting was developed after 1890, the principal argument in its favor was that consumers noted how much cleaner it left the air. Electricity was supposed to pave the way for hydroelectricity, green coal, from rivers, and white coal, from glaciers, which unlike black coal, would decrease pollution. However, in spite of high hopes, nuisances continued to present themselves, as the majority of electricity was produced from coal-powered plants. Consequently, in 1890 New York City, the leading producer of electricity, was faced with a concerning level of atmospheric pollution. Electricity spread so quickly that rather than lowering levels of pollution, it actually added to the emission levels. Although some sites reduced their smoke levels thanks to electricity, this new power source simply moved the smoke pollution to where the generators were located. Rather than embarking on an impossibly long inventory, two principal problems which faced industrial societies in the 19th century might serve as examples: smoke and acidic and sulfuric vapors. In the first case, smokeless furnaces became the archetypal technical device designed to resolve atmospheric pollutions. Great Britain played a pioneering role in its transnational dissemination of knowledge and technical discussion. British experiences were closely watched by other states. Even though smoke-reducing apparatus appeared concomitantly with the first steam engines, they only became more widely available after 1825. In swift succession, many other methods were adopted, improved, and abandoned. Various machines to condense or filter smoke, or even to wash it by passing it through jets of water, were conceived, but improving combustion remained the central concern. This involved circulating oxygen and experimenting with double furnaces. The second furnace was fed charcoal, which permitted an undeniable reduction in coal smoke. Numerous models of mechanical loaders refined the process. With machines loading the coal, the doors to the furnaces were opened less frequently, resulting in more optimal and regular combustion. Among the more successful furnaces were those patented by British engineers: Charles Y. Williams between 1838 and 1841, and Fairbairn in 1844. London's 1853 anti-smoke ordinance, and a similar one in Paris in 1854, stimulated further innovations. In 1855, the engineer Adolphe Mill, from the Pont-Saint-Chauchet Technical College, testified to the diversity of devices available on the market in London. He also observed the prevailing optimism the new technologies provoked. If the smoke around us has not disappeared high above outer chimney, it has otherwise been notably reduced. This optimism, shared by industrialists and public powers, could not entirely conceal the failures encountered throughout the century. In 1894, a report presented in France to the Society for the Encouragement of National Industry, SAIN, affirmed that the problem of eliminating smoke emissions from industrial furnaces has not as yet a general or truly practical solution. The multitude of promises and technical processes actually had a counterproductive effect in Germany and the United States. Presented with such a range of processes, their high costs, and their low practical efficiency, industrialists became skeptical about combating pollution at all. Renewed attacks on environmental associations saw their cause weakened and discredited. Authorities were aware that the technology was imperfect, often fragile, costly, and restrictive. Further, even after installing the smoke-reducing technologies, industrialists were loath to use them to their full potential. As a result, municipal and national regulations engaged in a politics of pragmatism. They specified that industry should consume as much smoke as possible. This was the priority, but rather than rigid preventive measures and metrics, industry was left to demonstrate its own efforts. The guideline, consume or burn as far as possible all the smoke, and the request to use the best practical means, were vague enough for manufacturers to accept and interpret as they saw fit. The belief in improved technology actually led to a surge in smoke-reducing equipment. Technical progress was, however, undeniable. By the end of the century, smokeless furnaces had advanced thanks to new apparatus. Therefore, in order to understand the continuing increase in smoke levels in Western cities, it is important to consider the rebound effect. In 1865, the economist William Jevons explained that increases in energy production efficiency led paradoxically to more, not less, consumption. The same reasoning could be applied to industrial smoke. Within the workings of a single furnace, fumes were largely diminished, but as more factories were permitted or tolerated, global pollutions increased by dint of the aggregate number of pollution sources. Faced with this logic, municipal police and courts were powerless, because the industrialists' willingness to install and use modern processes generally managed to silence plaintiffs. Added to this was the difficulty of achieving a verifiable measurement of pollutants. It is shocking to discover the lack of rigorous criteria dealing with emissions surveillance, and how little progress had been made in this domain since the first parliamentary inquest in 1819. Attempts by the French engineer Maximilien Ringelmann in 1898 to scientifically define and quantify smoke density were circulated in Europe and the United States around 1910. These measurement grids, containing a series of differently shaded gray squares with which to compare against ambient smoke, were rudimentary and difficult to manipulate. Nevertheless, they provided the means for anti-smoke militants and local associations to acquire a counter-expertise in the smoke pollutions debate, by gauging and measuring smoke for themselves. The condensation of acidic gases followed the same logistical path. The production of caustic soda was particularly problematic. So, too, was the production of sulfuric acid and nitric acid, as well as all metallurgical production, such as refined copper from iron pyrites. Amongst tested condensation methods, the so-called Gay-Lussac tower, named after the French chemist who first introduced it to the Saint-Gobain factory in Chauny, north of Paris, at the end of the 1830s, is certainly the best remembered. Although a series of trial and error improvements enhanced its performance, the basic principle hardly changed. It involved passing the acidic gas through towers filled with brick, carbon, and/or lime, into which a highly concentrated sulfuric acid was added to condense the gases. After 1860, the Gay-Lussac tower was generally used in industry in France and Belgium. In Great Britain, the chemist John Glover improved the process after 1859 and obtained a condensation close to 80%. The United States adopted the principle after 1880. Jacques-Louis Kessler's towers, put into use in 1877 at his Clermont-Ferrand factory, were also popular around 1900 in France, Great Britain, Germany, the United States, and Russia. The quest for new innovations that would free industrialists from public regulations and court cases was particularly advanced in copper metallurgy. Beginning in the 1860s, the most efficient systems were developed by Moritz Gerstenhofer, a German industrialist, even if they only succeeded in condensing 20% of the sulfur. Condensation with the aid of electric flux, invented in 1886, was not widely used before the First World War. But it was the soda industry that posed the biggest problems, especially since until the middle of the 19th century hydrochloric acid use was so low that manufacturers were reluctant to condense it. It was already known that hydrochloric acid was condensed using water and lime. In 1836, the Englishman William Gossage designed the first truly effective absorption tower by passing the gas through long pipes and towers into a pool of water. Having become a copper refiner in Wales in the 1840s, and then in Widnes in the 1850s, where he linked copper refining, from imported copper pyrites, to the production of sulfuric acid and soda, his experiments gave him a yield of 90% condensed liquid. However, Gossage towers did not find favor until requirements of the Alkali Act of 1863 put them into general use in factories in Great Britain. The next step to extract chlorine from the condensed product was carried out after 1880, to the benefit of the textile and cellulose paper industries. By 1900, Gossage towers and their substitutes were used around the world, in particular in the United States, which became the world's leading producer of sulfuric acid. Figure 6.2. The Gossage Tower in the Hutchinson Sulfuric Acid Factory in Widnes, 1880. Source: Georg Lunge, A Theoretical and Practical Treatise on the Manufacture of Sulfuric Acid and Alkali with the Collateral Branches, London, John Van Vierst, 1880, 2-252. These few examples permit some general conclusions. Far from reducing pollution, faith in technological advancements conversely led to its increase instead. Moreover, it established a technical fatalism which favored political inaction and hope for hypothetical progress in the future. Often a reduction in one form of pollution produced secondary effects, through either the rebound effect, as in the case of smoke, or by simply displacing the source of pollution. Thus, after 1860, with the success of removing hydrochloric acid from the air, rivers bore the brunt of the transferred pollution until after 1880, when the waste was disseminated and used in the paper and textile industries. Finally, these technical innovations became a part of discussions surrounding recycling, which industrialists latched onto in order to justify their activities. Since the chemical industry posed the most significant pollution hazards, the industry was tireless in inventing new uses and reuses for its byproducts. The perpetual race for innovation only complicated the nature and spread of pollution. Recycling, trend to crisis. Instead of being spurned as threats, toxic substances and waste were embraced as assets to be valued, materials to be re-injected into production cycles and born again in new form and for new purpose. The middle of the 19th century saw recycling become more of a trendy endeavor, although the term recycling had yet to be coined. It was perceived by many as the best option to deal with the problem of unsolvable pollution, a promise of prosperity and abundance, a full-fledged way to manage industrial residue. The idea of reusing waste was not a new one, of course. The novelty, therefore, lay less in the systemization of this practice. Sadly, though, untreatable and unrecyclable waste was on the rise, and more in its use as a means to justify industrialists' activities that emitted highly toxic byproducts. Recycling had long been concerned with waste for strictly agricultural use, especially manure and human excreta used as fertilizer for their nitrogen content. Victor Hugo noted in a famous chapter from Les Miserables that all the human and animal manure that the world wastes, if it were put back into the land instead of being thrown into the sea, would suffice to feed the world. The socialist philosopher Pierre Roux, while in exile on the island of Jersey, developed his theory on circulus, the idea that waste feeds production, in a circular vision of material flux. One proposed solution to remove excess waste from cities was sewage farms. They were cost-efficient and, mid-century, were an exemplary demonstration of the benefits to be reaped from recycling. Historians have studied at length this thrilling enterprise of revitalizing the countryside purged of its nutritive elements by hungry cities. In return for food, the countryside received the elements necessary for replenishing its soils in the form of urban wastes. This urban agricultural cycle demonstrated cultural, spiritual, and political resilience. After industrialization, it also witnessed expression through technical and chemical efforts. Following London's example, numerous cities sought to fertilize surrounding land with sewage carried through pipelines, sometimes over long distances. Not surprisingly, these sewage farms became cause for debate about the supposed virtues of this mode of fertilization in the hinterlands of Berlin, around Edinburgh, and Brussels, as well as on the plains of Gennevilliers downstream from Paris. Industrial waste was also partially re-employed in agriculture. Thus, byproducts from the production of rapeseed oil, flax oil, and other oleaginous seeds were turned into oil cakes to be used as fodder for livestock. This consequently gave rise to another international business in the 19th century. In 1863, on his experimental farm in Essex, John Joseph Mechie attempted to systematize the circulation of oleaginous seeds on a much larger scale. Dregs from the steel industry were used as a more economical source of phosphorus, a good substitution for bones, which heretofore had been used in chemical operations to produce products rich in phosphorus. Essentially, phosphorus could be extracted from calcium carbonates that had absorbed phosphates during the steelmaking process. But the principal source of industrial waste introduced into agriculture in the 19th century was from gas lighting. The distillation of coal produced ammonium sulfate, which contained nitrogen, but industrialists were not sure what to do with it. During the 1870s, agriculture in Britain consumed 46,000 metric tons of this ammonium sulfate per annum. But its nitrogen content was inferior to that of guano or sodium nitrate mineral imported from Latin America. As a result, farmers were reluctant to make use of this bluish, damp, sticky, and foul-smelling substance, which also contained enough sulfuric acid to corrode farm machinery. However, the reformed 1881 Alkali Act encouraged the use of this troublesome product, which otherwise contaminated factory depots in the heart of cities as it sat unused. By 1913, some 400,000 metric tons of ammonium sulfate, the byproduct of gas factories, were being put to use. The majority was exported to Germany, where beet growers were less discerning. Even though the use of these industrial byproducts may have remained limited, the constant promotion enhanced the economic policy of industrialization and seemed to justify the promise to recycle industry's waste and toxic products. Recycling was mainly encouraged within industrial sectors, particularly within the chemical industry, where chemists, technical experts, and engineers attempted to find ways to reuse the waste in place of having to simply dispose of it. From 1862 to 1868, at the government's request, the engineer Charles de Freycinet, a member of the Corps des Mines, and future Minister of Public Works between 1877 and 1879, led an inquiry in England and Europe, notably Belgium and the Rhine region in Prussia, to study industrial sanitation. The results were published in various reports that offered a very detailed array of remediation or depollution strategies and practices for the reuse of dangerous substances available at the time. Freycinet asserted that, whereas industrial residues may infect the soil when they are buried indiscriminately or dumped without measure, they can be rendered inoffensive and even useful when they are spread on land in a methodical and suitable manner. Certain major industrialists specialized in recycling contaminated matter. Payen and Frederic Kuhlmann were prominent among them. The latter made his money by recuperating byproducts from lead chambers for use in paint production, and waste from chlorine soda plants to manufacture large quantities of barium chloride. In the soda industry, where each metric ton of soda produced incurred 2 metric tons of sulfur waste containing 90% sulfuric acid, it was tempting to find a way to reuse these foul-smelling residues to recuperate the sulfur and acid content. The former otherwise had to be imported from Sicily at high cost. In 1837, Gossage enjoyed some modest success in treating dregs with carbonic acid to yield hydrogen sulfide, which when burned to ashes, furnished sulfur dioxide. The sulfur dioxide was subsequently reintroduced into the production of sulfuric acid. The Alkali Act of 1863 standardized this practice. The Mond process, named for Ludwig Mond, succeeded in recuperating 40% of sulfur from soda factories in Liverpool. As a guarantee for innovation and profit, recycling contributed to recharacterizing pollution as primarily a technical problem. Chemists involved with coking and the production of lighting gases searched for ways to enhance the many byproducts of the coal industry: tar, ammonia, bitumen, and other volatile compounds. This was for all intents and purposes the beginning of carbon-based chemistry. The extremely polluting nature of operations within this branch of chemistry was immediately evident, with even parent Dutch Aycklet himself admitting as much with respect to the distillation of tar at gas plants. But in his treaty in 1870, Freycinet actively promoted the recycling of carbon derivatives. At this time the quantities in circulation were still quite limited. For example, benzol, a toxic mixture of benzene, toluene, and xylene, was extracted from coal to make aniline, but it accounted for only 1% of available tar, itself a byproduct of coal. Another 0.7% was used to produce naphtha. The majority of tar and other residues from the gas lighting industry, whatever the champions of recycling might have claimed, actually continued to be burned or buried. However, at the end of the century, carbon-based chemistry underwent considerable developments, notably with progress in organic chemistry and later the development of recovery coke ovens in Germany. These new ovens recovered byproducts such as tar, benzene, anthracene, and phenols. Such symbiotic potential helped make sense of the regularity with which chemical plants were established near coal mines. Benzene was a precursor to the synthesis of numerous organic compounds. In 1845, the British chemist Charles Mansfield isolated benzene in coal tar, and then in 1849 began producing benzene from coal on an industrial level. In 1869, in France, Berthollet was chemically deriving benzene from acetylene. This very toxic, carcinogenic compound was used as a solvent in glue, varnish, paint, and ink. It was also applied in dry cleaning and degreasing metals. In the middle of the century, Great Britain began producing aniline industrially for use in dyes and artificial colorants. In 1856, William Perkins discovered morvaine, a colorant derived from aniline, and founded in Greenford, a London suburb, history's first factory for the production of synthetic dyes. At the same time in Lyon, the Renard brothers launched production of fuchsin, from aniline and toluidine, which resulted in byproducts such as benzene and toluene. Germany would become the world leader in industrial recycling of coal for the dye industry. In 1869, chemists Karl Graebe and Karl Libermann, who worked for BASF, Badische Aniline und Soda Fabrik, took out a patent for the synthesis of alizarin, red in color, which was derived from anthracene extracted from coal tar. Vegetable madder, the previous source for the color red, was quickly abandoned. Likewise, the plant source for indigo blue was replaced by its synthetic equivalent, manufactured from benzene and aniline, and marketed by BASF in 1897. By 1914, Germany was producing 85% of the colorants used globally and became one of the most chemically contaminated places on the planet. If a large number of intermediate products or byproducts of the chemical industry stimulated the creation of new branches of activity, it is important to recall that more and more residues were thrown away or burned, and that the overall quantity of waste produced increased, despite the ongoing promotion of recycling. This led to the creation of garbage dumps and incinerators, two ultimate destinations for waste whose function and locations were emphatically debated in every country. Once again, Great Britain pioneered the way with the first garbage incinerator put to use in the 1870s. Popularity grew, and by 1893 55 cities were equipped with incinerating devices. Britain exported its incinerators around the world, thanks to its colonial empire, Calcutta, Madras, New Zealand. At the beginning of the 20th century, the engineer Walter Francis Goodrich listed the places in the world where the British destructor had been installed. His list was published in works that celebrated the wonder and superiority of British sanitation systems, which converted incinerator heat into electricity. From 1905, New York and other American cities built incinerators. However, incineration of urban waste was slow to spread to the European continent. The first commitment to incineration was found in Hamburg in 1892, following a cholera epidemic. In France, incinerators appeared very gradually, perhaps because of the continuing exchange between city and countryside. Dilution, the ultimate solution. Throughout the entire century and all over the world, taking into account the limits of administrative and judicial regulations and imperfect methods of recycling, the preferred method for dealing with pollutions was dilution. Dilution was both atmospheric and aquatic, but separating the sources of pollutions from populated areas remained a favored practice as soon as railways made that a viable possibility. In his 1870 treaty, Freycinet perfectly summed up the guiding principles for authorities and technicians. The isolation of factories is the optimal means to achieve our goals. The next best option was to construct tall chimneys to disperse toxic emissions high up into the air because the damage caused must, to say the least, be diminished as a result of the chimney's height. The third method was that which we refer to as the natural outlets, dumping into fast-moving rivers and directly into the sea. Uncertainty on how to best evaluate air and water pollution meant that the enduring belief in the Earth's ability to absorb harmful substances and to perpetually regenerate itself held strong. Arrhenius's warnings about carbon emissions gained little traction. In 1901, the German chemist Clemens Winkler, a member of the Royal Science Academy of Sweden and a professor in Hamburg, asserted that the volume of coal consumed disappears without a trace into the vast ocean of air. Tall chimneys remained costly to build and maintain. Without pressure from their neighbors, industrialists were reluctant to invest in building them. Between 1830 and 1850, minimum height imposed on the chimneys for factories with steam engines was set between 20 and 30 meters, with individual countries setting their own standards. But already a race to build the tallest chimney had been launched by the chemical industry. In 1841 to 1842, two chemical factories built smokestacks 124 meters and 133 meters tall in Liverpool and Glasgow. In Manchester, some exceeded 100 meters, and in 1857 Peter Spence, an alum manufacturer, proposed constructing a 200-meter chimney that would collect the entire city's smoke emissions and resolve the problem once and for all. This project failed, however, due to the public financing it would have needed. Copperopolis, Swansea, devolved into an industrial oven. Feeble protests from citizens did little to slow the expansion of the city's smokestack forest, between 20 and 50 meters tall. Conversely, in 1860 in the neighboring town of Llanelli, local protests led to the construction of a chimney almost 100 meters tall. Constant disagreements and disputes did not impede the quest for taller chimneys, and in 1889 the tallest one in Europe, at 140 meters, was built in Freiburg, Saxony. Once condensers were installed in chemical plants, mines and metallurgical foundries, for copper, silver, and lead, set new chimney height records. In 1908, the Boston and Montana Consolidated Copper and Silver Mining Company constructed a smokestack at Great Falls, Montana, that was 154.2 meters high. Of course, as an 1851 pamphlet from an Orleans industrialist Riley appreciated, from the summit of this immense pedestal, the enemy escapes, hovers and falls on his prey, spreading even further due to the height of its point of departure. By dispersing smoke out of the immediate vicinity of the plant, the tall chimneys had the merit of rendering their pollutions invisible. However, at the beginning of the 20th century, detrimental effects on the Tharont forest, located 15 to 20 kilometers from Freiburg, were already visible. It might seem a familiar, almost repetitive refrain. The Emscher and the Rhine in Germany, the Mersey and the Tyne in Lancashire, and other rivers became the dumping grounds for some of the period's most critical pollutions. Dumping wastes into rivers became a common disposal solution for the dominant pollutions of the 19th century, a situation in stark contrast with the attitudes of the previous century. Before the First World War, it was widely accepted that large rivers could dilute and evacuate pollutants. The same notion carried over to dangerous condensed gases that held no other industrial purpose. As Freycinet explained, when the body of water is sufficient, not only does the insalubrious element become, by dilution, a little less offensive, but it might also be rendered completely non-existent. In other words, it might be chemically destroyed by the special action of the environment. This is why, for Freycinet, the first care of a factory must be to look for an abundant stream. Table 6.1. Examples of tall chimneys in the 19th century, 1835–1913. But what to do with solid waste? In Switzerland, industrialists in Basel discharged solid waste from their synthetic dyeing process into the Rhine from an opening on a bridge. As was the case in numerous such locations, the dumping usually took place at night. In the middle of the century, the inhabitants of Chicago and Zurich felt the lakes that bordered their cities were large enough and deep enough to easily absorb harmful waste. This hope was disappointed at the beginning of the 20th century, when locals noted the proliferation of algae and bacteria that had destroyed the entire aquatic ecosystem. Although there is little quantitative documentation, and inasmuch as the process was largely invisible, discharges into the sea seem to have been widely practiced in the littoral industrial zones. From the 18th century, it was traditional for soap makers in Marseille to dispose of their waste on the coastline. The refuse became the foundation for the port's piers. This led prefects to regulate discharges into the Mediterranean, requiring that they be made further and further away from the shore. In 1830, the extent of waste dumped into the water was such that 100 meters from the coast, the sea's depth was only 4 meters. This hindered navigation, forcing authorities to order new, more removed areas for dumping. Successive port developments between 1844 and 1853, in which 150,000 cubic meters of soap waste was used as filling substrates, inspired a period of tout à la mer, everything into the sea, which received considerable support from doctors and engineers. In 1895, the emissary of Cortiou facilitated these discharges, despite the warnings of the biologist and oceanologist Antoine Fortuné-Marion. A dredging to 20 meters revealed the brutal devastation suffered by the ecosystem. The machine only dredges up pottery fragments, debris of all kinds, in a black mud. The earth from the soap residues forms a crust in places which is quite hard, and which the dredger scours, finding underneath a greenish slime with a sulfurous odor. These are the polysulfides that have accumulated and that have destroyed almost everything. These discharges and overflows served as archetypal outcomes of Marseille's chemical industry from 1880 onward. One typical example: as soon as it was installed at L'Estaque in 1883, the mining company of Rio Tinto chose to dispose of its soda waste by dumping it by the bargeful at sea. The French Mediterranean was not an exception. Metallurgical plants created jetties by dumping their slag into the sea. In Wales, Yorkshire, and Middlesbrough, for example, wagons would dump their dregs over cliff tops to the sea below. Piles of waste, 12 to 15 meters high, would creep out to sea for more than 200 meters. Rails were subsequently built on top of this new foundation, allowing for even more extended sea dumping grounds as they gradually grew longer. In 1870, at the mouth of the Tyne River in Lancashire, the Jarrige chemical factory chartered a large boat every day to dump the residues of its soda production 2 kilometers from the shore. In New York, the oil industry quietly poured its refuse into the sea that adorned its facilities. The water acquired an ink color and destroyed the flourishing oyster culture and fish resources. Such pollutions continued, and increased, up to World War I. Dilution had a spatial dimension to it, since the ability to physically remove pollutions away from inhabited areas has always been a sensible thing to do, if not the most efficient in the fight against pollution. According to Freycinet, the most toxic factories could operate safely 4 kilometers from the nearest town if the population could tolerate slight inconveniences. This process of spatial dilution played out on 3 different levels: urban, regional, and global. In the context of polyfunctional cities, in addition to the gradual eviction of dirty factories to their outskirts, as already noted, all studies show the spatial and social differentiation that took place as a result of pollution. Working-class neighborhoods dealt with the most nuisances, in essence because workers' housing grew up around factories. In America, however, a more insular approach was adopted. For example, in New York, which welcomed numerous petroleum refineries linked to chemical product plants at the end of the century, factories were gradually concentrated in districts like Newtown Creek and New Jersey, Standard Oil and Rockefeller among others, and on the East River estuary, through a combination of actions at municipal and judicial levels. Real estate and social and environmental factors also played a role. All of this resulted in a clear-cut social division. It fostered the creation of densely populated, working-class areas in industrial zones. Middle and upper-class populations migrated to places like Manhattan, which remained unmolested by heavy industry. Any improvements in the fight against urban pollution generally only benefited the middle class or those who were more comfortably off, and were usually even more detrimental to the working-class neighborhoods to which insalubrious factories were relocated. Such was the common pattern in early American struggles against air and water pollution. Authorities volunteered no urban or infrastructural planning solutions to pollution. Germany, however, revealed a glimpse of the emergence of pollution featuring in planning. Darmstadt and Mannheim, old regional capitals that industrialized over the course of the century away from the big basins of heavy industry, sought balance between healthy living and the demands of an industrial economy. After 1890, in an effort to promote public health, authorities adopted patterns of spatial differentiation between districts left to industrial contamination on the outskirts, and city centers devoted to residential life. This was achieved by encouraging and building railway networks to attract industry to its newly designated zones, as well as reinforcing control over steam engines within the city limits, and encouraging gas lighting and chemical companies to vacate the city center. The result was that, even in the absence of a truly coercive plan, authorities managed to reconfigure pollution's geography for the benefit of the more privileged classes. In 1870, in a similar move in Great Britain, the Metropolitan Board of Works in London ordered highly polluting manufacturers to move their premises beyond the boundaries of the metropolitan area. The result was to transfer nuisances to the suburban district of Blackheath. Pollution's spatial distribution can be observed on a smaller scale at the regional level. Thanks to the railways, it became increasingly easy to establish factories near mines, and to sacrifice isolated zones for heavy industry. This was the case, for example, in Middlesbrough, in England. A small coastal village in Yorkshire with a population of 200 people in 1830, its exceptional growth, it supported 100,000 inhabitants in 1900, was due exclusively to heavy industry, steel and metallurgy, that set up there. This safeguarded the regional, middle-class capital city of York, as well as the plurifunctional, industrial cities of Sheffield and Leeds. As Britain's new steel capital, nicknamed Ironopolis, Middlesbrough relied on its railway system and port. It became one of the most polluted steel cities in the world, but locals complained little about living conditions, in no small measure because most of them depended on the industry for their livelihoods. These new spatial configurations were made possible by railway networks connecting mining districts and factories. Coal was refined into coke on site at the mines, which kept this highly polluting and toxic process in isolation away from cities. The coal was then easily transported in its less polluting form into urban areas for consumption. Of course, urban pollution reductions often meant a rise in pollution levels elsewhere. Soda factories also took advantage of the railway and relocated farther away from city centers. As such, in France after 1870, they were found in outlying areas such as Douze, Lorraine, Thann, Alsace, the hinterlands of Marseille, and even the Cylindres commune in the Gard department. These zones, and others like them, fulfilled the principles for spatial isolation for industrialists. In 1854, the owner of the soda factory in Cylindres started out by compensating his neighbors for nuisances before eventually buying them out to create a protected and isolated buffer for himself, amounting to 144 hectares, about 355 acres. Here he built a train station that connected his property to the Sennens mines. In the 1870s, the Pescini Company took control of the business, and local life was thus defined by its patronage, its control of the local workforce, and its degradation of the environment. Lastly, pollution can be diluted on a global scale. In the latter half of the century, the United States began constructing manufacturing sites on wide expanses of virgin soils that had recently been vacated of native peoples. From the gold rush in California in 1848 to the explosion of big corporations in the 1900s, which amalgamated the banking, railway, mining, and electric sectors, Morgan, Rockefeller, Guggenheim, and others, a veritable mining of the New World led to an exponential rise in the production of precious metals, copper, and lead, with the polluting foundries that accompanied them. Out of sight and out of mind, this massive exploitation occurred far from the eyes and lungs of middle-class Americans, in places like Montana, Michigan, the mountains of California, and the deserts of Utah, Nevada, and Arizona. Around 1900, Australia, South Africa, and Canada, notably Ontario, each took their turn in developing metallurgical mines and foundries, due in large part to the reduced cost of merchant shipping. Pollutions experienced their nascent globalization. In some sense, colonialism at the end of the century, when looked at through a particular lens, could be said to have also played its part in the global spread of pollution. In India, for example, regulating pollution was first and foremost a response to racial segregation. In 1863, the air in Calcutta, connected to mining districts by rail, was just as polluted as in some European cities. the city issued an order to regulate industrial smoke in accordance with British metropolitan norms. In Calcutta, as in Delhi, policies to fight against pollution and for cleaner, healthier urban environments were inspired primarily to protect the districts where European settlers lived. Areas where indigenous people lived were described as dirty and polluted, proof of the backwardness of local populations. In the French Empire, regulating polluting industries, though there were far fewer than in India, also stemmed from segregation between colonists and indigenous populations. In Algiers, around 1850, the governor refused to allow the construction of a sulfuric acid factory because it was going to be too close to a military hospital for European soldiers. Throughout the 19th century, controlling pollution seemed like an impossible task. Despite undeniable achievements and the adoption of some laws after intense debates, controls, regulations, and solutions varied greatly between countries, time periods, the scale of the task at hand, and of course the particular industries in question. On a more general level, however, industrializing nation-states welcomed polluting industries. To them they constituted a symbol of wealth, prosperity, and their rise in importance in the world. More than the recourse to common law, which was largely ineffective, or to the often fragile, defective, and easily circumventable laws that sought to impose controls, pollutions diminished in some places when industries began to relocate to more suitable areas, far from the madding crowd. Rail and maritime transport revolutions permitted the conquest of new territories, which made it possible for industry to find more isolated locations. At the same time, the century of progress held fast to the notion that technical advances would solve pollution problems. Promoted by regulatory authorities, it was a nice idea, but it accelerated and exacerbated the rebound effects and further dispersal of pollution. The institutional legacy of the period between 1830 and 1914 remained prominent throughout the century that followed, even as the 20th century would have to reckon with an increase in contaminants, as well as new contaminants, as a result of wars, globalization, and continued industrial growth. 3. New and massive scales of pollution, the Toxic Age, 1914–1973. Contrary to what might be suggested by a quick comparison of the clearer skies over European cities in the 1970s and those drowned in the smog of the 1890s, the 20th century did not witness an overall reduction in pollution. Rather, the nature of pollutions changed, but their growth was always rapidly increasing and correlated with the demographic explosion, the increase in the consumption and production of manufactured goods, and the remodeling of physical environments by synthetic chemistry. While the population quadrupled during the 20th century, energy consumption grew ninefold and industrial production increased 40 times over. Despite cyclical and regional crises, economic growth accelerated in the industrialized world after the Great War, reaching its peak during the period known as the Glorious 30, 1945–1975, with growth rates of 3% to 4% in England and the United States, 5% in France and Eastern European countries, and even 8% in Japan. Between the Great Industrial War of 1914 and the oil shocks of the 1970s, a massive acceleration in environmental changes led to increased pollutions and their spatial redistribution. A new standard, endowed with all the virtues, stands out as a paragon of the desirable society. The gross domestic product, GDP, inspired visions of infinite growth and a society pacified by an abundance of material benefits on the horizon. Its algorithm for determining the economic health of a nation became a kind of lingua franca for rulers, business leaders, unions, and historians alike. Developed in the United States to solve the serious crisis of the 1930s, the language and concept of GDP spread after 1945 to Europe and the world. Measuring the production of goods and services within a country during a given period, however, this indicates a neglected heritage and nature. As a result, environmental damage and the depletion of natural resources was rendered economically invisible or irrelevant. Worse, far from supporting the fight against pollutions, the obsession with the rise in GDP tended to exacerbate environmental problems. Pollutions were the byproducts of manufacturing goods, which weighed positively on the GDP spreadsheet. Services provided to attend to accidents or medical treatment of environmental diseases were regarded similarly. In this perpetual race for more, humanity entered surreptitiously into a new, toxic age, par excellence. New chemical substances, in particular, caused expansive wastes that spread through air, soil, and water. They were often dangerous and sometimes resisted biodegradation in natural environments or organisms. Still, industrialists mostly disposed of their untreated waste in pits, dumps, rivers, or the sea. Such contaminated spots were still relatively isolated and modest in number in the early 20th century. Their number and size expanded rapidly after 1945. In 1980, estimates suggested that the United States alone was home to 50,000 hazardous waste dumps. Moreover, these substances did not only pollute at the time of their production, rather, they became defined by their persistence through every aspect of their cycle: production, consumption, and disposal into the ultimate outlet, the oceans. Poisons that do not die. This created a kind of universal poisoning, according to the journalist Fabrice Nicolino, a new age of toxicity, according to historian William Cronon, an age of poisons, according to biologist Rachel Carson. Like an uncontrollable oil spill, the development of pollutions took on a metastatic character that attacked societies in myriad ways. They aggravated the social, economic, and environmental imbalances between regions preserved for healthy living for those who could afford it and those corridors sacrificed to industrial production and the reception of its waste. At the end of the 20th century, human activity extracted some 70 billion metric tons of materials annually to feed its rapacious appetite, but only 15% of the population, living mainly in the industrialized countries of the North, consumed half the mineral and fossil resources. Despite this inequality with regard to environmental dangers and hazards, which remain an inequality linked to economic development, pollutions were unmistakably a globalized problem. Although each particular industry tended to pollute less, thanks to the adoption of new, more efficient processes and because producers found means to reduce the quantity of their waste, demand and the scale of production meant that global pollutions, in aggregate, continued to increase. In fact, four phenomena counteracted the effects of technical improvement. First, industrialization standardization throughout the world mechanically increased the overall volume of toxic discharges. Second, the exhaustion of mining resources meant that the industry was forced to exploit veins that were less and less pure, which in turn demanded more aggressive extraction processes. Third, mass consumption and population growth shifted pollution downstream to the act of consumption itself. Finally, globalization and global economic integration accentuated the transformation of nature into a commodity. Consumption of, or the perceived need for, new goods helped to soften opposition to pollutions, often rendering them less a feature of public discourse. Several processes played a decisive role in the advent of this new toxic age. First, two world wars and the Cold War promoted a certain disinhibition of, or prioritization away from, the damage wrought by progress and the ravages of industrial expansion. Chapter 7. The establishment of a fossil fuel energy regime and the ascendancy of oil also accentuated global pollutions. Chapter 8. The lifestyles and birth of the consumer society, which depended on industrial growth for its goods, multiplied and disseminated pollutants. Chapter 9. Finally, the persistent weakness of legal regulations and intervention methods, which failed to slow the phenomenon, made it possible to understand the emergence of many new hazards in the 1970s. Chapter 10. 7. Industrial wars and pollution. If wars before 1914, starting with revolutionary and imperial conflicts, the Crimean War, 1853-1856, and the Civil War in the United States, 1861-1865, were terribly destructive with a variety of environmental effects, none reached the scale or intensity of warfare in the 20th century. A new era of total war brought with it new methods of widespread contamination. Napalm and the chemical defoliants used in Vietnam in the 1960s and 1970s were emblematic of the ecological ravages and pollution caused by 20th century conflicts. Gas warfare was launched during the First World War and, with the help of aeronautics, Spanish and French colonial powers dropped the first incendiary bombs on Moroccan Berber tribes during the Rif War, 1921–1927. Napalm, a gasoline-based substance initially used for flamethrowers, was developed at Harvard University in 1942, before being used extensively in 1945 against Japanese cities, during the Greek Civil War, 1944–1949, then in the Korean War, 1951–1953, and in Vietnam. In addition to the innumerable human casualties, fauna, flora, soil, and water were permanently contaminated by its liberal use. The massive dropping of the famous herbicide nicknamed Agent Orange by the American Air Force during the Vietnam War to destroy the forests in which the Viet Cong soldiers were hidden, is considered one of the most important ecocides in history. It also reveals the close links between the civilian and military uses of this type of chemical. Total war, as a concept and a practice, began in 1914. Rather than just mobilizing soldiers to a battlefront, the entire population and economy of the belligerent countries were recruited into complete subservience to the conflict. War also became more and more industrial, enlisting chemical resources, and commandeering scientific and industrial innovation on an unprecedented scale to inflict maximum destruction. As La Nature, a French magazine aimed at the popularization of science, observed in January 1916. If there is an industry that is equally valuable in both war and peace, it is the tars and benzols industry. In times of peace, it allows our elegant women to dress in bright colors and surround themselves with delicate perfumes. In wartime, it supplies our cars with a valuable substitute for exotic oils, and above all it serves as a basis for the manufacture of the most powerful explosives, melanite, trotol, amatol, etc. Figure 7.1. Bombardment of Agent Orange from American planes during Operation Ranch Hand, 1962 to 1971. Too often we forget how wars are major sources of pollution. The concept of ecocide comes from the Vietnam War because of the massive bombardment of Agent Orange by the US Army over the forests where communist fighters hid. More than 3 million hectares, about 7.4 million acres, were contaminated by this Monsanto-manufactured herbicide. Scarcely visible for a long time and considered secondary to the countless human casualties, an estimated 180 million deaths during the wars of the 20th century, environmental damage and destruction has recently emerged as an important research interest. The relationship between military action and environmental change is the subject of a growing number of works. Indeed, war reconstitutes the interactions of, and between, nature and society, engages the world in the service of action, and intervenes in the redefinition of representations of nature, as in the construction of knowledge and ecological mobilizations. We can ascertain that more than the pollution itself, wars were marked by the destruction and radical transformation of landscapes. The most spectacular damage to the natural environment was linked in the first place to policies of terror and scorched earth. The destruction of the Yellow River's dikes by Chinese nationalists in 1938, a desperate action to halt the Japanese advance, undoubtedly had a much greater impact on ecosystems than pollution. Widespread deforestation of vast areas is arguably the most important environmental impact of 20th century warfare. Similarly, upstream from the war process, military-industrial complexes undertook the construction of massive infrastructures and developed scientific programs that shaped environments. But as a matrix of new techno-scientific trajectories, as a space in which exceptional mobilization and unprecedented lack of restraint dictated social activities, wars marked the sea change of scale in pollution's history during the 20th century. In war, environmental protection and public health were relegated to the background as the theater of combat, and its imperatives took center stage. Conflicts were the inspiration for technological developments that would otherwise have been inconceivable, from destructive chemistry to nuclear energy, to say nothing of the considerable acceleration in the design of new materials and logistics. A whole range of new, highly polluting products emerged. Wartime mobilizations and the end of restraint. In the age of extremes, military interventions transformed landscapes and the environment. In certain circumstances, it could be said that military actions led to the creation of sanctuaries conducive to the special protection of ecosystems, away from industrial influence. Indeed, war could reduce local pressures exerted on certain natural environments. This was the paradoxical case for the 250-kilometer-long demilitarized zone created in 1953 between North and South Korea, which has seen the development of a rich biodiversity. To a lesser extent, the more than 3,000-kilometer zone of the former Iron Curtain which divided East and West Germany manifested a similar condition. In times of war, restrictions and rationing policies reduced the footprint of some particularly polluting activities. Some countries experienced shortages of basic consumer goods. For example, Italy and France suffered a decrease of 40% and 50%, respectively, in their GDP between 1938 and 1945. In France during these years, fishing for salmon in the Seine became possible again for the first time since they had disappeared in the 1880s resulting from pollution of the river. The same phenomenon was noted in Finland. Shortages sometimes forced a return to older production techniques that required less energy consumption and generated less pollution. Energy conservation was the rationale behind the introduction of daylight savings, adopted in 1916 by Germany and the Austro-Hungarian Empire, followed by France, Great Britain, and the United States. After entering the war in April 1917, the United States tried, unsuccessfully, to limit the dense fumes escaping from the factories, which appeared to be wasteful and a sign of anti-patriotic inefficiency. During the Second World War, the American government encouraged the use of bicycles as a patriotic duty, while Britain promoted recycling. In other cases, rationing forced agriculture to dispense with chemical fertilizers or to develop low-energy farming techniques. In Japan, for example, during World War II, the ammonia shortage, the use of which was monopolized by the industrial sector in order to prosecute the war, pushed farmers to practice composting in order to enrich their soils with organic matter. Though such examples of constrained wartime management of resource shortages exist and abound, they should not obscure how much, on a more macroeconomic level, the belligerent nations engaged in a total mobilization of their productive apparatus. On average, nations' GDPs grew by almost 35% during the Second World War, and in the United States by 214% between 1938 and 1944. During the wars, the decline in pollution, if and where it occurred, was still limited and circumscribed, usually followed by a phase of intense economic and concomitant pollution growth after the end of hostilities. Although the situations varied greatly according to landscape, the economic structures of the countries, and the location of the battlegrounds. War favored a recomposition of markets, nourished the insatiable appetite of the great powers for natural resources, wood, sugar, oil, or uranium, and encouraged their intense exploitation. Wartime priorities also redefined ways of thinking about and exploiting natural environments. War allowed for unprecedented logics of predation, lifting controls and inhibitions, silencing opponents, and imposing a modernizing framework favorable to the unprecedented growth of polluting emissions. At the heart of this industrial mobilization was the production of shells, machine guns, airplanes, tanks, and trucks, but major projects also featured. The manufacture of large-scale equipment as well as transport and energy infrastructures were critical to the war effort. For example, after 1941, the U.S. Army ordered 500 million shoes, and the auto industry was required to produce military vehicles. Until 1945, American industry alone made two-thirds of Allied military equipment, 2 million trucks, 300,000 aircraft, 193,000 pieces of artillery, 86,000 tanks. Such production intensification was inevitably accompanied by numerous environmental impacts. Its continuation required a relaxation of stiff environmental regulations and some tolerance of legislative infringements. War and production pressures dictated that polluting discharges were poured directly into watercourses or hastily dumped. In this context of industrial reconversion to meet military demand, ecological considerations and worries were subsumed by the urgencies of the time. Administrative and legal controls on pollution were eased and protest movements lost considerable influence. The Great War was the first highly polluting energy and chemical conflict. It propelled oil production from 40 million metric tons in 1910 to 100 million metric tons in 1921, while Royal Dutch Shell's dividends multiplied fourfold between 1914 and 1919. Mechanized war made oil such an essential requirement that in December 1917 the head of the French government, Georges Clemenceau, urged U.S. President Woodrow Wilson to send him 100,000 metric tons of oil quickly. If the Allies do not wish to lose the war, then, at the moment of the Great German Offensive, they must not let France lack the petrol which is as vital as blood in the coming battles. Demand for oil forced the major powers to increase their influence over the resources of the Middle East. During the conflict, the patriotic Sacred Union in France and the defense of the nation imposed in most belligerent countries a consensus around the needs of production and fostered an intense techno-industrial modernization. The conflict convinced many participants, such as the French socialist Albert Thomas, union organizer of arms production workers and the first director of the International Labour Office after the war, that the growth of production and the use of new technical processes were necessary. In 1917–1918, the United States broke records for the quantities of coal burned. In so doing, it reversed previous efforts to reduce industrial fumes. Air quality declined dramatically in many cities, including Pittsburgh, St. Louis, Cincinnati, and Chicago. The press reported that smoke clouds had never been so thick. In New York, an anthracite coal shortage forced manufacturers to use dirtier, lower-quality fuels. In addition, war and its patriotic propaganda silenced protest movements and anti-smoke activists. For example, private sector engineers came to dominate and take control of the International Association for the Prevention of Smoke. In Germany, too, the necessities of war production pushed the administration to put a moratorium on legislation that limited industrial fumes. In 1915, the Prussian Minister of War invited local authorities to suspend environmental quality regulations. The suspension of certain environmental regulations seemed a universal rule that applied as much to the Second World War as the First. In the United States, the anti-pollution regulations adopted in St. Louis and Pittsburgh before the American entry into the war were quickly suspended after 1941. They were not reinstated until the post-war period. In Nazi Germany, the economy was geared to victory on September 3, 1939 and, from 1943, a year marked by a succession of defeats in Stalingrad and in North Africa, the whole nation and its human and ecological resources were mobilized. Admittedly, the Nazi administration was torn over the question of air pollution and its control. The subject did not directly interest Hitler, but it did breed debate, nevertheless. Some lawyers wanted to promote a policy of reducing fumes in the name of the good of the nation and the Germanic race, but authorities finally decided and ordered the limitation of the legal constraints that governed polluting emissions. However, complaints against nuisances and pollution never completely disappeared during the war. After 1945, the rivalry between East and West further polarized tensions, and the specter of the Cold War significantly slowed down any concerted return to the regulation of pollutions. If it featured at all in the great international conventions of the post-war period, pollution was only ever at the margins, until the 1972 United Nations Conference on Humans and the Environment, held in Stockholm. Israel's case marked another rationale for alleviating environmental regulations. Given the tensions and context surrounding its creation in 1948 and the many conflicts with its neighbors, in the first place, the Six-Day War in 1967 or the Yom Kippur War in 1973, the Israel Defense Forces acquired a special status within the State of Israel, and an immunity from adhering to the country's environmental regulations. As with conflicts, war preparedness and the militarization of societies in the 1930s, or during the Cold War, legitimized major projects, removed the political constraints that could curb them, and set aside prudence for the benefit of a total mobilization of industrial capacity and resource appropriation. Armed conflict notwithstanding, military maintenance added to overall pollution levels, accounting for 6% to 10% of air pollution, for example, since 1945. Daily military operations, such as research, development, testing, and storage, as well as training, maintenance, or deployment of troops and arsenals, created vast amounts of waste and polluting emissions. For example, the US military alone generated 750,000 metric tons of toxic waste per year, more than the 5 largest chemical companies in the country combined. That waste needed to be processed or stored in the 8,500 military enclaves in the United States and installations in allied countries, such as Canada, Germany, Great Britain, Italy, Panama, the Philippines, South Korea, and Turkey. The expansion of the number and influence of military bases stemmed from the increased warlike tensions of the 20th century, which the Cold War only exacerbated. At the end of the 1980s, military encampments and facilities covered 1% of the surface of the globe. Many housed some of the most polluted places on Earth. At that time, the United States had 375 major and 3,000 smaller military bases scattered around the world. These bases were responsible for environmental transformations that gave rise to much opposition, particularly in Great Britain and France. In France, the fight against the extension of the Larzac base in the 1970s also precipitated the emergence of an environmental consciousness that goes beyond purely military concerns. The American military presence around the world, which provided the basis for the post-1945 international order, created multiple localized pollution incidents. Generally, military secrecy ensured that such infractions were ignored, excused, or covered up. In Panama, for example, chemical weapons experiments, conducted over several decades at large U.S. military installations, provoked many nuisances and local complaints. After the bombing of Pearl Harbor in 1941, the United States Armed Forces purchased most of the island of VX, near Puerto Rico, as a strategic naval base. After the war, the military turned the island into a munitions depot and base for testing and maneuvers. For 60 years, the small island has been under colonial control, with a veritable deluge of bombs causing rates of cancer or cirrhosis well above the average observable in the Caribbean. In Europe itself, the presence of U.S. troops and North Atlantic Treaty Organization, NATO, forces to stem the threat of communism weighed heavily on some ecosystems. In Sardinia, for example, the Italian government authorized in 1956 the establishment of shooting ranges and various military installations which, for several decades, heavily contaminated the island. Energy consumption related to maintaining the military presence of the great powers has increased steadily along with the relative gigantism of military equipment. After the Second World War, military technologies became ever more energy hungry. A U.S. Army Abrams tank consumed 400 liters of fuel per 100 kilometers, a B-52 bomber, commissioned in the 1950s, burned 12,000 liters of kerosene per hour, an F-15 used 7,000 liters, more than a car over several years. Between 1945 and 1975, CO2 emissions linked to military training and the production of weapons in the United States alone represented around 10% of all emissions. On the other side of the Iron Curtain, the desperate quest for strategic mineral resources for the war effort and the rapid construction of a vast chemical and metallurgical industry to meet military demands transformed entire regions of the USSR into militarized camps and industrial deserts. After the Second World War, during which the Ural regions, rich in mineral resources, were mobilized to feed the war effort, mining and industrial cities flourished. This caused massive increases in pollution, especially in the north of the Soviet Union. In the same regions, mushroom towns were born around mines and military bases, typified by gulags. Vorkuta, located in the heart of a vast mining basin beyond the Arctic Circle, constituted an archetypal example. Connected to the rest of the country by railway from 1941, and hosting a major military base for bombers during the Cold War, the Vorkuta region offers a paradigmatic example of the pollution of water and air by heavy metals. The same phenomena were observed in the cities built in Siberia to exploit the mineral resources that fed military needs. Though the scale may have varied, other countries' practices followed the same pattern. In Japan, for example, during the interwar period, air and water pollution worsened as the war effort intensified. Local authorities reported numerous contaminations by the mining and quarrying industries and chemical plants. The Fisheries Administration within the Japanese Ministry of Agriculture identified more than 1,000 cases of water pollution, and most of the country's major cities were victims of toxic emissions from industry. A matrix for new polluting trajectories. By mobilizing human and material resources, removing restraints and marginalizing concerns about pollution, war set the stage for the great acceleration of environmental changes in the latter half of the 20th century. The new armed conflicts were both total wars and world wars, prosecuted on all continents. In effect, the two world wars reshaped categories and representations of space and time, and undermined previous balances of power, particularly colonial, while impelling new scientific and industrial dynamics on a spectacular scale. By removing all inhibitions, the world wars initiated the global triumph of brutal and destructive technologies. They also prepared the ground for new pollutions by shaping the technical and legal framework of the mass consumer society, stimulating a military-industrial complex under state control, and boosting motorization, aeronautics, and new, especially polluting sectors such as pesticides and aluminum. Wars in the 20th century ushered in the establishment of big science, which made a new world of research increasingly dependent on partnerships between the state, scientists, and industry, all in the service of far-reaching projects that had profound and lasting impacts on the environment. This heavy science stemmed from developments during the First World War and interwar period, which set decisive milestones. In 1916, the National Research Council was created in the United States to place academic research at the service of military objectives. But especially after 1940, science settled at the heart of political issues around major research programs, particularly nuclear, and scientists acquired a central position of power. While in 1939 fundamental research was still dominated by small teams with limited budgets, scientists found themselves after 1945 at the heart of military programs whose polluting capacity had increased tenfold by the alliances it established with industry. After chemistry, physical science, particularly nuclear and high-energy physics, maintained ever closer relations with military research. By the Cold War, the great powers were investing massively to improve their knowledge of the physical world and matter and to develop new, more destructive weapons. Satellite imagery, oceanography, seismology, meteorology, and climatology were recruited for military control of the planet. Some universities, such as the Massachusetts Institute of Technology, MIT, in the United States, were at the heart of the nascent, military-industrial complex. Its director stated at the end of World War II that MIT's military value was equivalent to that of a squadron or an army. Although CERN's European project was more independent of the military because of the unique diplomatic issues it presented, Most major post-war research organizations, such as the French Atomic Energy Commission, CEA, were closely beholden to or derived from military interests. Without the war, motorization across European and North American societies, like the development of aeronautics and new chemical substances, would have been much slower to develop, and some new and particularly toxic products would probably never have emerged or spread with such ease. If the rise of the automotive industry received a boost during the Great War, Renault and Citroën in France, for example, aeronautics was the key sector that greatly benefited from 20th century conflicts. While 5,000 aircraft were built worldwide in 1914, their number surpassed 200,000 in 1918. The French army had fewer than 350 aircraft in August 1914, but by 1918 it had built 41,500, including nearly 10,000 for the Allies. The increase was not only quantitative. In 1918, planes flew twice as fast and 5 times higher than before the war, and their energy consumption increased. In 1918, the Royal Air Force was created in Britain, and in the 1920s aerial warfare was studied and theorized. New aerial technology meant that from now on civilian areas would be part of the destruction of war. Aerial bombardment became an essential element of total war. But the advent and ascent of aeronautics helps in understanding the fundamental impetus of the Second World War in a very energy-intensive mode of transport that became commonplace for civilians in the second half of the 20th century. In 1945, the United States alone produced 20 million metric tons of aviation fuel, compared to 2 million metric tons for Great Britain. The age of jet engines also emerged during the Second World War. Simple experimental prototypes in the 1930s, they became operational during the conflict. They were subsequently employed during the Korean War, before being adapted for civilian use. War as a matrix of new production models also affected a wide range of technologies, of which aluminum and chemical substances were probably the most representative. At the beginning of the century, aluminum was still a precious metal produced in small quantities. However, it became a fundamental metal in aviation, ideal for its lightness and physical characteristics. In the 1930s, Fascist Italy and Nazi Germany increased their demands on the aluminum industry. The authoritarian regimes also repressed protests, such as those from the villages of Mori, in northern Italy along the Adige River, affected by fluorite pollution from aluminum smelters. The Second World War tripled global production capacity. To meet the war effort and the needs of the military, American aluminum production rose from 130,000 metric tons in 1939 to 1 million metric tons in 1945, 3/4 of world production. Germany produced 200,000 metric tons in 1944. In order to profit from the vast amount of industrial equipment used during the war, it became necessary to find post-war civilian markets for aluminum, all the while without restricting its continuing military uses. The metal was touted as a modern material with almost miraculous properties. It was promoted for the manufacture of cooking utensils, packaging, the famous soda cans, or storefronts. Aluminum became one of the veritable symbols of mass consumption after the war. In 1950, 1.5 million metric tons were produced globally, a figure inconceivable without the decisive impetus of the Second World War. The two world wars also introduced a large number of new chemical substances, often already known but for which opportunities and markets had been lacking. Their proliferation contributed to the universal poisoning by chemistry. One example, during World War I, the Haber-Bosch, 1909, ammonia synthesis process for fixing nitrogen in air was improved because nitrate was critical in the production of explosives. Responding to the freezing of German imports and growing military needs, the American chemical industry expanded on an unprecedented scale. The war profoundly transformed American chemistry, notably under the influence of the American government's Chemical Warfare Service. In November 1917, Charles E. Roth, Secretary of the American Chemistry Society, asserted that the country had accomplished in only 2 years what had taken Germany nearly 40 years. The Second World War presented an industrial echo of the first on an even larger scale. While the large American companies in the chemical sector were still confined to local markets before 1940, they dominated international markets after 1945. In a few decades, tens of thousands of substances were put on the market and infiltrated into and entrenched themselves in people's daily lives. Prior evaluation of their hazards and real administrative control over their production or distribution were largely dispensed with. Functional chemical oversight in the United States did not emerge until the Toxic Substances Control Act was passed in 1976. By that time, 62,000 chemical products were in circulation. Much of the proliferation of chemical pollutants was due to the need to recycle war products. After the hostilities of the First World War, the chemical gases used in the fighting were converted for civilian use, primarily as sanitizing materials. Chlorinated gases were reused for disinfection in medicine and in public places. Arsenic gases controlled pests, especially weevils. Despite intense debates, polemics, and resistance, the insecticides from combat gases spread widely in American agriculture in the 1920s and 1930s, a use supported by para-institutional propaganda and the prestige of the powerful chemical industry that sought to optimize the equipment it had developed for wartime production. The famous case of dichlorodiphenyltrichloroethane, DDT, offers another remarkable example. This substance, synthesized by an Austrian chemist in the 1870s, had remained a simple laboratory feat before the Swiss Paul Hermann Müller, 1899–1965, discovered in 1939 its utility as an insecticide. First against moths and then against Colorado potato beetles. He received the Nobel Prize for Medicine in 1948 for this discovery. In May 1943, after the Food and Drug Administration studies attested to its safety, DDT was manufactured on a large scale to supply the U.S. military and eliminate disease-bearing insects from theaters of operations, particularly following the typhus epidemic in Naples in October 1943. Nearly 1.3 million civilians were treated with neocide powder, a substance containing DDT. In 1944, 14 U.S. companies produced DDT in large quantities. It was used extensively in the Pacific War to fight mosquitoes, often portrayed in advertising copy as the treacherous Japanese, 1943–1945. DDT was perceived and sold as a miracle product that had contributed to the Allied victory and the protection of soldiers. After 1945, manufacturers had to create numerous new markets for its overproduction. Post-war agricultural pollution was largely the result of the disposal of stocks inherited from the war. Historian Edmund Russell has shown the incessant intersections and linkages between certain forms of wars between humans and wars against nature through chemistry, particularly in the form of pest eradication programs. War deeply shaped systems of norms governing the relationship with the environment, couched in a rhetoric of increased violence, which in turn further radicalized warlike action. Through the 20th century, the brutalization of human societies and nature went hand in hand. The exceptional, justified in wartime, became normalized in times of peace. It is therefore hardly possible to understand the reinforcement of pollution's entrenchment after 1945 without reflecting on these large-scale military clashes. Under the bombs, the gases. Assessing the relationship between war and pollution in the 20th century also involves diving into the heart of the battle, so as to scrutinize its impacts on air, water, and soil. Depictions of nature were profoundly redefined by experiences derived from war. This was especially the case during the unprecedented violence of the Great War. Peaceful country landscapes were evoked as a means of symbolizing hope and providing a serene atmosphere to calm anxiety and fear. In contrast, the battle landscapes of desolation were nevertheless mainly represented in iconography and testimonies. Soldiers, educated or of more modest origin, painted the ecological ravages. Visions of death and of silenced spring, a long-standing symbol of rebirth and profusion, scarred war's witnesses. Visions of grass without grass, buds without buds, and flowers without flowers. Season of poisoned bulbs. Seasons of total war. Seasons of lovers without love. Lunar landscapes. Visions of dead stars. Seasons of unnecessary and bloody offensives. Seasons of sterile and desperate mutinies. Seasons of strange sources. Seasons of flooded tombs. Seasons of gases and poisons. Nature hungry and carnivorous. Rusty locks. Trench warfare, along a front line stretching from its western extreme on the North Sea to the Swiss border, left behind the detritus of war. Polemological, landscapes strewn with sterile soils, riddled with metals and unexploded shells buried underground, unsuitable for agriculture. Of the 3.3 million hectares, about 8.2 million acres, of agricultural land affected by the fighting in France, studied with precision because they entered into the post-war calculation of war reparations, tens of thousands could not be cultivated after the war. Reforestation projects in the 1930s served as rehabilitation of spent lands. The artillery's impact on the land corresponded to 40,000 years of natural erosion. The ravages were also ecological. Red zones were massively polluted by substances of all kinds. The risk of contamination of groundwater from the decomposition of corpses was a problem that was quickly realized. The French Academy of Sciences identified the issue as early as December 1915. During the long siege of Verdun in 1916, experiments were conducted with chlorine to disinfect the water and counteract the risks of epidemics. The term, Verdunization, stuck. But the war also posed longer-term problems of persistent pollution. Atmospheric fallout from weapons fired and explosions lead to high concentrations of pollutants in some areas. Very high levels of heavy metals such as lead, from shells, or mercury, used as primers, durably contaminated local areas where they were left in abundance. For example, surrounding the so-called Placer Gaz, located in a forest near Verdun, the French army dealt with 200,000 chemical shells in the 1920s. Surveys and measurements carried out a century later in 2014 indicated intense and lingering quantities of arsenic, 17% of the weight of the soil, but also of cadmium, lead, and mercury. If this site is still closed to the public by prefectural decree because of pollution, all the areas near the front line were affected by such residual pollution related to the First World War. In his famous novel Under Fire, 1916, Henry Barbusse described the world of trenches as a polar desert whose horizons fume, with barren fields, invoking in his story recycled imagery of previous industrial pollutions. He compared the dark, nauseating atmosphere of the trenches to the smoke and smell of factories, as if the industrial war had brought to an end the environmental costs of the industrialization of the previous century. Gigantic plumes of faint fire mingle with huge tassels of steam, tufts that throw out straight filaments, smoky feathers that expand as they fall, quite white or greenish-gray, black or copper with gleams of gold, or as if blotched with ink. The asphyxiating gases, mentioned by Barbusse as a chemical threat were, however, in 1915 only a whisper of the great danger they would become with rapidly increased use. The Great Chemical War began in earnest on April 22, 1915, when a wave of chlorine from German lines broke into an Ypres trench on the Belgian front. 15,000 French soldiers were quickly incapacitated, 5,000 of them died. The significance of the new threat incited the Allies to redirect their chemical industry into a producer of offensive weaponry. At the peak of production in 1918, English factories produced 210 metric tons of chlorine a week for the war effort. But chlorine was quickly supplanted by phosgene, which had already caused 6,000 deaths on the Russian front on May 31, 1915. Research into toxic gas innovation and production, and, ideally, methods of firing them as projectiles, escalated. In addition to asphyxiating gases, including phosgene, diphosgene, and chlorofacrin, the new research yielded an arsenal of incapacitating gases, based on bromide or cyanide, and subsequently sternutatres, based on arsenic, or compounds of chlorine and arsenic. Research in the Allied camp was concentrated in Great Britain, under the direction of the great chemist William Pope, who promoted the industrialization of laboratory tests on triphenylarsine dichloride, TD, and diphenylarsine chloride, and even chlorofacrin. In Germany, chemical research was conducted under the direction of Fritz Haber. The introduction of Ypres shells, named after Ypres, which again served as practical laboratory for the military use of chemical gases. These were the now famous mustard gas, or dichlorinated ethyl sulfide, on July 12, 1917, marks a much more important milestone. The new poison attacked any part of the body, causing extensive burns. Insidious and persistent, mustard gas required that soldiers keep mask and waterproof protective clothing readily at hand. As soon as it appeared, mustard gas became the main combat gas, quickly adopted by Germany and then by the other belligerents. Responsible for most of the casualties from gas, it was however produced in industrial quantities only from the summer of 1918. After the end of hostilities, chemical warfare raised many concerns. In Europe, pacifists and nationalists shared the same fear with respect to combat gases. Speeches and writings from the interwar period warned against the risk of contamination by new military technical means. These debates shared many points in common with those surrounding industrial pollution. Physicist Paul Langevin, vice president of the League of Human Rights, claimed that 100 metric tons of gas were enough to cover Paris with a toxic layer 20 meters deep. These strong concerns contributed to the imposition of regulations, such as the Washington Treaty, 1922, which was supposed to prohibit the use of asphyxiating gases but was never put into effect, and the Geneva Protocol, 1925, on the prohibition of chemical and bacteriological weapons. In 1931, an International Commission for the Legal Protection of Civilians Against the Dangers of Air Warfare was also created. The march to war during the 1930s nullified these tentative attempts at regulation. The bombing of Guernica in Spain on April 26, 1937, by the Nazis and the Italian fascists, which is one of the first raids in the history of military aviation on civilians and a defenseless city, signaled the destructive intentions of the Second World War that followed. In the Pacific, Japan and the Allies became ensconced in a terribly destructive conflict, while imperial powers reinforced colonial control over these territories. The ecological damage produced by the war on these often fragile island territories was particularly important. Direct pollution linked to the fighting is unfortunately poorly understood. From January to June 1942, for example, during the Battle of the Atlantic, German submarines sank dozens of tankers, which dumped their cargoes of crude oil into the ocean, but it is difficult to assess their range. American bombing of German cities was equally damaging, inflicting real environmental punishment and turning swaths of Germany into a desert. For example, on July 27, 1943, the Allies dumped nearly 10,000 metric tons of phosphorus bombs on Hamburg, while the bombing of Dresden on February 13, 1945, killed 25,000 civilians and totally destroyed the city. In all, 2 million metric tons of bombs were dropped on the Third Reich in May 1945 alone. The Asian wars after 1945, starting with that of Korea, 1950-1953, extended the same destructive logic. The British introduced the military use of defoliants against the Malay Communists, 1948-1957. Since the Vietnam War, which spanned 20 years, 1955-1975, historians have begun to speak of ecocide. So devastated were landscapes that they became unfit for agriculture because of the extent of pollution. During this conflict, the destruction of the physical environment became a primary military objective. The American infantry advanced with powerful bulldozers, Rohm plows, that cleared forests and crops. A new 6-ton, metric, bomb, the specially developed Daisy Cutter, was designed to instantly create landing zones in the middle of the forest for helicopters. Noting the failure of incendiary bombs and napalm to destroy the dense tropical Vietnamese rainforest, the US military finally pulverized the landscape with defoliants from the herbicide industry. More than 70 million liters of herbicides were dumped between 1961 and 1971, including 44 million metric tons of Agent Orange, the notorious herbicide from Monsanto. Some 2.6 million hectares, about 6.4 million acres, were sprayed with this product, which subsequently seeped into soils and water, permanently contaminating vegetation and living creatures. In total, half of Vietnam's mangroves and 40% of the country's arable land were contaminated. The country lost 23% of its forest area. The effects on the populations remain still 40 years after the end of the conflict. More generally, after the fighting, the impact of military pollutions was immense. Much of this history remains unexamined. Many sites were contaminated for generations, banned from the public, secretly monitored by the military authorities. In other cases, egregious post-war spills, especially at sea, at sites that were forgotten or no longer monitored, produced disastrous ecological consequences many decades later. In France, thousands of metric tons of munitions have been immersed in Lake Avralet, Maine-et-Loire, or buried in the Jardel Chasm, Doubs. In Belgium, part of the stockpile lies off Zeebrugge. Contaminated black zones became even more ominous after World War II, and the Cold War created new cemeteries of weapons, ammunition, and toxic products. Indeed, after World War II, nuclear waste was added to more conventional weapons stockpiles. Nuclear contaminations. The atomic bomb serves as the singular and most spectacular symbol of 20th century warfare. Its enduring legacy, nuclear contamination, may rival the bomb's destructive significance. While most of the theoretical knowledge concerning protons, uranium fission, and the resulting chain reaction were available before 1939, wartime exigencies galvanized the switch to practical applications, and primarily military operations. In 1939, US President Franklin Roosevelt ordered applied research on this new technology, and in 1942 the Manhattan Project was launched to move to the industrial stage of production. This led, in spring 1945, to the development of 2 bombs with plutonium and another with uranium, 3 bombs that were detonated, first in the desert of New Mexico, July 16, and subsequently over the Japanese cities of Hiroshima, August 6, and Nagasaki, August 9. The two assaults on Japan remain the only nuclear bombings as an act of direct aggression. The atomic bombs killed roughly 200,000 people at once. Measuring the impact of the radioactive fallout that persisted long after the war is a difficult proposition. Since 1945, questions surrounding health and environmental impacts from nuclear weapons have been constantly debated. After the destruction of Hiroshima and Nagasaki in 1945, scientists found that deep-sea fish had survived. Similarly, an October 1947 survey of Hiroshima's fauna found that vertebrates and insects had returned to the city, while local flora also showed a strong resilience and was robustly reclaiming the ruins of the city itself. But nuclear pollution was not limited to this solitary, explosive event. The race for arms and power resulted in a rapid proliferation of nuclear weapons. Increased weapons testing and its resulting nuclear waste caused much more damage than the bombs of 1945. In addition to the Cold War's two superpowers, by 1975 the United Kingdom, France, and China had managed to build the atomic bomb. These five nuclear powers were the permanent members of the UN Security Council. Their atmospheric nuclear tests carried out in 1971 released energy equivalent to the explosion of more than 500 megatons of TNT. In total, more than 2,000 explosions have been officially recognized by the major powers, more than half of them by the United States. Although the sites chosen for these trials were located in isolated or even desert areas, the extent of contamination is persistent. Between 1946 and 1958, the U.S. military conducted 33 atmospheric nuclear tests on Bikini Atoll, previously emptied of its inhabitants. In March 1954, the detonation of a prototype of the H-bomb, or thermonuclear bomb, weighing 11 metric tons produced a crater 2 kilometers in diameter and permanently irradiated an area of more than 100 kilometers in diameter. In the 1970s, the contamination of fauna and flora was such that the local population was still prohibited from returning to the island. On the other side of the Iron Curtain, the USSR produced 45,000 nuclear warheads and officially conducted 715 nuclear tests between 1949 and 1991. But if we add accidents, the sabotage of submarines or the civilian use of military nuclear warheads to open canals, the egregious dumping of waste in the Arctic Ocean, and countless leaks, the Soviet military nuclear regime has helped to pollute the world on a scale hitherto unknown. Between 1949 and 1989, the Soviet Union detonated 468 atomic bombs, 125 in the atmosphere and 343 underground, at a single site known as the Polygon, at Semipalatinsk in Kazakhstan. Many studies have since revealed the extent of radioactive pollution. The Western Siberian testing grounds remain one of the world's most radioactive places. Although there is no comparison of scale with the magnitude of pollution the United States and the USSR have produced, other countries have contributed to the radioactive contamination of the environment with their own nuclear weapons programs. After 1960, for example, France carried out 210 nuclear explosions in the Sahara and Polynesia, with numerous health consequences for the local communities and populations. Pollutions related to the development and maintenance of the nuclear arsenal are also important, although they were hidden for a long time. The United States and the Soviet Union built tens of thousands of nuclear warheads in the utmost secrecy. In the United States, Hanford's manufacturing facilities near the Columbia River in Washington state, which were inaugurated during the Second World War, dumped thousands of liters of radioactive waste into the river over the course of 50 years. This polluted the Columbia and the region's groundwater over the long term. In 1957, the French Atomic Energy Commission installed in a rural area in the north of the Côte d'Or department the only French metropolitan site for the production and maintenance of nuclear charges for atomic bombs. Despite reassurances about the facility's safety, regular tritium discharges have slowly and discreetly polluted the surrounding environment. 50 years of nuclear weapons production and rivalry between major powers has resulted in the production of tens of millions of cubic meters of enduring, hazardous waste. This radioactive waste has either been temporarily stored in facilities, or simply released into the environment. Nuclear wastes also contaminate the oceans, as stringently pointed out in 1960 by Commandant Jacques-Yves Cousteau in France or, before him, Rachel Carson in The Sea Around Us, 1951. In 1956, a study by the American National Academy of Sciences on the biological effects of atomic radiation concluded that the ocean could be safely used to store waste. Consistent with the traditions of 19th-century expertise, whose first priority was always technological advancement, such reports championed the environment's regenerative capacity. The oceans were deemed sufficiently large and wide to dilute and disperse all radioactive byproducts. From 1947 to 1959, the United States dumped 50,000 barrels of nuclear waste into the Pacific and Atlantic Oceans. The British submerged radioactive containers in the English Channel. Starting in 1963, the year of the greatest Russian and American atmospheric nuclear explosions, international regulations were introduced to control nuclear weapons testing. The Partial Test Ban Treaty, signed on August 5, 1963, by the United States, the Soviet Union, and the United Kingdom, limited and regulated these atmospheric tests. Testing would continue, but the detonations would occur underground to limit the dispersion of radioactive fallout. The overall ecological impact of this new restriction, however, must not be underestimated. The magnitude of the pollution caused by these explosions is fraught with a large number of uncertainties, because they are difficult to assess as the extent of contamination varies according to meteorology, winds, and dilutions. For example, the explosion of a nuclear bomb in the upper atmosphere does not necessarily cause significant ground contamination, even though rains can bring radioactive dust or ash back to Earth. Available data are poor and the effects of low doses of radiation remain controversial. In 2005, a report by the Centers for Disease Control and Prevention concluded that it was impossible to make any reliable estimate, while pointing to the possibility of 11,000 deaths from radiation-induced cancers in the United States since 1950. Despite these uncertainties, the atomic bomb plays an unequivocally important role in the evolution of ecological thought and the emergence of new representations of the environment. The destructive potential of military techniques gave rise to philosophies of fear and catastrophe that served as a matrix for the development of political ecology. In the 1970s, the historian Donald Worster considered July 16, 1945, the date of the first nuclear explosion, the beginning of the Age of Ecology, where humans could no longer deny the effects of their actions on the Earth. For whistleblowers and environmental activists, war was often used as a metaphor for describing global environmental risks. In Our Plundered Planet, 1948, the American biologist Fairfield Osborn warned against this other worldwide war, that of man against nature. The same year, in response to the threat of a Third World War, ecologist William Vogt also proclaimed the prospect of the apocalypse in his book Road to Survival. In the United States, pacifist movements against the Vietnam War and opposition to nuclear weapons provided fertile ground for the emergence of new forms of environmental activism in the 1970s, as illustrated by the career of biologist Barry Commoner. Mobilized in the U.S. Navy during the Second World War, Commoner became a recognized specialist in plant physiology before embarking on the fight against nuclear weapons testing in the late 1950s, from which his environmental activism was born. The nuclear issue also led to the development of new international laws of the sea concerning the management of ocean pollution. In the wake of the United Nations Conference on the Human Environment, 1972, the Convention on the Prevention of Marine Pollution by Dumping of Wastes and Other Matter, also known as the London Convention, prohibited dumping nuclear waste in the sea. It was ratified by 15 countries and entered into force in 1975. And in July 1974, the major powers signed the Treaty on the Limitation of Underground Nuclear Weapon Tests, which supplemented the 1963 text by banning the testing of nuclear weapons with a power greater than 150 kilotons. In the 20th century, war and new military actions played a central role in the evolution of the relationship between nature and society. By initiating new industrial trajectories and the dissemination of new toxic products, and in the establishment of wartime priorities that exempted industry from environmental responsibility, which was in turn conducive to the aggravation of pollution, war transformed environments in myriad ways. The magnitude of 20th century wars provoked unprecedented destruction, of which pollutions were only an often neglected aspect. But these wars should not be analyzed as aberrant phases. Rather, they radicalized polluting practices that existed in times of peace and that, in the emergency of conflict, found new horizons in which to unfold. The chemical, automotive, and aeronautic industries were the main beneficiaries of deadly conflicts. Without them, the enormous resources of men, raw materials, and energy would not have been gathered together. Groups like BASF, Monsanto, or DuPont de Nemours would not have become the industrial empires that flooded the planet with their products. These moments of exacerbated pathological power heralded new energy and industrial trajectories, the consumption and transport revolution, while consolidating the logics of Fordism and generalized mobility at the risk of their pollutions. 8. A high-energy consuming world. Between the First World War and the oil crisis of the 1970s, a new and particularly polluting energy model became entrenched around the world. The decline in national energy intensities the world over, the ratio between energy consumption and energy production, was counterbalanced by an overall increase in global energy production. To wit, total energy use jumped from the equivalent of 2.3 billion metric tons of coal in 1948 to 4.2 billion metric tons in 1960 and 6.8 billion metric tons in 1970, a threefold increase in just 20 years. According to John McNeill, the world consumed more energy over the course of the 20th century than during the entire history of humanity prior to it. While coal was the leading source of energy in the 19th century, it was usurped by petroleum in the 20th century. The annual growth in petroleum production averaged 5% per year, with 84 times more petroleum being produced at the end of the century than at the beginning. It had long been used in its natural solid state, bitumen and naphtha. During the 19th century, the distillation process was perfected to yield a fluid rich in carbon, which was used to produce kerosene to light cities, and oil for sea, and later land, propulsion. Drilling began in the United States, Central America, and the Middle East. Over the course of the century, more and more countries became hydrocarbon producers, from only a handful in 1914 to over 100 in the 1970s. The United States led the way, and its supremacy was bolstered during the Second World War. In 1945, American production accounted for 65.4% of petroleum consumed worldwide, significantly ahead of Venezuela, 13%, or the Eastern Bloc, 6.7%. After 1950, petroleum production exceeded that of coal, increasing from 770 million metric tons to 2,334 million metric tons between 1955 and 1970. By 1960, American production only amounted to 34% of global production as the Middle East and Africa had emerged as major players in the industry. Figure 8.1. Protest against automobile pollution in United States during the 1970s. Photograph, Charles Gatewood. In the 20th century, oil and gasoline engines added to the already wide range of pollutions across the environment. In countries with a high standard of living, numerous demonstrations denounced the ravages of the petroleum civilization. Here, young protesters parade in front of a motor show in the United States and make the link between the increase in population, automobile production, and pollution. As the century unfolded, societies around the world became ever more dependent on petroleum. Although gross consumption of traditional energy sources like wood continued to grow, the relative part they played at this point was in drastic freefall, less than 10% in 1990. But the so-called Glorious 30 period, that rapid, three-decade economic expansion after World War II, came at a high cost, with the use of fossil fuels causing many setbacks in terms of pollution. Every stage of fossil fuel production generated nuisances. From extraction, to transport, to refinement, to final consumption, fossil fuels polluted air, soil, and water. After the 1970s, marked by the oil crisis and higher ecological stakes, changing forms of energy underwent numerous investigations and critiques to examine their ecological impact. The new global energy model for the 20th century identified pollutions and pinpointed their locations. Yes, coal smoke was still a serious issue in many regions of the world, but new challenges needed to be addressed in the face of the expansion of the petroleum industry and its energy derivatives, gas, and expansive hydroelectric and nuclear infrastructure. Coal's deadly fogs. While coal still represented 50% of the world's energy consumption in 1914, the 20th century witnessed the relative decline of its previous supremacy. Coal dropped to a 40% share of global energy consumption by 1946, and to only 25% by the end of the century. Its collapse in North America was even more precipitous, from 70% down to 20%. However, the total global consumption of coal by volume more than doubled from 1,220 million metric tons to 2,500 million metric tons between 1913 and 1980. This increase in absolute consumption helps explains why, despite the change in the structure of the energy mix, smoke, dust, soot, and dirt from coal continued to sully the air in and around cities and industrial sites, to the point where the term smog, 1905, was used frequently to describe the mists and fogs that blackened the air with deadly fumes. Figure 8.2. Global energy consumption since 1915. Source: Yves Mathieu, Atlas Mondial des Energies. Ressources: Consommation et Scenarios d'avenir, Paris, Armand Collin, 2014, 12. The location of coal seams also cut across geopolitical issues. Largely concentrated in the United States and Western Europe before 1914, coal mines and consumer markets expanded to other locations in the years between the two world wars. Most notably, these new territories were located in the Soviet bloc, around the large Kuz-based coal deposits in southern Siberia, and the Donbass region on the border between Ukraine and Russia. Despite the failures of the Great Leap Forward, 1958-1960, coal production in Maoist China continued around a few larger, highly mechanized mines and tens of thousands of smaller mines that employed 20 million miners at the end of the 1950s. In 1976, China became the third largest coal producer in the world. In comparison, India was only a small producer. While coal production was in crisis in the United States, deposits in the Appalachians and Wyoming, and Western Europe. Extraction processes were transformed and outputs improved in the larger mines, thanks to mechanization, their increasing size, and the rationalization of labor. The miner was simultaneously a heroic icon of the proletariat, a hero of emancipation, combining strength and will while confronting the chronic dangers of the subterranean world, as embodied in the USSR by Alexei Stakhanov, and a polarizing figure, due to strong connections to labor organization and the trade union movement. If, in relation to the tonnage of coal extracted and the number of workers, mine shaft collapses and accidents diminished throughout the century, the number of poisonings by dust increased. Indeed, in addition to the de-skilling that it caused in the profession, the mechanization of labor alleviated certain tasks but led to an increase in dust in the mines, caused by drilling machines and rock cutters operated by technicians. Silicosis, a pulmonary illness brought on after inhaling silica dust, was the archetypal mining malady of the 20th century. It was first diagnosed in Great Britain, where a well-organized workers' movement had the ear of a more sympathetic government, compared to in the United States, where silicosis was not detected until much later. Though exact numbers are hard to come by, it is estimated that in French coal mines alone about 100,000 fatalities were the result of silicosis between 1945 and 1987. Unfortunately, lowering the risk of silicosis never really became a national cause in France because employers strategized to employ immigrant and temporary workers as a solution. Also, certain doctors were complicit in efforts to overlook the illness, trade unions and the Communist Party were passive, accurate records were not kept, and there was a general sense of obedience to the paternalistic system in place at the time. In Belgium, pneumoconiosis, a combination of pulmonary illnesses, was not recognized as a malady that warranted compensation until 1964. Such delays in awareness also featured in Italy. In 1954, filmmaker Georges Franju documented the prevalence of dangerous particles in these workplaces in his documentary evocatively titled Les Poussières, Industrial Dusts. Industrial dusts from mines not only affected miners, but also the health of those living around the mines, as was shown in the United States by historians Gerald Markowitz and David Rossner. Coking plants were usually constructed close to coal mines and were recognizable by the thick plumes of smoke. Their production of purified coal also linked him to the carbon chemistry industry, a particularly polluting sector. Moreover, coal deposits and mining towns were affected by soil erosion, groundwater pollution, and destruction of the surrounding countryside, all of which sparked numerous conflicts over land use. In China, health and environmental damage was linked to a dangerously high number of cave-ins, as well as atmospheric pollution, without provoking any major protests. The filmmaker Wang Bing filmed the crisis of Shanxi Province's vast coal and metallurgical industrial complex in northeast China, highlighting its ecological devastation and the helplessness of former workers. Developed in 1933 under Japanese occupation to produce military equipment, the mining region was transformed into a huge state industrial zone after 1949. It employed 1 million workers at the height of exploitation during the 1970s. In typical form for the grandiose projects of the Cultural Revolution, it left the region devastated. The land and its people still bear testimony to this today. But the main feature that characterized the metamorphosis in coal-based industries of the 20th century was the change in production scale. In his novel I Married a Communist, set in McCarthyite America in the 1950s, the American author Philip Roth describes the narrator's surprise, despite his familiarity with industrial landscapes, when on a train ride he passed factories in Gary, Indiana, near Chicago, where coal and steel industries coexist under the control of one industrial giant, U.S. Steel. Coming as I did from industrial North Jersey, I confronted a not unfamiliar landscape. We had the big factories and the tiny job shops, we had the grime, we had the smells. We had the black smoke rising from high stacks, a lot of smoke coming up everywhere. We had the dirt and we had the stink, but what we didn't have was the open hearth furnaces that lit up the sky when the mills were pouring steel, a red sky that on clear nights I could see, from as far away as my dormitory window, way down in Jarrige. Concentrated here was the power of the Midwest. What they had here was a steel-making operation, miles and miles of it stretching along the lake through 2 states and vaster than any other in the world, coke furnaces and oxygen furnaces transforming iron ore into steel, overhead ladles carrying tons of molten steel, hot metal pouring like lava into molds, and amid all this flash and dust and danger and noise, sucking in vapors that could ruin them, men at labor around the clock, men at work that was never finished. While I took in what looked to me to be mightily up-to-date, modern, the very emblem of the industrial 20th century, no fact of my life seemed more serious than that. A change in the scale of production also occurred in the USSR, where coal-based heavy industry became the showcase of the new regime's exploits and the extent of its power. Certain areas were particularly affected, such as the Ural-Kuznets combine that connected the iron mines at Magnitogorsk to the coking coal mines of the Kemerovo-Novosibirsk-Altai Triangle, situated 2,000 kilometers away. The rapid industrialization of Magnitogorsk, following the model of the U.S. steel factories at Jarrige, was a priority in Stalin's 5-year plan in 1930. Linking these immense coal and iron ore reserves created the perfect site for a steel industry to thrive and rival any in the United States. Safety measures and air pollution controls were not high priorities. Bronchitis, asthma, and other respiratory illnesses increased in what was to become one of the most polluted cities on the planet. Sometimes, a stifling, coal dust-laden fog would rapidly descend. In December 1930, a mysterious fog enveloped the Meuse Valley in Belgium for several days. Many thousands of people complained of breathing problems. Roughly 60 people died. In the search for the cause, in line with the expertise and decision-making processes of the 19th century, the state health services at first wanted to reassure the public that what had happened was the result of a purely meteorological event, or an aggressive flu epidemic. Ultimately, however, blame came to rest on industry. The valley was one of the zinc manufacturing centers of the world, producing more than 200,000 metric tons per year in the late 1920s, which amounted to 15% of global production or the equivalent of 1/3 of Europe's overall output. Transforming mineral into metal required copious amounts of coal, 4 or 5 times the amount of zinc finally produced. The results of a 10-month inquest by a committee of experts concluded that the noxiousness of the fog was due to sulfide particles resulting from the burning of coal, notably sulfur dioxide and sulfuric acid. Yet, despite these conclusions, the catastrophe, presented as inevitable, did not highlight the responsibility of the zinc industry, a significant contributor to the Belgian economy, and the second largest producer in the world after the United States. Instead, the blame shifted to weather inversion, the valley's topography, and the fact that certain people were more susceptible to the adverse climate conditions that had manifested. Coal and coal-related industries were not to blame. Figure 8.3. Fog in the Meuse Valley, 1930. Source: Albert Humblot Collection. In the face of disasters, absolution of industry was a common theme. The Donora catastrophe in the United States served as another example. Donora was an industrial zinc city in a valley near Pittsburgh where, in October 1948, a significant portion of the local population was poisoned by a smog linked to a weather episode that trapped carbonaceous particles in the air. As was the case in the Meuse Valley, a few dozen people perished, and reports from the inquiry into the incident incriminated natural conditions more readily than economic activity, proof that regulators and experts, notably in the Industrial Health and Safety Division, a branch of the Public Health Service, had vested interests in industrial production and its major companies, particularly U.S. Steel. The death rate associated with coal did not only affect mines and industrial sites. Although mostly used in the form of coke, coal remained the most widely used form of fuel in homes, workshops, and urban factories. In spite of the advancements in smoke filtration systems, sulfur and nitrogen oxides, fine particles, and greenhouse gases were still being released into the air. It is true, however, that, on the coal front, the situation had changed since the 19th century. Coke had become widespread and the coking process took place mainly at coal mines, while electricity was gradually replacing gas lighting and steam engines, much to the benefit of cleaner city air, and reducing the number of factories necessary for the distillation of coal. Of course, thermal power generation plants were often established in close proximity to cities, and they used a lot of coal as a fuel source. But at the same time, energy converters were constantly being improved with technological advances, so that while in 1955 it took on average 0.7 TCE, tons of coal equivalent, to produce 1,000 kilowatt-hours, by 1967 only 0.458 TCE were required. Despite these structural changes, and before the spread of electrification and natural gas and fuel oil were in general use, large European cities were regularly engulfed in fog caused by the burning of coal. In Paris, for example, the height of coal consumption was between 1930 and 1950, where it accounted for 80% of the city's total energy use. The city's coal dependency provoked widespread concerns in the press. In 1926, in an article on carbon dioxide, the French communist newspaper L'Humanité lamented that, "We do not know how to burn coal, city air is vitiated by fumes and discarded debris." 1. Factories' chimneys in Paris emit 1,500 kilos of ash an hour. In order to better evaluate these emissions, measuring instruments became ever more precise, but slowly. The Ringelmann scale for measuring the apparent density of smoke, black, thick, and extended, was in use for quite some time. During the 1930s, devices were invented in Great Britain to measure levels of sulfur dioxide. Meteorological observations were boosted by new measuring apparatus and measuring stations, which became standard, although visual and olfactory perception remained in regular use until the 1950s. At that point, academic research led to the creation of more sophisticated sensors. Different types of pollutants could be identified and the instrument's calibrations became increasingly exact. Above all, not only sources of pollution were measured, but so too were levels of pollution in cities. The air became an object of permanent, technical surveillance. Unfortunately, advancements in surveillance equipment did not impede the increase in urban air pollution. After the Second World War, in Great Britain, the country with the most measuring devices, the mortality rate from bronchitis was 62 in every 100,000, compared with 4.5. In France, the majority of these deaths were caused by coal smoke. Great Britain was also the place where the biggest public health catastrophe struck after the war. On December 1, 1952, in response to the great demand for heat, the British government stopped rationing nutty slack, a poor-quality coal that produced a lot of smoke. A few days later, London was completely hemmed in by smog. The mortality rate for this period is the subject of heated debate, with historians estimating the death count as anywhere between 4,000 and 12,000. Such catastrophes stemmed from the fact that the fight against pollution still confronted, just as it had done in the 19th century, a laissez-faire regime, a blind trust in industry to install the necessary filters, and a general allergy to regulatory oversight. New urban pollutions, from growing numbers of automobiles, also introduced new challenges. If, in the years that followed, air pollution from coal decreased in European and North American cities, this was the result of a displacement of nuisances and the adoption of a new energy system founded on petroleum and natural gas, as well as hydraulic and nuclear energies. The curse of black gold. The rise of petroleum in the 20th century transformed industrial zones profoundly and added new sources of pollution to carbon emissions. If hydrocarbons were more or less toxic depending on the type of product used and the particular environment contaminated, pollutions varied just as much depending on whether petroleum was being extracted, transformed, or burned. Still in its nascent state outside of the United States before the Great War, petroleum's role in global energy consumption grew from 3.4% in 1915 to 50% in 1973, surpassing coal around 1965. It completely overhauled knowledge, global geopolitics, and consumer practices. According to Timothy Mitchell, who examined the socio-political stakes of this liquid fuel, oil would play its part in the vast project of social control and the domestication of the labor movement, which was particularly contentious in the coalfields. It would also influence the evolution of the portrayal of the working class, as the figure of the coal miner was gradually supplanted by that of the qualified worker in the petrochemical industry. While coal pollution remained for the most part limited to areas around mines, ovens, and steam engines, petroleum pollution spread over much vaster global reaches because its uses were far more numerous and it was far easier and cheaper to transport. Pollution began with extraction, primary transformation, and transport. Ecological damage from oil began in the United States, where production jumped from 60 million barrels per year in 1900 to 600 million barrels by the early 1920s. New oil states emerged: Texas, where the first oil deposit was drilled in 1901, and California. Born in the California oil boom, Los Angeles' population increased from 500,000 in 1920 to 1.2 million in 1930. Wells and derricks sprang up even in the heart of the city, between Long Beach and the city center, and up Signal Hill, which was nicknamed Porcupine Hill, because of the number of derricks poking out of it. During peak production in 1923, tourist associations promoting seaside vacations began to denounce the erosion and pollution of the shorelines. In his novel Oil, 1927, the muckraking journalist Upton Sinclair gave insight into the obsession with profit, how the working class was being exploited, and how nature was being destroyed by drilling. In the decades that followed, oil reserves diminished, forcing drilling to move farther from cities, inland to deserts and then out to sea in the 1960s. Each migration spread the pollutions that accompanied these activities still further afield. The first derricks were equipped with modern pumps, the iconic nodding donkeys, in Texas in 1925, further increasing access to underground resources and the speed of extraction. Along the coast of certain southern states, ports that received oil and oil fields were rapidly sullied by hydrocarbons, much to the chagrin and financial cost of fishermen and residents. Damage was so bad that the U.S. Bureau of Fisheries wrote a report titled Danger to Fisheries of Oil and Tar Pollution, 1921. Even insurance companies were alarmed by the magnitude and rapid growth of the problem. Houston, a former capital of the cotton trade, became a petroleum hub, more thoroughly shaped by the oil industry than Pennsylvania, Southern California, Dallas, or Los Angeles. With its dense concentration of refineries, petrochemical plants, transport infrastructures, and storage facilities, Houston was both the energy capital of America and the site of the worst petroleum pollution in the United States in the 1930s. Complaints were limited and also curtailed by a local political life controlled by business and conservative elites, who prevented any regulation of the extraction process. In 1938, North America was producing 60% of the world's oil, and its companies, Standard Oil, John Rockefeller's historic company, ExxonMobil, and Chevron, became multinationals and the largest of the mining giants. After the fall of the Iberian empires, South America became an exclusive domain for American interests, and the second largest prospecting terrain for petroleum companies. In Mexico, the second largest producer in the world after the Great War, the small port of Tampico, north of Veracruz and located close to numerous waterways and tropical forests, was by 1921 a city of 100,000 inhabitants. 58 different oil companies were established there, along with 16 refineries and 400 kilometers of pipeline. This unbridled infrastructure was the source of numerous emissions, leaks, and spills, all of which had a destructive impact on the local environment. In 1938, after a drop in domestic oil production, Mexican President Cárdenas signed an order that expropriated nearly all of the foreign oil companies operating in Mexico, in turn leaving Venezuela to become the second largest producer of oil in the world. Lake Maracaibo, the most important freshwater reserve on the continent, was gravely contaminated by the petroleum industry as wells were drilled using archaic techniques. In addition, refineries dumped huge quantities of petroleum residues, which sterilized wide swaths of land and put an end to agriculture in the area. In the interwar period, the oil industry also developed in Western Europe, mainly in the Netherlands, Royal Dutch Shell, and Great Britain, British Petroleum, which relied heavily on the colonial empires in Asia and the Middle East. Although not quite as developed, the oil boom in France gives an idea of the extent of its pollutions. The Compagnie Française des Pétroles, CFP, was only created by the state in 1924. Although most of the petroleum and its derivatives were imported in the early 1920s, refineries in France produced 400,000 metric tons of petroleum products in 1931 and more than 8 million metric tons by 1938. At that point, 15 refineries, located mainly in the lower Seine Valley and on the banks of Étang-de-Berre Lagoon near Marseille, refined petroleum from Romania and the Middle East. The state established new prospecting companies to stimulate the sector: Régie Autonome des Pétroles, 1939, Société Nationale des Pétroles d'Aquitaine, 1941, and the Bureau de Recherches de Pétrole, 1945. They became one group in 1966, which eventually became known as Elf Aquitaine. This new entity benefited from the opportunity to exploit oil in Algeria. Around the same time, the CFP became a subsidiary of Total in 1965, the same year that oil surpassed coal in global energy consumption. A new generation of refineries was established at Faisin, south of Lyon, as well as around Étang de Berra, to handle the oil imports from Algeria. With such high stakes at play worldwide, risks and pollutions were given little attention in spite of complaints and recurring protests by locals. In 1936, the mayor of Rouen, in southwest France, complained about pollution from two petroleum refineries in the Gironde estuary. The companies were exonerated from all responsibility by the prefect, who issued a decree prohibiting discharges of hydrocarbons from ships' bilges into sea or river water. Around that time, the newspaper L'Humanité reported that 1,000 fishers on Étang de Berra had gone on strike, because of pollution of the lake water, resulting from ever-increasing discharges from oil refineries. Since the First World War, the area had become a jewel in the crown of the chemical and petroleum industries, in large part due to a deliberate desire of the Chamber of Commerce in Marseille to make it the dirty, industrial suburb of the Phocéan city. After 1945, the rise in importance of hydrocarbons drove the petrochemical industrialization of Étang de Berra forward. The development of the neighboring harbour Fos-sur-Mer, situated on 20,000 hectares, about 49,000 acres, soon followed. This development had the support of both central and regional authorities. Arbitrating between incommensurable industrial, farming, and fishing interests, the state was swift in throwing its lot behind black gold. In 1957, fishing was prohibited in the lake because of the contaminated waters. In fact, this coastal region that had previously been a place to fish and walk and for birds to find shelter, was now gravely harmed by polluting hydrocarbons, which the banning of fishing could evidently do nothing about. On the contrary, as a priority of the 5th and 6th plans, 1966-1975, designed to help Marseille compete with the larger ports in northern Europe, such as Rotterdam, further industrialization was encouraged and abetted. In 1973, Marseille witnessed the highest level of oil traffic ever. Close to 95 million metric tons passed through the city, while daily emissions of sulfur dioxide into the air were estimated to be between 800 and 900 metric tons at the beginning of 1975. On the initiative of local elected officials, often communists or fishers, grouped under the umbrella of the CGT, General Confederation of Labour, complaints were drafted. In response, the prefect created the Secrétariat Permanent pour les Problèmes de Pollution Industrielle, SPPPI, charged with supervising industrial waste, coordinating construction permits, and setting standards amongst industrialists. In the east, despite the early exploitation of oil fields at Baku, Soviet authorities continued to focus on coal, and it was not until the 1950s that they embraced petroleum. The shift was remarkable. In 1960, oil accounted for 30% of energy consumption in the Soviet Union. At that point the country was producing 700 million metric tons of oil, and there was a frenzy of refinery and pipeline construction. Reserves in the Caucasus region of Azerbaijan were surpassed by those in the Volga-Ural region. The economic stakes were such that the issue of ecological devastation was systematically suppressed even though damage was apparent, especially in the Baku region. The Caspian Sea's vast basin, into which the Volga flowed, also fell victim to petroleum pollution. Rivers and the inland sea rapidly deteriorated. The sturgeon population diminished drastically, compromising caviar production. In Africa, oil exploitation did not begin in earnest until the 1950s, coinciding with a wave of decolonization. The French Equatorial Africa Oil Company, SPAEF, a branch of the French Empire, was established in 1949, but the first oil reserves were not found until 1956 in Gabon and the Algerian desert at Hassi Messaoud. In Gabon, refineries quickly established themselves in Port Gentil and the region south of the town. Crude oil production increased from 1.4 million metric tons in 1966 to more than 11 million metric tons in 1976. Most was produced offshore, 85% of it exported abroad. In Nigeria, after the civil war that led to independence in 1960, the petroleum industry grew rapidly around 3 large deposits in the Niger River Delta. Production of crude oil increased from 396 million barrels in 1970 to more than 823 million barrels in 1974. But numerous spills seriously contaminated the delta, damaging fishing areas and agricultural lands at the expense of local populations, among them the indigenous Ogoni people who subsisted on local resources. Their protests were suppressed by authorities, whose only real concern was to protect the interests of large companies. As in many regions where the petroleum industry operated, notably the Middle East and the Persian Gulf, pollution remained invisible for quite some time, because of its relative isolation in a desert setting removed from larger towns and cities. This was especially the case in Iran, Iraq, and Saudi Arabia, all of which became major players in the petroleum industry after the Second World War. Because of geopolitical tensions, these countries had difficulty extricating themselves from British and American influence. In 1960, however, their struggle led to the foundation of OPEC, Organization of the Petroleum Exporting Countries. The oil energy system was based on an increasingly globalized economy in which transport played a primary role in connecting production sites to their consumer markets. In 1966, petroleum in and of itself accounted for 53% of the total value of global trade. Transporting these great quantities of petroleum required immense infrastructure. Much of that infrastructure proved fragile and became the source of spills and accidents that resulted in long-term contaminations of oceans and soil. Between 1953 and 1967, gas pipelines grew to 2.4 times the length they had previously been to cover a total of 1.9 million kilometers. At the same time, the average size of oil tankers drastically increased as the age of supertankers dawned, a leap from an average size of 10,000 metric tons around 1950 to 200,000 metric tons by 1961. The closure of the Suez Canal after the Six-Day War in 1967 further accelerated the race for bigger and bigger tankers. Also in 1967, the Torrey Canyon oil tanker was shipwrecked, causing an environmental disaster, the first in a chronicle of big oil spills. Some 40,000 metric tons of crude oil were spilled into the English Channel, with pollution spreading 350 kilometers from the coast, killing almost 100,000 birds. 10 years later, the Amoco Cadiz catastrophe resulted in more than 200,000 metric tons of crude oil contaminating 400 kilometers of the coastline in Brittany. In 1979, the explosion of an offshore oil field in the Gulf of Mexico poured 600,000 metric tons of crude oil into the sea. These spectacular oil spills overshadowed many more not covered by the media. In fact, innumerable spills that were less visible contributed overall to the destruction of environments around petroleum sites. At least 1,500 maritime spillages greater than 500 metric tons of oil were recorded between 1951 and 1999. Add to these the routine discharges of oil at sea, by definition uncontrollable, but numerous nonetheless. The smell of gasoline. In the final pages of A Simple Life, a novel by Émile Guillaumin about country life in France in the 19th century, the narrator, in the twilight of his life, reminisces about how the world around him has changed over the course of his life. His vantage point was 1902. With the sudden loud entrance of an automobile intruding on the peaceful pastoral surroundings, he intuits that a change is coming to civilization. Now there are carriages that have no need of horses. I would suddenly hear a noise, shrill and disagreeable, which got louder and louder, and the motor car, carrying men fantastically dressed in caps and oilcloth jackets and wearing goggles like stonebreakers, would pass rapidly, raising a cloud of dust and leaving behind it a disgusting smell of petrol. In 1899, the journalist and satirist Léon Charles Bienvenu, known by his pen name Touch It Out, ranted against the automobile. It threatens, poisons, and deafens everyone with its puff, bowling us over with its petrol fumes, and its unconventional appearance. From the outset the sudden entrance of the automobile was frowned upon, with drivers drawing disapproval. Those smelly and noisy machines were considered destructive and dangerous. The dust that they kicked up and their speed were yet other symptoms of the oil madness that characterized them, and over several years, a struggle for space and class seized fossil fuel transportation. Those in favor of the motor car, typically the elite who could afford to buy such a luxury item, argued that the car, driven by an internal combustion engine, invented in 1893, would be better for the environment, because horses would no longer be needed and their waste would therefore no longer sully the roadways. Industrialists, for their part, managed to focus attention on accidents by defining the problem in terms of risk behavior, thereby putting an educational morality on the political agenda, while ruling out the possibility of questioning the act of driving in and of itself. The outcome was an historically important success and a founding feature of modern civilization in the 20th century, the social acceptance of a major risk, the automobile. Every year since World War II, car traffic has killed a few 100,000 people worldwide. 1.3 million people die every year in the 21st century, peaking in France and the United States in 1972 with 16,000 and 54,400 killed, respectively. The automobile's environmental consequences were considerable. Without even taking into consideration its symbolism, social uses, or components, but focusing only on the issue of energy, the motor car opened up a new Pandora's box for fossil fuel consumption, mainly oil. Both the internal and external combustion engines, developed in the 1860s and adapted for individual locomotion, were introduced into the first automobiles at the end of the 19th century. An engine is a sensitive piece of machinery. It was necessary to refine the oil to eliminate the impurities, then to distill it, which meant separating the different components to obtain, in a schematic fashion, fuel for automobiles, kerosene for airplanes, diesel for trucks and tractors, heating oil, and heavy oil, essentially bitumen, for industry and maritime navigation. These refining and distilling operations were extremely polluting in themselves, which explains why petrochemical plants were often situated far from populated areas, in France at Faisin, south of Lyon, Étampes-de-Berre, and Fos-sur-Mer, which did nothing to slow down global pollution, of course. Producing diverse types of fuel progressed exponentially throughout the century, in keeping with the growing number of cars that needed fuel. The United States was one of the first countries to produce a high quantity of cars. In 1913, it boasted one car for every 77 people. In France there was one for every 318 people. In Italy only one for every 2,000 people. In Africa and Asia this luxury item was still very rare. Motorization spread through Europe and the United States during the interwar period. A significant jump from 1 million motor vehicles worldwide in 1910 to 50 million in 1930, to 100 million in 1955, and 500 million by 1985. In 1950, 5 million cars were manufactured. The rapid increase in production meant that another 1 million were added each year. A symbol of Western individualism, the car took longer to become commonplace in the USSR. In 1970, only 1.5 million individual vehicles were in circulation, compared with 13 million in France at the same time. It should be noted, however, that Russian cars had a reputation for being especially polluting. Accompanying the increase in fuel consumption, road traffic became the primary cause of pollution in the 1960s. Apart from carbon dioxide and methane, two greenhouse gases, automobiles also emitted gases toxic to humans and ecosystems: carbon monoxide, ozone, nitrogen oxide, sulfur dioxide, fine particles, VOCs, volatile organic compounds, and lead, added to gasoline in 1921 to improve combustion. By the end of the century, lead additives had been banned in numerous countries, but gasoline still contained ordinarily more than 150 other chemical substances added to hydrocarbons to improve the octane value, increase combustion efficiency, and protect the motor and exhaust components. Diesel, typically limited to trucks and tractors prior to the late 1970s, emitted a complex mix of gases including nitrogen oxide, carbon monoxide, formaldehyde, acetaldehyde, benzene, and polycyclic aromatic hydrocarbons, with and without nitrates. Diesel motors spewed up to 100 times more fine particles than gasoline engines. Being only 0.01 of a micrometer to 1 micrometer in size, these particles were small enough to lodge in the lung tissue, and those smaller than 0.1 micrometers, ultrafine particles, were able to invade the lungs through the vessel wall to enter the bloodstream to reach other systems in the organism, such as the cardiovascular system. But air pollution from automobiles was only slowly identified as a public health risk. In 1910, the German manufacturer Wilhelm Maybach, of carburetor fame, wrote an essay titled Über Rauchbelastung von Automobilen, on the problem of automobile fumes. In 1926, the Journal of the American Medical Association carried out a now famous and often cited study that revealed the high level of carbon monoxide in police officers' blood in Philadelphia. For scientists and engineers, however, fumes and public health problems were first and foremost a technical issue, with a few proposing perfuming the gaseous exhaust fumes to stifle this inconvenience. Public authorities were hesitant to attempt to regulate this rapidly growing sector, which provided an increasing number of jobs. German regulations did try to control gaseous exhaust fumes through the creation of a special police patrol in Berlin during the interwar period, but it was unsuccessful. Concern over automobile pollution grew during the 1960s and 1970s. Despite the importance of the automobile industry for the region's economy, the United Automobile Workers, UAW, union in Detroit rallied around improving working conditions and controlling fume emissions. In 1969, it helped to create the League Against Pollution, whose goal was to improve the environment for local inhabitants. Difficulties in regulating automobile pollution and the relationships that civil societies had with this problem were also shaped by the influence of large industrial lobbies and national contexts. In Greece, the absence of car manufacturers led to more ambitious public policies than in France, where the number of automobiles was much larger and car manufacturers more politically powerful. A turning point in awareness took place in Los Angeles as a result of chronic post-war smog. Ironically, the City of Angels had originally been founded by immigrants seeking pure air to heal tuberculosis, but because of its topography and weather conditions, its location and low atmosphere tended to trap fumes. The city, which had a population of barely 100,000 in 1914, had become a megalopolis of 6 million people by 1960. Few cities were more designed with the automobile so explicitly in mind. The railway tracks and tramways had been dismantled in the 1920s when the decision was made to create a car-friendly city. In 1950, close to 3 million motor vehicles were in circulation in Los Angeles, contributing levels of pollution akin to those coming from industry. 1,160 metric tons of toxic gases per day compared with 1,280 from industry. Smog was an issue almost all year round, affecting public health and tree growth within an 80-kilometer radius around the city. Indeed, every city that had based its development around the automobile experienced myriad problems. Those like Los Angeles that did not have the benefit of wind to eliminate pollution were particularly susceptible. In Athens and Mexico City the number of vehicles increased, with the latter seeing a rise from 100,000 in 1950 to 2 million in 1980. In Bombay, the 400,000 vehicles in circulation at the beginning of the 1980s were responsible for roughly 90% of air pollution. Influential city planners such as Jane Jacobs and Louis Mumford vociferously condemned the nuisances derived from auto-centric urban development, while other protest groups launched boycotts and demonstration campaigns to put pressure on automobile manufacturers. In this context, technological improvement continued to be put forward as a viable solution. In 1966, the catalytic converter, which converts certain exhaust fumes into less toxic matter, was built into engines in California. Car manufacturers worldwide did eventually comply with new standards and measures put in place to reduce pollution at the beginning of the 1970s. This was necessary for them to remain competitive in foreign markets, in particular the North American market. In fact, competition is what drove the continued improvement of filtering fine particles and the energy efficiency of engines, which led to an overall reduction in pollutions over the remainder of the century. Or, rather, polluting substances were replaced by others, the deleterious effects of which would not be revealed until later. Regularly, the industry promised the clean car. In August 1968, the American newspaper Nation's Business announced, perhaps a little prematurely, that the day is close at hand when the automobile will no longer be considered a major source of pollution. 3 years later, while pollution from cars continued to rise, the propaganda magazine Petrol Progress, published by SO, Standard Oil, announced the next triumph of the electric car while asserting that in theory hydrocarbon combustion should only produce harmless products. But the gains were in fact largely offset by the increased distances traveled, the soaring number of cars on the road, and the power of the engines in them. This explains why, similar to the case with smoky furnaces in the 19th century, the undeniable drop in toxic releases per unit actually added to, through addition and progression, the global volume of pollutions emitted. The unbearable lightness of natural gas. Faced with the environmental risks associated with other fossil fuel energy sources, natural gas seemed to be a welcome alternative in the 1960s, because it produced fewer toxic fumes. As a source of energy, natural gas was already well known. It is a fossil fuel naturally present in gaseous form under pressure in the porous rocks of the subsoil, composed of a mixture of hydrocarbons, mainly methane but also propane, butane, ethane, and pentane, but its implementation was complex. Prior to 1945, gas consumption was limited and concentrated, because of the absence of infrastructure to transport it, even though the development of leak-proof seals dated back to the end of the 19th century and the first major gas pipeline network was constructed in the United States in the 1920s. In 1950, the United States was producing 90% of the world's supply of natural gas, and the number of homes using it doubled between 1945 and 1955, particularly in new residential suburbs in California. Between 1950 and 1973 in Western Europe, consumption increased 800%, and global consumption climbed from the equivalent of 266 million metric tons of petroleum in 1949 to 1.2 billion metric tons in 1973. Natural gas gradually replaced the former gas supply known as city gas, which had been derived from the distillation of coal and the cracking of petroleum products. The latter was a particularly toxic process, because it emitted carbon monoxide. Natural gas, however, released no dust, only a little sulfur dioxide, SO, nitrogen dioxide, number 2, and less carbon dioxide, CO2, than other fossil fuels. Its methane content, a significant greenhouse gas, was only a marginal issue before 1980. Old factories and their extremely harmful, and dangerous, manufacturing processes in the heart of cities gave way to the more discreet infrastructure of natural gas. Its high calorific power, double that of coal gas, and low toxicity propelled natural gas over the next few decades to become an essential fuel in the effort to overcome carbon pollution, while also meeting growing energy demands around the world. Fluid, efficient, and easy to use domestically and industrially, natural gas has continued to be presented and promoted as a clean energy source, which has contributed to its success. The emergence of new marketing techniques such as liquefied gas in 1964, which enabled natural gas to be transported in liquid form, at -161 C, reducing its volume by 600 times, galvanized the worldwide distribution of this form of energy far from the site of its natural deposits. This mode of transport by gas carrier completed a network of pipelines that were difficult and costly to build. Japan, anxious to diversify its energy supply, became one of the biggest importers of liquid gas from Alaska. Japanese authorities saw this as an opportunity to reduce air pollution in larger coastal cities, which up until that point had been powered by coal and oil. In the 1960s, new deposits of gas were tapped in the Volga, the Caucasus, the Central Asian republics, Algeria, Iran, Libya, and Indonesia. In Europe, significant gas fields were discovered in Norway, the Netherlands, and the United Kingdom. In all of these countries, the gas sector was considered strategic, and controlled by the state. Big national public companies such as Gaz de France, British Gas, Eni, Italy, Distrigas, Belgium, and Gasunie, Netherlands, maintained national monopolies on imports, transport, and distribution. However, as deposits were depleted, Europe became more and more dependent on gas imports from abroad. Although it was far less polluting than coal or oil, natural gas was still a fossil fuel that emitted greenhouse gases such as nitrogen oxides, sulfur oxides, and reactive hydrocarbons at every stage of the exploitation process. Indeed, once extracted, in order to be commercially viable, it had to be treated and purified through a series of transformation steps from extraction at the source, to storage, compression, transport, and distribution. Byproducts, such as helium or corrosive compounds like sulfur, required disposal. Moreover, in regions around gas fields, soil and water became heavily polluted. Prior to 1960, considerable quantities of residual gases were simply burned off, as companies were not sure what else to do with them. In Iran, for example, the world's second largest gas reserve after Russia, billions of cubic meters of methane from refineries or natural gas were simply left to burn. The National Iranian Gas Company continued to simply burn off methane until 1966, when it constructed a network of pipelines to export the gas abroad. The environmental impact of exploiting natural gas was still not completely understood. On a local scale, it provoked new cycles of pollution, as was the case at Lac, one of France's biggest natural gas deposits in the southwest of the country. The discovery of natural gas in 1951 was met with great enthusiasm during the post-war reconstruction phase. Lac was hailed as the French Texas. The press celebrated the prodigious force of nature tamed by French genius. The political and economic elite sang the praises of this industry, which they imagined would bring wealth, employment, and modernity to a region perceived as isolated and backwards. Within a few years, however, the province of Béarn, traditionally a small agricultural corner of France, was overwhelmed by the construction of factories, wells, and pipes that branched out over a 10-kilometer radius. The brutality of the process and the first environmental breaches led to complaints and conflicts, but these were muffled in a general sense of euphoria. However, some protests by local residents against nuisances produced by the infrastructure for natural gas extraction were relayed by certain unions like the French Confederation of Christian Workers, CFTC, in 1961. The residents of Arons, a neighboring village of Lac, are apprehensive about living so close to industrial plants, which they fear might negatively impact their health. The gas and sulfur fumes make the crops in the fields wither and die, the leaves on the grapevines turn yellow long before harvest time, and farmers, who have lived here in peace for generations, have come face to face with the gas mask and fear. Local complaints were in response to sulfur odors. Fishers complained that the fish they caught had acquired the taste of petroleum. Farmers' land was bought from them. New pipeline construction damaged many of their fields. In September 1961, a union committee was formed to study the agricultural problems of the Lac commune and protest the toxic fallout of sulfur dioxide and fluorine. In the face of economic optimism, a growing countercurrent denounced these nuisances for what they really were. In 1959, Bernard Charbonneau, who taught and lived a few kilometers from the site, also spoke out about the Lac myths and how his beloved Bern had been transformed into a garbage dump. A few years later, François Mauriac lamented the irreparable damage caused by the discovery of hydrocarbons. There is no help for nature, violated day and night, on all the roads and from the sky above, or the assaulted earth, and condemned to chemical overproduction, gutted by prospectors there where we thought it best protected. Quote, fluid electricity. From the end of the 19th century, electricity became one of the fastest growing forms of energy. It could fulfill myriad uses, without foul-smelling, toxic smoke, or vapors associated with other fuels needed for steam engines, combustion engines, and lighting. In the 1920s, advertising focused on how quiet, clean, and safe electric energy was for its consumers and where they live, as opposed to coal and its grime. However, generating electricity required primary fuels, which meant that rather than eliminating pollution, electricity simply relocated pollutions upstream to sites of production. The electric current and the fantasy of its cleanliness contributed to the naturalization of energy pollution by hiding it from the consumer. Sources of pollution were moved to sites away from populated areas, thanks to sophisticated distribution networks that linked the fuel source to consumers. Initially scattered between a number of small production sites, in Great Britain, for example, half of the providers were municipal around 1900. Large coal power plants were built further from city centers and therefore required a means by which to transport electricity to consumers. A network of high-voltage wires was developed for this purpose over the course of the century. The first line to carry 100,000 volts was erected in California in 1908, followed by 200,000-volt lines in the 1930s. The USSR constructed a 500,000-volt line in 1961. It did not take long for electricity to be supplied to cities in the West, but supply to rural areas was slower. The USSR lagged behind and its electricity supply remained well behind that of the West. However, Soviet engineers, confident in the power of technology, built many more power plants under Khrushchev. At the beginning of the 1970s, all industrialized countries had adequate electricity supply and networks. Africa and most of Asia did not. To respond to the extraordinary development of electricity networks, it was necessary to mobilize many sources of primary energy, harnessed and converted at large power stations. Electricity was subsequently transported by means of metal cables, made primarily of copper, which was extracted from vast mines scattered around the world, with each one producing its own litany of environmental nuisances. Electricity provides an effective illustration of one of the central features of modern technology. It makes invisible the resources and waste required for its operation and removes the waste, pollution, and risks that accompany its production. Thus, to the consumer, electricity is made to seem a clean, non-polluting commodity. Thermal processes used to generate electricity by burning wood, coal, gas, or oil in a turbine that drove a generating alternator remained dominant in the 20th century. Ever-expanding electricity networks and the growing demand for energy increased the consumption of fossil fuels. Therefore, while individual cities reduced their smoke levels during the century, global pollutions continued to grow, as the case with coal in Germany demonstrated. Another of electricity's laudable virtues was the fact that it could be produced without the use of combustible fuels, thanks to running water, wind, and the fission of atoms, all of which could power turbines. Hydroelectricity was first developed at the end of the 19th century, initially near cities. Later, with the construction of more extensive and sophisticated networks, larger hydroelectric power stations, working in conjunction with dams and reservoirs, were built further afield. The first giant dams were built on the Colorado River in the United States and on the Volga River in the USSR in the 1930s. China was one of the best equipped countries, but the majority of its dams were small and used primarily for irrigation up until the end of the 1970s. Over the course of the 20th century, one large dam, over 15 meters high, was opened every day somewhere in the world. Their number swelled from 5,000 in 1950 to 30,000 by 1975. These large dams involved heavy investments and were backed by enough clout to overcome the strong resistance to them. They embodied state power, their capacity to transform nature, and to tame the elements in the name of national prestige and independence. All of the world's top political leaders used this tactic to reinforce their power. Roosevelt during the 1930s crisis, Stalin in his attempt to bend the rivers to the will of the state and its planners, Colonel Nasser in Egypt, anxious to modernize his country to assure political independence, and Nehru, in an independent India after 1947, in order to build modern temples that were supposed to encourage progress. This direct link between dams and politics explains why many of these projects were unprofitable and posed ecological problems. The artificial flooding of valleys upstream from dams involved firstly displacing huge populations, 20 million people in India between 1947 and 1992, 50,000 Nubians between 1960 and 1971 during the construction of the Aswan Dam in Egypt, and a total of between 60 million to 80 million people worldwide since the 1930s. Even if actual pollution while building a dam is only a partial aspect of the process, it must be noted that a dam permanently alters the environment around it. Dams accelerated the salinization of soils, diminished alluvial deposits, increasing the need for pesticides in the valley, increased waste as a result of evaporation, modified local climates and landscapes, and contributed to the contamination of their surroundings and the loss of fish and fishing grounds. Moreover, new energy supplied by the dam attracted new industry. After the construction of the Aswan Dam in Egypt, agricultural and industrial pollutions drastically increased due to the use of chemical fertilizers to compensate for lost intakes of silt, and the newly established industry close to the power plant. In France, the Rhône was the heart of a vast national energy independence program. It was completely transformed by hydroelectric equipment. The Compagnie Nationale du Rhône, CNR, one of the prominent electricity companies in France, was established in 1933, and its first major achievement, the Jarrige Dam, began generating power in 1948. However, the joint constitution of the chemistry corridor south of Lyon, the physical alteration of the water's course, the modification of its flow, and barriers that curtailed the movement of fish and sediment, all added to local pollution, which was denounced by various environmental movements in the 1960s and 1970s. One such group was the Association in Defense of Nature and the Fight Against Pollution in the Rhône Valley, which opposed and tried to impede large-scale projects by the CNR. This association, founded by Camille Vallon, senator for the French Communist Party and mayor of the Givers Commune, near Lyon, shed light on the ambivalence surrounding hydroelectricity. Hydroelectricity was a paradox, celebrated globally as a source of power but denounced locally as a source of nuisance. In the same spirit of technological power and energy independence, the civil nuclear power industry developed in a similar guise, promising unlimited and clean energy. Nuclear energy appeared after 1945 as a means of relaunching modernity out of the post-war ruins. As with all thermal power plants, nuclear fission created a water vapor, which turned a turbine connected to an alternator. The first experimental nuclear power station was created at the Idaho National Laboratory in the United States in 1951. It was quickly followed by commercial nuclear plants outside the United States, at Calder Hall in England in 1955, and Marcoule in the Rhône Valley in France in 1956. The push for nuclear energy accelerated after 1960. Global nuclear power surpassed around 1 gigawatt, GW, in 1960, and 100 gigawatts by 1980. Because of reassuring speeches and rhetoric, a framework of modernization, and other tools employed to render this exceptionally dangerous trajectory socially acceptable, the question of pollution emerged quite late in critical discourse and actions against the civil atom. Certainly, radioactive contamination was known in the science world. At the First International Congress of Radiology in 1925, the need to reduce and limit exposure to radiation was imperative, and the International X-ray and Radium Protection Committee was created in 1928. It provided details on acceptable limits of radiation dosage in 1934, the same year Marie Curie died from aplastic anemia, brought about by her exposure to radiation. After the Second World War, the International Commission on Radiological Protection, 1950, was responsible for specifying acceptable thresholds and studying the relationship between doses and their effects on health, flora, and fauna. As well, as part of the production of nuclear energy, radiation exposure also took place before and after the materials were used to create fission, in the uranium mines, far from production and consumption sites, and while managing and stockpiling nuclear waste. In addition, a thermal impact followed the release of hot water into local waterways, which could be harmful to flora and fauna. In the production phase, every nuclear power plant continually emitted radioactive and chemical effluent in liquid and gaseous forms in controlled quantities and within the framework of regulatory authorization for waste deemed acceptable by public authorities. But these limits were sometimes surpassed if there were accidents or incidents such as the 3 Mile Island accident in the United States in 1979. Health and environmental risks were only assessed after nuclear power plants were already in place. In France, diverse groups voiced fears over health risks for the workers in nuclear plants. Once Markel was operational, a French uranium miner remembered that the extraction of that mineral was not without its element of danger for the miners. One could not stop the rays that emerged from the mineral, nor the radon, a gas also coming from the mineral, from escaping or accomplishing their sinister work, death. At a Congress of the French Confederation of Christian Workers, CFTC, in 1957, a workers' delegate warned against the effects of radiation as well as the danger associated with the plant's unusable waste being absorbed into earth and water. Despite the fact that nuclear pollution was rendered invisible due to a lack of sensory stimulus and the fact that the mines were far removed from consumers, and that radioactivity released during the mining process was difficult to distinguish from natural levels in the mines, movements in opposition to nuclear pollution formed after 1968 and enjoyed considerable publicity. In Cherbourg, various groups came together to form a committee against atomic pollution at the main waste treatment center in Europe, which began operation in 1966 in Le Hague, at the end of the Cotentin Peninsula. In the 1970s, Friends of the Earth investigated the uranium mines in the Limousin and Morvan regions in France, and warned against extraction, which is the cause of significant, normal, as opposed to accidental, radioactive pollution, in particular for the miners. It was precisely at this time that the extraction of fuel and its local nuisances were increasingly pushed abroad. The Atomic Energy Commission, CEA, had its geologists locate prospective mining resources in Africa, Madagascar, Gabon, and Niger, where sizable deposits of uranium had been found in 1969 at Arlit in northern central Niger. Thus, environmental damage was confined to post-colonial peripheries, where fewer complaints were made, even if such damage and pollution was a significant source of environmental injustice. In the 60 years that separated the Great War and the oil crisis, the world functioned with an intensive and highly polluting energy model while dealing with a population explosion, the need for a development policy, and an ever-increasing hike in demand. New energy converters were developed, but these simply added to the list of energy possibilities, and their pollutants, rather than replacing former energy sources. The energy-consuming world of the 20th century was a world predicated on accumulation, which also extended to the range of pollutants it generated. Thus, while natural gas, diesel, and nuclear power produced new toxic effluents, the amount of coal consumed had never been higher, in spite of its apparent decline. The process also reflected a deep global imbalance. Northern countries, mainly industrialized and capitalist, who engaged in these new riskier and more polluting trajectories, essentially pillaged resources from countries in the global south. In 1974, the United States, which accounted for only 6% of the world's population, consumed 44% of the world's coal, 33% of its oil, and 63% of its natural gas. Next to these industrialized countries, who became ever more dependent on hydrocarbons, stood the other rural and agricultural regions in Africa, India, and China, where human and animal labor provided sufficient mechanical energy. In 1971, of the 15.7 million tractors in use in the world, only 7% of them were used in countries in the southern hemisphere. In these countries, draft animals and human strength remained the principal forces of labor and transporting goods, contributing little to the growing pollutions in the northern hemisphere, with its higher standards of living and societies infatuated with mass consumption. 9. Mass consumption, mass contamination. If the production of energy is generally conspicuous, noisy, and smelly, the act of consuming energy seems much more benign. During the 20th century, it became the norm for societies to symbolically and physically keep at some remove the nuisances, inconveniences, and risks generated by the increasing profusion of material goods. However, each product hid subtle pollutions incorporated into the heart of the production process, from the mine to final consumption. During the 20th century, between the extraction of materials and their use in the form of manufactured goods, the operations and stages of production became more complex. Goods incorporated more and more composite products, many of which, for the average consumer, were almost magical in their derivation, but also profoundly affected the environment and human health. Surreptitious and chronic, the pollutions of the consumer society that flourished in the post-war period also provoked rapid and serious problems. Thus, in the early 1950s in Minamata Bay, in southwest Japan, cats were seen dancing strangely and frenetically before suddenly dying. Shortly after, fishermen were afflicted with a comparable mysterious evil. It gradually became apparent that these unexplained deaths were due to releases from the Chiso petrochemical plant, which specialized in the manufacture of acetaldehyde, an organic chemical derived from ethylene, used in particular for the production of dyes and the synthesis of rubber, in high demand by the automotive industry. The plant was installed on the bay in 1907, and in 1932 it adopted mercury oxide as a catalyst for the synthesis of acetaldehyde. Mercurial compounds, 400 metric tons between 1932 and 1966, were added to the many other heavy metals released into the bay, which contaminated marine fauna, accumulated in the food chain, and poisoned the local populations. Once mercury poisoning was revealed as the source of the mysterious ailment, the scandal was immense. 900 directly attributable deaths were recorded between 1949 and 1965, and more than 10,000 patients were compensated. But these figures represent a minimum that obscured long-term neurological disorders and the diseases, which subsequently became known as Minamata disease, lasting effects over several generations. Figure 9.1. Who owns it, anyway? Drawing from Life, November 20, 1902. Symbol of mass consumption, from its inception the automobile provoked popular concern because of its noise, speed, and pollution. In this satirical drawing published in the American magazine Life in 1902, the artist depicts the feeling of loss of control that accompanied the appearance of the new fetish in the American way of life. In fact, it is difficult to identify 20th century pollutions not exacerbated by its advent. Materials that needed to be mass-produced, including rubber, plastics, and metals, resulted in blackened sites in many parts of the world. Based on the growth of carbon-based chemistry and petrochemistry, synthetic organic chemistry became more complex during the century and pushed the boundaries of technological advancements. With synthetic rubber and plastics, both derived from fossil fuels, and other carbon-based derivatives, the range of materials used to produce consumer goods, in addition to wood, glass, vegetable matter, and metals, increased sharply in the 20th century. Further, the global population explosion, 1.8 billion inhabitants in 1920, 4 billion in 1975, combined with rising standards of living, led to a dizzying increase in the demand for materials that ushered in the visible manifestations of the world's entry into the Anthropocene, or Great Acceleration, that some date back to the post-war period. In developed countries, the consumer society's attraction deeply reshaped the needs of individuals. In so doing, it also altered their ecological footprint. That is to say, consumer societies exerted new and greater pressures on natural resources and ecosystems. So-called mass consumption, linked to the strategies of industrial capitalism in search of new markets to absorb the increasing production capacities allowed by the turn to Taylorism, became a global phenomenon, even if it took on highly variable forms. On the demand side, the emergence of advertising, consumer credit, and the revolution in distribution chains amplified the potential for the dissemination of products and their impact on the environment. Be it transportation, food, housing, or recreation, the new synthetic lifestyles created waste and pollutions in increasing quantities. Contaminated life was embodied in a consumer society of which some iconic products, plastics, automobiles, aluminum objects, and pesticides, shed light on the change of scale in 20th century pollution. The American way of life. The 20th century witnessed the flourishing of consumer society. Admittedly, the system of objects, and the elites and bourgeoisie's consumer habits were already well established in Western cultures, and had been for several centuries. But, in the United States first, from the 1930s, Then in Europe and other prosperous areas of the post-war world, the consumerist way of life grew and the commercial tools to develop it became more defined and standardized. To respond to the economic crisis following the stock market crash of 1929, the US government adopted a policy of stimulating consumption, an important part of the New Deal. Around the same time, the British economist John Maynard Keynes wrote the General Theory of Employment, Interest and Money, 1936, which became the dominant theoretical work for demand-driven economic policies. Keynesian economic theory and American economic policy were both engaging with the rise in purchasing power. Especially after 1945, the rise of the welfare state provided the framework for many developed countries, which permitted access to this consumer society to unprecedented swaths of their populations. The entry into the consumerist frenzy took place early in the United States, where purchasing power increased by 60% between 1939 and 1944. After 1945, consumption was widely affirmed not only as the precondition for economic prosperity, but also for democracy and peace. In the land of the American way of life, a veritable consumer republic was reshaping the idea of happiness. But already, the problems of pollution transcended the ideological confrontations between the capitalist West and the Soviet bloc. American university studies drew parallels between the two worlds, and insisted that the communist world's environmental contaminations were no less severe, even if their ideologies were still supposedly resistant to liberal ideas of consumption. This desire for a growing number of objects and services was deliberately cultivated by states seeking peaceful social relations and by companies seeking profits, through the use of advertising, access to credit, and the valuation of macroeconomic indicators such as GDP. While savings, sobriety, and repair became obsolete values, even dangerous for the progress of nations, the frenetic consumption of products with limited lifetimes asserted itself as an imperative. Consuming became a patriotic duty and a fundamental freedom that profoundly reshaped political economy. During the Cold War, the promotion of the North American consumerist model in the world, including through the Marshall Plan, also aimed to stem the lure of communism by the enactment of a popular capitalism. Capitalism in the developed world promised a hopeful future and provided the stability of social compromise, which was supposed to end misery and shortages. The resulting prosperity and consumerism defined the celebrated Glorious 30, an expression coined in 1979 in an essay by the noted French economist Jean Forestier. In 1956, Boris Vian could sing his Complaint du Progrès, while Georges Perec triumphed with his 1965 novel Les Choses. Both served as testament to the eruption of objects into the affective lives and innermost experiences of individuals. But the triumph of mass consumption cannot be reduced to a global process of Americanization. Between the two world wars, in Europe as in Asia, there existed various national traditions mixing the call for austerity with the quest for material abundance. The entry into consumerism took variable paths, and ambivalence often dominated, between attraction for wealth and individualism on the one hand, and respect for frugality and community on the other. This phenomenon was observed in Nazi Germany as in post-war Japan. The triumph of mass consumption also coincided with the growing urbanization of societies. While on the eve of the Great War only 20% of the world's population was urban, nearly 40% was concentrated in cities in the 1970s, despite significant contrasts. In the developed West, the share of urban dwellers already exceeded 70%. In China and Africa, urban populations made up less than 25% of the total. Urbanization was linked to car travel, which in turn disrupted existing marketing practices. The centralization of commodification led to the creation of supermarkets, then hypermarkets, or superstores, more than 2,500 square meters of floor space, a model born in the United States in the 1930s which then spread to Europe. The first French hypermarket opened in the suburbs of Paris in 1963. In 1970, however, supermarkets and hypermarkets still accounted for only 6.2% of retail sales in France. Mass consumption, socially very differentiated, but universally buoyed by the feeling of emancipation by objects, was a major source of pollution, because new consumerist lifestyles imposed strains on energy, materials, and toxic products. Take the example of leather, a very old material, but whose high global consumption reconfigured production. After the discovery of a new potential chrome tanning process based on a chemical treatment by Friedrich Knapp of Germany in 1858, industrial applications began in 1884 under the impetus of August Schultz, another German chemist established in New York, who worked for an importer of artificial dyes. Major changes appeared at the beginning of the 20th century. After millennia of vegetable tanning, the entire industry converted to chrome tanning in 50 years. At the end of the 20th century, 85% of world leather production was manufactured using this method. Chrome tanning was perfectly adapted for the consumer society, since the speed of manufacture was improved by a factor of 30 a day instead of a month. In addition, the leather was sufficiently inert, allowing it to be transported over long distances. However, chrome tanning is particularly toxic. Though the chromium salt that is used does not present a health or environmental hazard, it can oxidize during the production process or the incineration of leathers. The resulting, hexavalent, chromium, is a true poison. It was commonly released into the environment by many tanneries and was also present in some leathers. In particular, it became a scourge in India, the main country of leather production after 1945, for both workers and residents. The post-war consumerist revolution produced a lot of waste, but, paradoxically, it promoted a cult of cleanliness and personal hygiene, activated by advertising propaganda aimed at women. Electric home appliance equipment was synonymous with liberation and progress. By the 1930s, 50% of American homes were already equipped with vacuum cleaners and washing machines. Only 8.4% of French households had the same appliances in 1954. 20 years later, however, that percentage had increased to 66.4%. The cult of cleanliness insisted that these appliances were necessities. Modern living demanded tools to clean homes, kill bacteria, and remove substances dangerous to health. Indeed, along with other new home appliances, they became symbols of modernity. The post-war period was also the heyday of industrial design. Objects were redesigned to hide their inner workings while suggesting efficiency and cleanliness. As for detergent, it became iconic, while hygiene and beauty products enjoyed massive growth. Ironically enough, a gigantic increase in urban waste stemmed from more disposable products and the obsession with packaging, which were invented in the name of hygiene. The relationship with objects changed dramatically. Ephemeral consumption, even programmed obsolescence, as theorized in the 1930s by the promoter Bernard London in the United States in order to stimulate the production cycle, became a common and preferred approach. In his 1932 novel, Brave New World, Aldous Huxley already anticipated this new disposable consumerist imaginary through the slogan, "Ending is better than mending," or, "The more stitches, the less riches." The case of nylon stockings is a good example. As a synthetic product invented by the chemistry company DuPont de Nemours in the 1940s, nylon was hugely successful. But its strength caused a stagnation of sales. The original formula for nylon was subsequently revised, voluntarily decreasing the strength of the fiber to weaken stockings and force consumers to buy more. The light bulb was another symbol of planned obsolescence, whose lifetime was deliberately shortened from 2,500 hours to 1,000 hours by the Phoebus cartel of American light bulb manufacturers, created in 1924. Even before computing and electronics, consumer society embraced the logic of disposable and replaceable goods and their spiral of waste. As early as 1925, the American economist Stuart Chase described this phenomenon in his book The Tragedy of Waste, and 10 years later the historian Lewis Mumford denounced its mechanisms. During the Glorious 30, planned obsolescence spread in many sectors, encouraged by designers such as Brooke Stevens. But it was equally criticized by economists such as John Kenneth Galbraith, The Affluent Society, 1958, and journalists like Vance Packard, The Wastemakers, 1960. The decoupling of sites of production, subjected to direct pollution, from sanitized sites of consumption rendered almost imperceptible to the public the increase in emissions of toxic substances in the environment. Yet, the extent of the waste produced by this mass and disposable consumption quickly emerged as a problem. Even if the installation of new reprocessing plants and sewer systems, more expensive and more technically advanced, to be sure, relocated nuisances and made it possible to clean up some cities, particularly in developed countries, the spiral of waste was incessant. Though new waste management methods mitigated some of the problem, urban society's rapacious appetite for goods demanded ever more artificial products. The quantity of waste produced ballooned. Where efficient infrastructure existed, garbage was collected and dumped elsewhere, just like in New York City, which in 1948 opened a gigantic landfill on Staten Island. It received thousands of metric tons of waste every day and became the largest landfill in the world. Management methods varied in different countries. Japan seems to have deployed considerable ingenuity in recycling urban waste, repurposing it, in some cases, as building materials. On the other hand, in many megacities in the global south, waste management became a source of increasing contamination. For example, in the 1950s, Mexico City produced 3,000 metric tons of garbage per day. The thrall of the consumerist movement left little room for environmental dissent. In the 1960s in France, some trade unionists, such as Fredo Crumnow of the French Democratic Confederation of Labour, CFDT, denounced the waste civilization. In the United States, the first Earth Day in April 1970 drew attention to this problem. The model of frenetic consumption was contested by activists who challenged the nuisances provoked by the American way of life. Yet these oppositions failed to radically transform the bounds of the debate. For the most part, they remained outside of mainstream discourse and marginalized by the addictive attraction of access to new goods. By the end of this period of rapid growth, humanity's ecological footprint had exceeded the planet's carrying capacity. That strain on the Earth's biocapacity was calculated retrospectively. It was an indicator born from the Rio Conference in 1992 and has since been calculated by the Global Footprint Network. It measures the amount of space needed to produce the goods and services consumed, regenerate resources, and absorb waste, including the carbon dioxide derived from these activities. With regard to the environmental footprint, it assesses the impacts of a product type or organization. Another approach, virtual water, focuses on the consumption of water needed to produce each good or each food. It shows that demands on water increased proportionately more than aggregate consumption, because consumption structure changes with the addition of new products that use greater amounts of water. As noted by Jacques Thys in the early 1980s, each growth point seems to become more toxic. Traditional industries, based on natural materials, declined in favor of composite and synthetic products that were subject to multiple operations and resulted in many intermediate wastes. As a result, quantities of very bulky but low-polluting waste, such as ash or inert organic matter, stagnated or decreased, while the most dangerous forms of waste, be it nuclear waste or the chemical industry's production of long-lasting plastics or hydrocarbons, tended to grow. For example, a study of Wellington's ecological footprint in New Zealand between the 1950s and the early 2000s showed that food production quantities had changed little. Meanwhile, transportation, habitat, and consumption of manufactured goods and services all rose sharply. It should also be noted that these ecological footprints, which are often calculated on average, depend on consumption practices, so they are extremely diverse in the world according to social groups and regions. The decades of strong growth in the middle of the century deepened inequalities and disparities in the amount of waste between North and South, between richer and poorer populations. The plastification of the world. In this consumer society, carbon and petrochemistry profoundly transformed the material foundations of life. Already initiated at the end of the 19th century, the synthesis of new materials expanded during the interwar period. Though oil offered some competition, coal was still king. Industrialists and engineers continued to marvel at the mineral's potential to create a vast array of products. In 1930, during the Liege World Exhibition, a radiating diagram synthesized the omniscient power of coal's byproducts. Figure 9.2. L.S. Lowry, Industrial Landscape. Tate Museum, London, 1955. This oil on canvas is typical of urban scenes painted by the British artist L.S. Lowry, 1887–1976, during his career. Despite being an imaginary composition, the painting is punctuated by real elements that give the idea of an urban environment dominated by factories and chimneys spewing their smoke. This was typical of the imagination of the previous decades. The foreground acts as an invitation to enter this terrifying world. The quantity of synthetic chemicals released into the environment increased in order to meet the demand for new materials for clothing, housing, construction, transportation, recreation, and agricultural production. According to DuPont's famous 1935 slogan, "Better things for better living," through chemistry, chemical expansion was designed to preserve nature by decreasing demands on biomass and offering substitutes for rare or expensive natural materials such as silk, ivory, or rubber. Despite uncertain estimates, about 10 million chemical compounds were synthesized during the 20th century, of which 150,000 acquired commercial applications. But after 1945, oil reigned supreme in the design of new materials, spurred by a full range of plastics, with properties considered miraculous. Roland Barthes analyzed the new plastics craze in his 1957 classic Mythologies. At the far reaches of these transformations, man measures his power, The very itinerary of plastic gives him the euphoria of a prestigious freewheeling through nature. The hierarchy of substances is abolished, a single one replaces them all, the whole world can be plasticized, and even life itself. After the first polymer synthesis derived from hydrocarbons in 1910, Bakelite, the first plastic, was produced on an industrial scale until the 1950s. The interwar period experienced an explosion of research and patents on plastics and synthetic rubbers, in Hitler's Germany as in the United States and the USSR. This resulted in the universal spread of polyvinyl chloride, PVC, industrialized production of which its German creator IG Farben launched as early as the 1930s. Its cost-effectiveness and properties, such as being light and waterproof, ensured its wide distribution. PVC production began in 1933 in the United States, by Union Carbide. Annual production multiplied 120 times during the Second World War, to reach 160,000 metric tons in 1952, then 2.7 million metric tons in 1973. The two world wars stimulated investment. During the Second World War, DuPont marketed the nylon stockings which would subsequently invade the world. The first commercial patent for plexiglass, which was transparent, smooth, resistant, and lightweight, was filed in 1948. Chemists from BASF and Dow Chemical developed polystyrene manufacturing, which was used for packaging, coffee cups, noise barriers along roadways, and housing insulation. Enumerating the long list of these plastic products is an almost interminable venture. In 1935 polyethylene, plastic bags, appeared. In 1937 polyurethanes, paints, varnishes. In 1938, polytetrafluoroethylene, which in 1945 became known by the commercial name of Teflon and was soon used as a frying pan coating and then for countless other uses. In 1954 polypropylene, bumpers and car dashboards. In the music industry, naturally derived shellacs were replaced by chlorinated vinyl polymers to make records. After 1945, the American record industry invented the microgroove and the now famous vinyl record became a worldwide success. Viscose, or artificial silk, or rayon, patented at the end of the 19th century, is one of those plastic products that grew in popularity after 1918. Derived from cellulose treated with various chemical substances, its manufacture required the use of toxic materials and the emission of large quantities of pollutants. In 1930, 2,000 kilograms of soda, 1,500 kilograms of sulfuric acid, and 550 kilograms of carbon disulfide, CS2, produced from coal, were needed to make 1,000 kilograms of viscose. The adoption of viscose manufacturing initially experienced strong resistance from the silk industry surrounding Lyon. In 1920, it represented less than 5% of overall production. But afterwards the bulk of the city's principal silk producers embraced this material, in particular, the Gillette Company, which built an industrial empire at the juncture of textiles and chemistry. Other viscose plants also opened in the United Kingdom, near Coventry, and in Italy, Japan, and the United States. Viscose production remained controversial for a long time. The hazards of carbon disulfide to workers were documented early on in the medical literature and social surveys. A report from the 1922 Labor Inspectorate in France and Alice Hamilton's investigations in the United States described cases of poisoning in these factories. In England, local residents also complained about air pollution and carbon disulfide emissions, but the authorities dismissed the dangers. Industrialists provided financial compensation to quell dissent. In the 1930s, manufacturing conditions were even worse in fascist Italy and Nazi Germany. Workers and residents were victims of very toxic waste, but the location of the factories and the exploitation of a quasi-servile workforce prevented any curbing of polluting production practices. After 1945, taking advantage of cheap energy and unprecedented demand for materials considered modern meant rewarding the standardization of processes and the triumph of mass production. Plastics became virtual necessities. In West Germany, for example, the consumption of plastic rose from 1.9 kilograms per capita in 1950 to 15 kilograms in 1960. But these new substances were also responsible for very different types of pollution, both in their manufacture in large petrochemical plants using hydrocarbons, and at their final point of consumption where a considerable amount were then abandoned in soils, rivers, and oceans. Petrochemical complexes, located near oil and natural gas deposits, first developed in the United States and Europe before expanding into third world countries beginning in the 1960s. The expansion of petrochemical corridors, significantly called cancer alleys in the United States, precipitated expansion of pollutions, especially surrounding vinyl chloride manufacture. Many cities and communities had their water and air contaminated by the plastics industry. This was especially the case along the lower Mississippi River. In France, the first large petrochemical plant was opened at L'Estaque near Marseille in 1949–1950. 10 years later, another 50 had already spread around oil refineries, Lower Seine and Étang de Berre, south of Lyon, and places of natural gas production like Lac. As in the United States, the plants produced many plastic products but also fertilizers. They were also responsible for significant environmental contamination and abnormal cancer rates. South of Lyon, for example, the imperatives of industrialization led to the acceptance of these nuisances, which were relocated to peri-urban and working-class communities. In 1964, the opening of the vast modern refinery of Faisin inaugurated a chemical corridor in St. Fons. 2 years later, a tragic explosion at this refinery fostered debate on industrial risks and their pollutions. The entire history of the 20th century petrochemical industry is predicated on chemists' efforts to imitate and improve upon nature's materials while being confronted with the excesses of their own practices. The new age of chemistry aroused the doubts of researchers such as Pierre Beranger, holder of the chair of chemistry at the École Polytechnique from 1949. In a synthesis on the subject published in 1956, he observed that plastics are only pale imitations of the admirable natural substances, their success being especially due to the deep and unconscious tendency of man to do without nature and to adore himself through his own creations in the center of an ersatz pantheon. Beranger also denounced the frenetic and unthinking squandering of fossil raw materials to obtain that pantheon of new creations. At the turn of the 1960s and 1970s, concerns about plastics were redefined as a public health issue and a source of major pollution. Modern society had to reckon with the fact that plastics were very difficult to recycle and that their degradation, which also contaminated the environment, was particularly slow, several hundred years in general. In addition, the microparticles derived from it were ingested by a large fringe of the marine biotope. Among hundreds of letters sent to the German Interior Minister in the course of an investigation into environmental issues, 70 blamed plastics and their waste as the main source of pollution, while a petition that collected hundreds of signatures in May 1971 protested against ever-increasing pollution of the environment and the deterioration of the living conditions of humans, animals, and plants due to automobile emissions, industrial waste, and the multiple non-degradable wastes of our affluent society, packaging or plastic bottles. In 1970, the American architect and designer Paul Mahon also asserted that industry should stop producing products with such high pollution potential, and especially to strive toward developing plastics with high reconversion potential. Finally, although the issue of waste was generally muted, with few studies before the 1980s on environmental contamination by plastics, two American biologists, Edward Carpenter and Kenneth Smith, raised the alarm by revealing the presence of high concentrations of synthetic polymer particles in the sea off Florida in 1972. The following year, the oceanographer Elizabeth Venrick reported the same finding north of Hawaii. It is impossible to be wholly comprehensive in recounting the number, variety, and quantity of the new petrochemical synthetic products that were assimilated with the plastics heretofore discussed. But it is necessary to acknowledge the scale of their significance. As an illustrative example, it is useful to focus on polychlorinated biphenyls, PCBs, synthesized at the beginning of the century and used for its dielectric properties and thermal conduction as electrical insulation in transformers, but also in capacitors, hydraulic fluids, paints, adhesives, and other applications. Their growth was due mainly to the Monsanto company, which became the main producer after 1929, before production spread to Europe after 1945. Although Monsanto was aware of their toxicity as early as 1937, the company's main production site in Anniston, Alabama became highly contaminated. PCBs were used extensively until the 1980s and caused widespread pollution. As a persistent organic pollutant, it was indeed a hypertoxic threat to human health and the environment. Before 1975, the Hudson River near New York City, and the area around Bloomington, Indiana, paid a heavy environmental cost for PCB production, but that was ultimately the case at all production sites, before their release and dissemination affected the entire planet to varying degrees. Figure 9.3. Global Plastic Production, 1950 to 2010. Source: Plastics Europe, Plastics, The Facts, 2013, an analysis of European latest plastics production, demand and waste data. 10. Automania, supreme fetish chemistries, plastics and new synthetic substances infiltrated all everyday objects, first and foremost the totem of consumer society, the automobile. It is difficult today to grasp the full effect of the automotive revolution and the shock that it caused its contemporaries. After lamenting the sound and smell of these machines, the old narrator of the life of a simple man remarked sadly in the early years of the 20th century that these motor cars really are the instruments of the devil, invading the roads, upsetting us and doing us mischief. A man from a bygone age, a grandfather shaking his head, it is not for me to pass judgment on that subject. The young people will get used to these vehicles of progress. 50 years later, in his mythologies, Barthes noted the cult of the car. I think that cars today are almost the exact equivalent of the great Gothic cathedrals. I mean the supreme creation of an era, conceived with passion by unknown artists, and consumed in image if not in usage by a whole population which appropriates them as a purely magical object. Symbol of individualism, status indicator, chasm of fuels and materials, cult object, consumerist fetish, the car dethroned the railroad in the order of fast mobilities. It also served as the medium through which humanity slipped toward a chronic acceptance of risk and pollution. A socially differentiated acceptance, it is worth stressing. While large engines offered their owners more safety, while emitting more polluting substances, traffic was relegated to the fringes of urban areas. In addition to the toxic dust from fuels, cars rapidly became the source of very serious environmental degradation and multiple contaminations due to chemical additives in fuel, tire manufacture and disposal, the production of composite materials, and the gigantic infrastructures necessary for their mobility. For the automotive system to become fully entrenched, it was first necessary to create a favorable environment. For starters, in the 1920s and 1930s, it chased trams from all cities that had them. Behind the scenes, the oil and automotive lobbies pushed for the supremacy of the private car in major cities all over the world. France became a pioneer in this shift toward the automobile. The network of tramways in Paris, at the time, the largest in the world, was removed in the 1930s. The inner city line removal was followed by the closing of lines in its suburbs. Trams were replaced by Renault buses. In the decades that followed, all the other provincial cities carried out the same process. In the United States, where tramway equipment was extensive, large automobile and oil consortia also exerted a major influence. As early as 1922, the head of General Motors set up a working group whose mission was to design a strategy to replace electric streetcars with buses and then cars. In 1935, Congress passed a law prohibiting energy companies from owning streetcar companies. This act encouraged their buyout by General Motors, who subsequently allowed their infrastructure to deteriorate. 2 years later, the 150 kilometers of Manhattan tramway tracks were removed. General Motors was also, in one way or another, involved in the dismantling of more than 100 streetcar networks in 45 cities, including New York, Philadelphia, St. Louis, and Los Angeles. In April 1949, a federal jury found General Motors guilty of conspiring with Standard Oil and Firestone Tire, but the damage had been done. The tram networks were not coming back, the car had taken their place. Buoyed by a powerful imaginary, the car was part of a huge technical ecosystem that shaped new desires and new landscapes. Automotive infrastructure became a second nature that inspired the invention of a world adapted to its measure, with the expansion of highways and the new urban forms that accompanied them. The highway was initially a concept of fascist regimes. The first section was inaugurated in Mussolini's Italy between Milan and Varese, 80 kilometers, in 1924. Then, shortly after the rise of the Nazi Party in 1933, the first major German motorway projects were launched. These Autobahnen provided jobs, economic recovery, and strengthened the country's centralism. They also facilitated the rapid movement of troops in anticipation of the war. Major instruments of Hitler's propaganda, they demonstrated the capacity of the new man to tame nature. On the same principle, these gigantic infrastructures were built in the United States during the Cold War. Under President Dwight Eisenhower in the 1950s, the construction of the interstate highway system cost more than $100 billion. In France, the Gaullist regime launched a similar movement by adopting in 1960 an ambitious master plan for the development of a road network that provided for the construction of nearly 2,000 kilometers of motorways before 1975. In cities, the priority given to car traffic burst a tenuous urban equilibrium,
cars promoted ever more sprawling suburban enclaves. Los Angeles became the emblematic case. The city grew from 1.6 million to 6 million inhabitants between 1930 and 1960, devouring space and requiring incredible quantities of energy as it spread spectacularly and tentacularly. The new urban-suburban landscapes had a considerable environmental impact. Tons of asphalt, from petrochemicals, were poured to build roads so that cars could carry citizens between urban work and ever more distant suburban homes. Systematized Taylorism in the factory plant, built on automation and efficiency, meant that the automobile also revolutionized workspaces and production methods. In the 1920s, Henry Ford developed the famous Model T with the first assembly lines. To control the production process, in 1928 Ford opened the largest factory in the world in Detroit, Michigan, on the banks of the Red River. As early as the 1930s, 80,000 employees produced 10,000 vehicles a day. Unlike other car manufacturers who spread the nuisances of their activity among many dispersed factories and suppliers, this integration strategy led to focused environmental impacts at the same site, making pollution particularly visible and palpable. In anticipation of this problem, the plant was equipped with methods of treating solid, gaseous, and liquid waste. Ford's waste management system followed the logic inherited from the 19th century. Unwanted waste was diluted and released into the environment, along the Red River. The main criterion guiding the treatment of toxic and polluting waste was financial profitability. After 1930, the world's leading automakers followed this pattern of concentration in large factories, and the trend became stronger after the war. Cars are assembled from so many diverse materials, many of them modified or substituted in and out over time, that it is impossible to list them. While iron and steel made up nearly 75% of the weight of the first Ford Model T, the range of metals diversified over the following century to such an extent that one might assert that hardly any metal was not used in automotive manufacturing. In the first environmental history of automania in the 20th century, Tom McCarthy drew a very complete picture of the controversies and many pollutions associated with the automobile at each stage of its life cycle. Heavy metals, in particular, became increasingly critical. In post-war Japan, the cadmium spilled by Mitsubishi manufacturers in the Jinzu River caused a terrible bone disease, while the increase in sulfur dioxide emissions in the heart of cities exacerbated respiratory ailments. For their part, plastics gradually became primordial materials. As early as 1936, at the Berlin Motor Show, the chemical company IG Farben introduced a new kind of synthetic rubber for tires, manufactured at its Saxony plants. The overconcentration on the atmospheric pollution of fuel emissions means that studies on the environmental impact of cars too often forget the considerable quantity of materials required for their production, the various solvents needed for their maintenance, and the waste that results, as well as the design of more and more composite and synthetic products, for dashboards, brakes, bumpers, bodywork, and so on. It is possible to get an idea of the breadth of these pollutions by drawing on a representative example of one of these composite and synthetic accessories, tires. Initially, tires were made of rubber cultivated from Hevea brasiliensis, the tropical rubber tree. The first car to run on pneumatic tires was designed by Édouard Michelin in 1895. Its production was itself a source of major pollution, given the vulcanization process designed in the 19th century. 10 times more watertight than rubber, butyl, a synthetic elastomer, was adopted in the early 20th century for inner tubes and membranes of tires, which incorporated chlorine to promote chemical bonds with the rubber. Production industrialized in the 1930s, DuPont invented neoprene, based on polychloroprene, the first real synthetic rubber. Neoprene was mythologized in popular culture after the actress Claudine Auger, a former Miss France, wore a revealing synthetic wetsuit in 1965 in the fourth James Bond film, Thunderball. After the war, tire materials diversified, sulfur, oils, and the very toxic carbon black were added, along with various braided metals, zinc, cadmium, to improve their resistance. In addition to the pollution generated in composite rubber's production, it is also necessary to add those of the daily abrasive wear with the road, which released a volume of fine particles probably as important as the fuels. These microscopic residues massively contaminated oceans. Finally, tires came to constitute the archetype of waste that befuddled waste management. In the early 1970s, piles of millions of tires in landfills posed insoluble problems. They were difficult to recycle, their quantity was enormous, and fumes from their incineration were very harmful. Incineration was initially quite popular, but it was gradually regulated.
Official initiatives were subsequently taken to throw tires into the sea. In 1972, 2 million used tires were dumped a mile off the Florida coast near Fort Lauderdale. The rationale for dumping tires at sea was grounded in environmental interests. The scheme aimed to create artificial reefs for marine life. Out of sight, out of mind. This invisible clearance of cumbersome toxic waste was copied in France, where 90,000 cubic meters of used tires were immersed in the Mediterranean Sea. Similarly, Portugal, Spain, and Italy followed suit. Japan laid claim to world champion status in this regard, dumping 20 million cubic meters of tires at sea. The cost of operations, as is often the case for pollution, was passed along to following generations. Unsurprisingly, the environmental damage of the enterprise was considerable. Future generations were forced to extract the tires from the sea at considerable expense. Many chemical additives were also incorporated into the operation of the automobile. Predictably, as with most automotive innovations, their origin was the United States. Starting in 1922, leaded gasoline constituted the ultimate automotive plague. General Motors added tetraethyl lead to improve engine performance. Although workers were poisoned during its manufacture and regulators prohibited its use for a year in 1925, time enough to confirm its transgressions, powerful lobbying interests eventually impelled lead's inclusion in gasoline. Tetraethyl lead's benefits to the automotive industry and to the economy were sacrosanct. The Kettering Lab, founded in 1930, was responsible for evaluating the product. The work, under the direction of the toxicologist Robert Keogh, was funded by General Motors, DuPont, and the Ethyl Gasoline Corporation. Keogh claimed tetraethyl lead's hazard was innocuous. His argument, that the burden of proof rested on determining the severity of a hazard rather than proving its safety, that demonstrable economic benefits should always outweigh unproven risks, delayed action on lead for several decades. Lead's toxicity was a real concern, and against Keogh's principle, several independent laboratories demonstrated it over the following years. Eventually concerns prevailed. In the early 1970s, gradual bans on leaded gasoline were introduced. But for half a century, the spread of lead in the environment resulted in one of the most significant cases of widespread pollution, found as far away as Arctic ice samples. Lead poisoning also heavily affected people living near road infrastructure. At the turn of the 1970s, the automobile increasingly became associated with the concept of pollution. Its omnipresence raised mainstream questions and doubts, even strong criticism. For the first time, televised reports were devoted to this question. On October 6, 1973, for example, on the occasion of the inauguration of the Paris Motor Show, a 15-minute report was broadcast on French television, in which the Deputy Director of Pollution and Nuisance Prevention at the Ministry of Quality of Life, 1973-1976, discussed technical solutions to reduce nuisances, and the engineer Gabriel Bouletin, head of the Department of Engineering of the Geneva Institute Batel, considered the automobile a pure anachronism in contemporary city life. The following year, the comic book Les Mange Bitumes, The Bitumen Eaters, presented a vast cautionary futuristic fable about the worst of all possible worlds. In this highly exaggerated mechanized future, people essentially live in their cars and consumerist obligations overlap with totalitarian social control. Humans mutate into drivers and leaders conceive of a society where traffic jams become a way of life. That year, 39 million vehicles were produced worldwide, compared with 4 million in 1946. But, contrary to what the emergence of these criticisms might suggest, and despite the oil shocks of the 1970s, automotive appetites continued to grow unabated. Production exceeded 50 million at the end of the century. Light metals, heavy impact. The mass production of manufactured goods, like the car, the weight of which was constantly growing, required huge quantities of metals. In addition to steel compounds, the exploitation of copper, lead, zinc, or light metal, aluminum, experienced significant growth over the 20th century, considerably exacerbating pre-existing nuisances and pollutions. For example, world copper mining grew from 400,000 metric tons in 1900 to 10 million metric tons a century later. As with most non-ferrous metals, that production was extracted from increasingly poor deposits. In 1800, English ore contained more than 9% copper, and 6% in 1880. But the veins were depleting. American ore contained 3% copper in 1880, 2% in 1930, and 1% in 1975. In comparison, demand was going up. This decline meant that in order to extract the pure metal, more aggressive means had to be found and even larger quantities of ore needed to be mined per unit produced. In ever larger mines, the productive geography changed. Copper deposits in the Belgian Congo and Zambia, and especially Chile, a copper giant since the 1920s, played a growing part. In 1970, Chile led the world in copper production, thanks to the Anaconda Copper Company, located in the Chuquicamata mine in the Atacama Desert since 1922. Production reached 130,000 tons in 1929. The United States retained an important role. For example, the giant open-pit mine at Bingham, Utah, opened in 1906 by Rio Tinto, became the world's first copper refining complex in 1912. During the following decades, large areas around it were contaminated with copper, arsenic, and lead. The environment was devastated by sulfurous gases. The same was true in Montana, around the Washoe mine, operated by the Anaconda Copper Company, CF. I.G.U.R.E. 101. Closing parenthesis. These giant mines initiated a novel kind of mass destruction, which also occurred around smaller mines. For example, a dramatic collapse of aquatic life and a general contamination of the environment occurred in just a few years of operation, 1964-1966, at the relatively small, 13 hectares, or about 32 acres, Mount Washington copper mine on the Solom River on Vancouver Island. The ore's decline in metal content necessitated new refining processes in the early 20th century. The Manhas David, 1880, and Pierce Smith, 1908, processes, which used a converter to oxidize undesirable chemical elements with air, were used throughout the century. In addition to these pyrometallurgical processes, a hydrometallurgical method was developed, which dissolved sulfides by watering the ore with sulfuric acid, cyanide, or ammonia. As a general rule, despite the use of filters, the sulfurous fumes, also loaded with zinc oxides, arsenic, and lead, were significant. The converter remained the main problem, because it was difficult to seal and its intermittent operation disrupted flue gas treatment installations. As a result, the copper industrial complexes were distinguished by chimneys that beat height records. In Washoe, a 178-meter chimney was built in 1918. It emitted more than 100,000 cubic meters of smoke per minute. The smoke was collected and traveled in pipes, sometimes for several kilometers, in which the particles were supposed to be deposited. See Phi. I.G.U.R.E. 101. Closing parenthesis. For the most part, regulations were almost non-existent before the 1980s, because of the relative isolation of these mines, especially in emerging countries. Because mining zinc and nickel required similar techniques to copper, soil and water contamination and the emission of toxic dusts, loaded with sulfur and arsenic, lead, and other heavy metals, were also common features of their extraction process. In addition to prominent disasters in the Meuse Valley in Belgium, 1930, and in Donora, Pennsylvania, 1948, where waves of toxic smog from the smelters killed numerous local inhabitants, zinc refining caused chronic pollution wherever it was practiced. The primary pollutant was cadmium. The Broken Hill mine in the remote outback of New South Wales, Australia, became the capital of zinc extraction in the 20th century. While nickel was hardly exploited before 1900, it enjoyed increased industrial use in fine and resistant alloys. The 20th century's arms race, in particular, fueled its development. New Caledonia has long been one of the world's major centers and reserves of nickel production. It was joined in the 1920s by Canada, Russia, and South Africa, and after World War II, by Australia and the Philippines. In the gold and silver mines that dotted the African continent, cyanide residues, which replaced mercury as the refining technology of choice for precious metals after 1887, devastated landscapes for many generations. But if there was an iconic metal of the 20th century, it was aluminum. Its production experienced the greatest increases over the course of the century, and it better typified the advent of consumer society and its new contaminations. Aluminum was originally a luxury metal before it became one of the most consumed metals in the world, beginning in the 1960s. It was widely touted as a miraculous product with seemingly infinite commercial possibilities, lauded in advertising catalogs and exhibitions, promoted by contests and in specialized magazines. In France, the periodical Revue de l'Aluminium was created in 1924 and ran until 1983. Aluminum provided another example of stimulated wartime production initiatives seeking post-war consumer outlets. It became the symbol of mass consumption of the post-war period. Gradually, it was also used as a food additive. The harmful effects of this new everyday material were generally ignored by a powerful industrial sector that was concentrated and organized in cartels, and by the state, which supported its development. The dominant buyer process extracted alumina from bauxite with soda, but it produced toxic waste that contained caustic soda and heavy metals, lead, mercury, chromium, called red mud, because of its color that came from high iron oxide content. Once extracted, the alumina was converted into aluminum in large plants through extremely energy-intensive electrolytic processes. This conversion stage created significant air pollution. Before the 1970s, 30 to 60 kilograms of fluorite were emitted for every metric ton of aluminum produced. In the Alpine valleys, the legacy of pollution inherited from the turn of the 20th century persisted, despite continued contention and very strong litigation. Near the big factory of Saint-Jean-de-Maurienne, opened in 1904, a report of the Hygiene Council, 1908, noted deforestation, the death of bees, and workers' health risks as problems. Farmers organized themselves into unions and received renegotiated benefits each year according to the amount of livestock affected due to the pollutions. Similarly, in Switzerland, peasants close to the Martigny plant blamed emissions of fluorine for the decline in their vegetable crops. In Italy, the Italian aluminum company, SIDA, Società Italiana dell'Alluminio, founded in 1927 under the consolidating context of the Mussolini fascist regime, established a vast factory in Mori, a small village in the province of Trento. Shortly after, local silkworms began to die, tens of thousands of people became victims of fluorite fumes, and pollutants spread over 4,000 hectares, about 9,900 acres. In 1932, a committee of locals confronted industrialists, who adopted a wait-and-see mentality, and the state, who simply paid compensation for damages to locals. Unimpressed, these inhabitants rose up in 1933. The factory was temporarily closed. Engineers traveled to France to study filtering techniques, while children from the surrounding villages were sent to homes beyond the range of the pollutions, and the company engaged in a massive propaganda campaign that denied links between plant activity and local health problems. When the factory reopened in 1935, the context had changed. The rise of international tensions and the march to war pushed the Mussolini regime to strongly repress the disputes. The United States reinforced its advantageous territorial and resource capacities in the interwar period. Spurred by the economic incentives provided by the New Deal and the war that followed, construction of major hydroelectric dams emboldened Alcoa, Aluminum Company of America, previously the Pittsburgh Reduction Company, and its industrial production. In Quebec, Alcoa, whose international holdings after 1928 were housed under a new company, Alcan, Aluminum Company of Canada, built a giant plant in 1925, the largest in the world. The plant required the construction of its own city, Arvida, named after the president of the company, Arthur Vining Davis. Urban planning was designed to stabilize the workforce entirely devoted to production, which explains why complaints about pollution were limited. In 1945, the plant produced nearly 500,000 metric tons of aluminum. The French aluminum example shows both uninterrupted growth after 1945 and the pollution problems that accompanied it. Production increased sevenfold between 1956 and 1972, from 160,000 to 1.14 million metric tons, often on sites away from the old industrial ones, near bauxite deposits and near access to hydroelectricity. In 1950, 85% of production was carried out far from major steel and coal mining centers. Aluminum's importance to the economy generated an agreement between the state, the industry, and the unions to limit opposition to the contaminations that became evident at the refineries, in surrounding vegetation, and among the alarming number of workers who contracted cancer. Companies also implemented paternalistic policies to ensure social peace and order in the factories. In the 1960s, the main bauxite processing complex in France, operated by Pechiney in Gardanne near Marseille, discharged a metric ton and a half of caustic residues for every metric ton of alumina produced. Huge amounts of red mud, stored in reservoirs, threatened to contaminate groundwater and soils. A pipeline, about 40 kilometers long, was built in 1966 to offload the sludge into the Mediterranean Sea. As ever an historical constant when waste is dumped at sea, fishermen and local authorities anxious to attract tourists protested. In the Maurienne Valley, fluorine air pollution from the aluminum smelting plants created tensions, especially because of the valley's depth, which trapped contaminants. The topography made the pollutants even more visible and intolerable, especially when the valley was also developing a tourism industry. In the 1950s and 1960s, as production increased to meet ongoing demand, the plant adopted an electrolytic process using so-called Soderberg tanks, which expelled fluorine in high amounts without taking effective measures to capture it before it escaped into the environment. Contamination thresholds of 40 ppm, parts per million, were greatly exceeded in some areas. In 1966, the National Forestry Office identified 10,000 hectares, about 24,700 acres, of affected forests. The contaminated area was 40 kilometers long. The aluminum company, Pecini, was forced to pay more than 4 million francs in annual compensation for a production of 99,000 metric tons. Widely covered by the major media and the emerging environmental press, the pollutions of the Maurienne, renamed Valley of Death, played a prominent part in the boom in environmental coverage by the media in the early 1970s. Fights backed by local environmental associations, and some unions such as the French Democratic Confederation of Labour, CFDT, emerged. An anti-pollution committee even appeared in the valley. Only in the context of stern opposition did manufacturers choose to invest in modernizing their facilities and significantly reducing emissions. Similar processes, oppositions forcing changes in production, with similar chronologies were common all over Europe, such as at the Martigny plant in Switzerland, for example. Figure 9.4. Global metal production in millions of metric tons, raw aluminum, unalloyed, refined copper, zinc, lead, source, derived from l'Annuaire statistique mondiale des minerais et métaux, CIM-ABRGM, as reproduced on the Société Chimique de France website. Green Revolution, grey soils. Like most economic sectors, agriculture became increasingly dependent on chemistry. Whereas before 1914 few chemical inputs were deemed useful, chemistry transformed Western agriculture after 1945, especially with fertilizers and biocides designed to fight against undesirable weeds and pests. In the 1970s, agricultural chemistry began to expand throughout the rest of the world. At the heart of this diffusion was a beautiful utopian idea: feeding a rapidly expanding world and eliminating famines and shortages by introducing food abundance. Green revolutions heralded this agricultural modernization, which constituted a transition from peasantry to agro-industry. The terminology was not neutral. It obscured the fact that the use of chemical inputs to amend soils, control crop pests, remove species considered invasive or harmful, and reduce uncertainty by standardizing landscapes and environments, contributed greatly to the contamination of soils, groundwater, and waterways. If the term insecticide in agriculture dates from 1838, it was replaced in the middle of the 20th century, 1959 in France, by the evocative term pesticide, which came from English. Though the term was readily adopted into French, it was curiously unsuitable, even if in hindsight it was curiously apt. In French, peste does not refer to parasite, but rather to an epidemic disease. In French, la peste translates as the plague. Subsequently, the term phytosanitary spread. Plant sanitation was a sufficiently neutral term. Phytosanitary products encompassed insecticides as well as herbicides around 1930 and fungicides 1912. Sanitation, as far as it was suggestive of scientific management, had little impact on the imagination. Insect, herb, and fungus killers, however, provoked other ideas. Between 1950 and 1985, global grain production increased 2.6 times. Though it was unevenly distributed, this explosion was only possible thanks to the massive use of chemical fertilizers, nitrogen, phosphoric acid, and potash, the famous NPK trio. Their application increased from 4 million to 17 million metric tons between 1900 and 1950, but then to 130 million metric tons by the end of the 1980s. Fertilizers were joined by a considerable increase in irrigation and the use of pesticides, the quantity of which was multiplied by 20 during the same period. The rise of petrochemicals played a major role in this change because the use of hydrocarbons made it possible to market new synthetic substances. The use of feed additives for livestock, such as acrylane, also deserves mention. A very toxic substance produced from a petroleum derivative, acrylane was used to produce a protein component for livestock called methionine. It was used in feed and in anticoccidials whose development permitted more intensive forms of poultry farming. Particularly in the United States and Great Britain, these innovations provided the context for a quantitative intensification of antibiotics that were used widely and on a massive scale in livestock farming. The use of chemical fertilizers and pesticides required that land be reorganized first. Old polycultures gave way to monocultures, and the number of farmers, who still represented half of the population in the United States in 1920, decreased drastically. Mechanization also played an important role. The spread of tractors, 300,000 worldwide in 1920, predominantly in the United States, increased to 3 million by 1940, 6 million a decade later, and 16 million by 1970. Modernization had a snowball effect. Since industrial monoculture was more susceptible to pests and soil nutrients declined more rapidly, the need for more pesticides and fertilizers established a vicious cycle to compensate for the problems of these new gray soils. The extent of agricultural chemical pollutions was derived, therefore, from these developments. Agricultural pollutions increased more quickly in the United States and Canada than in Europe, and faster in Europe than in the rest of the world. Prior to 1939, the United States had already experienced health scandals related to insecticides, especially from the use of arsenicals, but the Second World War ushered in a real turning point. As early as 1949, California farmers spread parathion. In 1951 they sprayed dimethan, malathion in 1953, and meticide in 1956. The danger of these organophosphorus products came from the action of an enzyme that disrupts the nervous system and causes heart problems and cancers. Among the main pesticides used after 1945, the famous DDT became prominent due to leftover stocks from the Second World War. Although the hazard of pesticides gradually emerged as a global political problem, and was addressed at the international level, much of the early information on this issue originally came from California in the 1950s-1960s, where it was first and foremost regarded as an occupational health concern. In 1949, in an incident near Marysville, 25 farm workers became ill after working in an orchard sprayed with parathion. The California State Department of Public Health then identified 300 cases of poisoning by agricultural chemicals. Geography and history combined to make California a major site for the production of fruits and vegetables. 50% of the country's oranges, and 100% of the olives, avocados, and apricots were produced there. The introduction of new species, accompanied by the introduction and proliferation of insects, pushed farmers toward chemical control of the environment. 20% of all pesticides used in the country were applied in California. The workforce, often made up of immigrant laborers, struggled to be heard, even though Mexican workers in California's orange groves conducted a death march in the 1950s to denounce their working conditions. Outside California, thousands of more or less serious chemical-related accidents also occurred between 1945 and 1970 among the African American workers of the cotton plantations of the southern states. In Europe, and especially in France after the liberation, the entire agricultural industry was in dire straits. Shortages persisted. The French government was forced to reinstitute wartime bread rations in 1946. In comparison, North American agriculture became a model of efficiency praised by agronomists such as René Dumont in his Leçons de l'agriculture américaine, 1949. Routine agriculture, Dumont warned, withdrawn into an autarkic and Malthusian position would ruin the entire country. French agriculture changed rapidly. The country saw a reduction of 1 million agricultural workers between 1946 and 1954, its share falling from 36% to 27% of the active population. The first plan of 1947, which relied on the American Marshall Plan funds, enabled the modernization of old practices and the widespread mechanization of agriculture. The number of tractors increased from 137,000 in 1950 to 558,000 in 1958 and 1 million around 1965, while the equipment for spraying the fields with pesticides spread. Initially, pesticides were applied through human and animal traction, but sprayers pulled by tractors followed. Within a few years, DDT and HCH, hexachlorocyclohexane, replaced the old arsenical products, arsenates of lime and alumina. Agricultural modernization and intensive use of chemical substances were especially beneficial to the larger farmers, while smaller farmholders were swept away. In France, Charles de Gaulle's rise to the presidency in 1958 further accelerated these changes. The creation, in 1960, of Land Development and Rural Settlement Corporations, SAFER, responsible for acquiring land, and the Common Agricultural Policy, CAP, of the European Economic Community, EEC, which entered into force in 1962, promoted the adoption of pesticides as a modernizing factor in production. The state's technical services, including the National Institute for Agricultural Research, INRA, 1946, encouraged the use of these products. So did the largest farmers' organizations, such as the National Federation of Agricultural Holders Unions, FNSEA, 1946, and the National Club of Young Farmers, CNJA, 1957. Jean Bustarrett, a specialist in hybridization and improvement of plant species, an inspector and then Director General of INRA from 1949 to 1972, was fascinated by the American example. He became an ardent promoter of pesticide products, launching first the National Federation for the Defense of Farming in 1956, and the Weed Control Committee, which included representatives of the industrial world, Pescini, for example, which in 1953 developed a weed killer for flax. The situation outside the Western world was quite different, because chemical products remained expensive and required more concentrated operations on smaller farm plots. As a result, their use was more limited. Beginning in 1953 in the USSR, Khrushchev initiated an ambitious plan to increase Soviet agricultural productivity and fight against undernourishment. Khrushchev's plan involved cultivating the Kazakh steppes, as well as parts of Siberia to extend cultivated areas from 9.7 million to 28.7 million hectares, about 24 million to 71 million acres, within a decade. The initiative failed due to soil erosion and the rapid degradation of soil fertility because of overexploitation. To compensate for this failure, the country began a rapid conversion to chemistry in the 1960s. The amount of chemical fertilizers produced tripled between 1965 and 1975, from 31 million to 90 million metric tons, placing the country at the head of world producers. Pesticides such as DDT were also used in increasing quantities on large collective farms. Dispersed by helicopters and planes, they contaminated the environment. Moreover, Soviet pesticides were less effective and more polluting than those used in the West. In the global South, economic means dictated that most small farms were excluded from chemical modernization. However, large cereal, sugar, and cotton fields in Latin America, as well as those devoted to export crops inherited from colonization in Asia, gradually adopted chemical treatments. In great secrecy, some very toxic pesticides were used on plantations. Nemagon, the commercial name for a powerful insecticide developed in the 1950s by Dow Chemical and Shell Oil, was liberally sprayed to destroy the microscopic nematode worms that attacked the roots of banana trees. Used in large quantities in banana plantations in Central America, the Caribbean, and the Philippines, Nemagon raised major health concerns after 1975 when it was banned in the United States. Nevertheless, tens of thousands of agricultural workers in Southern Hemisphere countries were victims of cancer, blindness, infertility, and other medical problems directly related to its use. In the same spirit as in the West, and with strong encouragement from the central government, which garnered support from American foundations, the Ford Foundation, for example, the Green Revolution and its tons of pesticides also affected India beginning in the 1960s. Pollutions were accompanied by considerable social changes, which upended the traditional peasantry and made them wholly subsidiary to agro-industrial powers. In China, resistance to this transformation was stronger, and the use of pesticides remained limited before 1976 and the death of Mao Zedong. The health and environmental problems linked to the intensive use of pesticides only became a concern for agricultural chemistry's proponents once insect resistance to chemicals emerged. Once the chemical industry developed new molecules, DDT's use declined. As in the Lyon region in 1966, organochlorines were chased out of the market in favor of increasingly complex organophosphorus compounds. Denunciations of the new products, initially marginal, rose nevertheless. In 1952, Roger Heim, director of the Museum of Natural History, warned against the large-scale use of certain chemical substances, insecticides, fungicides, rodenticides, herbicides, which may lead to very regrettable alterations of natural balances. In 1962, the American biologist Rachel Carson published her famous Silent Spring, in which she condemned the ravages of pesticides on animals. It was also at this time that the first movements for modern organic farming appeared, mainly in Germany and England.
Inspired by the agronomic principles theorized in the interwar period by the Austrian philosopher Rudolf Steiner, the German Ehrenfried Pfeiffer, the Englishman Albert Howard, and the Japanese Masanobu Fukuoka, advocated organic farming, l'agriculture biologique in French. The practice began to acquire momentum in the 1950s and 1960s as a reaction against the growing use of chemistry. In France, the French Association of Organic Agriculture and the Nature and Progress Association were created in 1961 and 1964 respectively. In this context, in 1972 the French government chose to reform a 1943 law on the approval of toxic substances in agriculture to adapt it to new health and environmental risks caused by agricultural pollution. This reform, which was also inspired by the 1969 American decision to ban the import of French milk and cheese containing high levels of DDT, was part of a worldwide movement. In 1970, Sweden banned DDT, followed by the United States and France in 1972, and most Western countries thereafter. But DDT remains in daily use on other continents. On the eve of the 1970s, the miracle and the hopes of the post-war period began to turn into a nightmare. Warnings against pesticide products multiplied in a manner similar to those that had accompanied widespread motorization and the rise of mass consumption. Governments were compelled to intervene, and companies were made to change their practices and markets. Nevertheless, the attraction of consumption limited the scope of these disputes. After a few years of economic crisis following the oil shocks, the image of a glorious and prosperous era emerged as the true expression of the times. It is no accident that the term "Glorious 30" was coined in 1979. However, an analysis of the setbacks to production and consumption forces a shift in gaze and change of focus in order to reconsider this period. The benefit of greater hindsight might justify rebranding the "Glorious 30" as the "Polluting 30" or the "Devastating 30". Since the First World War, economic and scientific transformations have been considerable. The world of 1975 hardly resembled that of 1914 at all. While the pollutions that accompanied this evolution changed in nature, the same logics of expertise and oversight remained. At the same time, a change in regulatory and political resistance to environmental contaminations corresponded with the change of scale in the pollutions themselves. 10. The politics of pollution. Wars, energy systems, and consumer societies all reconfigured the polluted world and its political management. Although regulations were still rooted in 19th-century modes and practices, with some localized variations, a combination of judicial recourse and administrative prevention and controls spread across different levels of jurisdiction, methods of intervening to protect contaminated spaces adapted to industrial excess and new means of international mobility, all while struggling to keep up with new, toxic products and the unanticipated hazards they posed. If the rise of white lead embodied the manner in which authorities demonstrated their bias in favor of industrialization in the previous century, asbestos became, after 1914, one of the new flagship products that came to symbolize the fragility and inadequacies of existing regulations. Asbestos was initially regarded as a modern miracle. This fibrous mineral silicate was first considered a symbol of purity because it was the perfect fire retardant, when fire was one of the greatest scourges of large industrial societies. Asbestos made its way into workplaces, offices, schools, and houses. Estimates suggest that 174 million metric tons of asbestos were used in one way or another over the course of the 20th century. It was responsible for extensive contamination and hundreds of thousands of deaths. The early history of asbestos as a miracle product is a little oversimplified. At the beginning of the 20th century, a work inspector named Dennis Orbo reported on the dangerous nature of this substance in a study that warned against the pernicious action of its dust, and the suspected deaths of at least 50 workers in a factory in the Condé-sur-Noireau commune in the Calvados department in France. The link between exposure to asbestos fibers and deaths in certain professions had already been established. In the United Kingdom, the first cases of death caused by asbestos were documented in the 1920s. Numerous articles, notably in German and English medical journals, dealt with the fiber's threat to the lungs. However, asbestos was not banned anywhere until the end of the 20th century. Figure 10.1. Anaconda Copper Factory at Washoe, 1916. Like many chemical industries, copper refining was extremely polluting, because of the acid and sulfurous gases that devastated the surrounding environment. The industrial scale of these refineries took on gargantuan proportions on the eve of the 20th century. At the Anaconda Copper Company operated Washoe Mine in Montana, United States,
An expansive network of laboratories, workshops, and storage facilities was organized around the flue pipes center, which converged on Anaconda smelter stack, which, at 178 meters, was then the tallest chimney in the world. More than any other product, asbestos clearly demonstrates how a complex network of control and influence lay behind the management and regulation of polluting substances throughout the century. In continuing to apply 19th-century legal and administrative policies, industrialized states proved incapable of banning or controlling the spread of toxic products, as industrial lobbies gained influence and international trade intensified. As a rule, hazardous products were only eliminated when a more profitable substitute became available. Anti-pollution policies did exist, of course, as did various measures to protect the natural world, but their enforcement was sporadic and limited. However, by the 1970s, the new industrial and health risks of the age of extremes radically transformed the nature of pollutions. New hazards and better understanding of old hazards meant that concerns about contaminations were a more significant part of discourse for societies and states and forced legislators to revise regulatory systems. New environmental policies evolved, as disputes and ecological organizations grew in number. In this framework, the 1970s were a decisive turning point. Weak regulations. Prior to the 1960s, policies to limit and control pollutions were fragile. Even though international organizations such as the World Health Organization, WHO, 1945, the Food and Agriculture Organization, FAO, 1946, the International Labour Organization, ILO, 1919, reformed 1946, and the International Union for the Conservation of Nature, IUCN, 1948, were working to better understand the phenomenon, pollutions had for a long time remained a local or a state prerogative. The four principal regulation methods inherited from the 19th century were common law, administrative procedures, technological promise, and confidence in dilution. These endured with varying degrees of significance, depending on the time period and the country. In the United States, both common law and local regulatory bodies became progressively less important, giving way to greater intervention from the federal government. In 1915, the Supreme Court declared that it was no longer unconstitutional for governing authorities to tackle industrial pollutions, a decision that set a precedent. Such legal changes notwithstanding, the advent of the First World War weakened environmental initiatives and the conflict marked a pivotal turning point as the fight against smoke pollution lost momentum. All countries involved in the war witnessed a weakening of anti-pollution movements. In 1916, for example, the Supreme Court of the German Reich deemed that polluting the river Roux was a normal part of industrialization. The previous year, a plaintiff arguing over the destruction of his orchard had had his case dismissed from court. The judge ruled that it was irresponsible to endeavor to manage an orchard in an industrial city. Pollution had become an inevitable phenomenon, a natural part of industrialization. The United States had seemed on the brink of resolving smoke pollution problems prior to 1914, but the funding to do so no longer existed during the Great Depression of the 1930s. In fact, any progress on the matter hardly went beyond the local setting. For example, in St. Louis between 1937 and 1950, the city's smoke commissioner, Raymond Tucker, succeeded in introducing a municipal ordinance that contributed to significantly reducing urban pollution by favoring the use of coke over its dirtier counterpart, coal. A similar improvement appeared to take place in Pittsburgh as a result of neighborhood protests that pushed local authorities to adopt measures to control industrial smoke. The first piece of federal legislation regarding pollution addressed waterway pollution in the 19th century. It was not until 1955 that any federal legislation regarding air pollution was passed. The National Air Pollution Control Act, followed by the Clean Air Act in 1963, was particularly significant because it offered the first legal opportunity for the federal government to intervene in this domain. In Europe, state intervention and public power varied according to social and political contexts. In France, municipal decrees on smoke fell into disuse during the Great War, but were reinstated thereafter to control pollution by the large suburban plants then in full development. The deadly fog in Meuse in December 1930 provoked numerous reactions in Belgium and abroad. Foreign reports of this event, however, relieved industrialists of all responsibility in favor of a more fatalistic vision. In 1933 this fatalism was further fostered by the Belgian Prime Minister, who wrote to the mining community that, even if it is important to prevent the atmosphere from being polluted by sulfur dioxide from factories, we cannot advocate measures that would undermine the industry and take away their livelihoods. Nevertheless, one consequence of the toxic fog was the Morizet Law, named after André Morizet, a socialist senator and mayor of Boulogne-Billancourt, passed in 1932 to govern air pollution in France in response to increasing industrial smoke. Its effect, however, was limited. Far from improving the situation, it instead hindered actions undertaken by municipalities by entrusting the prefects to manage the problem. Moreover, the law only applied to large industrial plants that were given a 3-year period in which to conform to prefectural decrees. The problem of smoke pollution was then overshadowed by both the tensions surrounding interwar politics and the great economic crisis of the 1930s. In France, as in Belgium and Germany, authorities hardly got involved, although certain large cities such as Lyon did take some initiative to protect the health of locals by negotiating limited compromises with industrialists. Globally, the political and social emergencies of the time, coupled with totalitarian dangers and mass unemployment, meant that concerns over pollutions were relegated to the margins of public debate. The prefect in the Rhône department showed that this was indeed the case, in a report written in 1938 that noted, several factories have had to postpone the installation of smoke-controlling devices, due to the economic slump and the precarious state of their treasuries. In France as in Great Britain, national laws governing air pollution were not introduced until the 1950s, in the wake of the deadly fogs in Donora, Pennsylvania in 1948 and London in 1952. The Great Smog of London accelerated the government's impetus to act. Hugh Beaver was chairman of the Committee on Air Pollution, 1953-1954, that produced the Clean Air Act of 1956. Unlike previous laws, this act contained a particular clause to include household fires, and introduced areas in some towns and cities where only smokeless fuel could be burned. Yet another spectacular smog, this time in New York in 1953, which resulted in 200 deaths, brought about the Air Pollution Act in 1955 in the United States. These smog episodes had a residual effect around the world. In France, an interministerial committee was put in place and various events were organized to discuss the problem. The Morizet Law was replaced by a law on air pollution and smells, promulgated by the new Gaullist government in 1961. But this national legislation was largely inefficient, and Paris was really the only city concerned that cars were still not considered part of the problem. This law was followed by a second, pertaining to water, its management, allocation, and preservation from pollution, 1964. Generally, authoritarian regimes around the world accorded very little attention to pollution, and repressed complaints by residents. This was the case under Mussolini in the 1930s to protect the aluminum industry. Similarly, in Franco's post-Civil War Spain, pollution remained a secondary concern. The country had long suffered political isolation and economic stagnation, and it was not until economic growth began in the 1960s, accompanied by a hike in pollutions, that some laws were put in place by the central government to regulate air pollution, notably 1972, 1974, and 1975. Worldwide, environmental concerns usually came from opponents of a particular governing regime, and thus after Franco's death in 1975, environmental issues could finally be heard in the political arena at the national level as well as in autonomous regional administrations. In Germany, before the Nazis' rise to power, the Weimar Republic was faced with the troubling fact that inflation and its negative social repercussions had led to a decline in the fight against smoke pollution, the result of a sort of official lethargy. The German bureaucracy was incapable of circumscribing pollution, and most efforts were put toward improving furnace efficiency and installing purification techniques and filters to curtail toxic soot. The status quo prevailed with Hitler's rise to power, even though some have thought that they could interpret Nazi policies as being ecologically significant, with the adoption of a law to protect animals as early as 1933, or the many speeches given on the protection of nature. In fact, no great measures were taken to reduce pollution at all, with rearmament and preparations for war actually increasing pollutions at that time. In the East, the emerging Soviet Union and Cold War ideologies weighed heavily. After the 1917 revolution, and in spite of continuing internal troubles and the threat of civil war, Soviet authorities quickly focused on sanitation and public health issues. Health services were drastically overhauled, and beginning in the 1920s several decrees were made by the People's Commissariat for Labor to protect cities from industrial nuisances. For example, parcels of land were allocated for industry in order to situate it farther from populated areas. Moreover, Soviet scholars engaged in a series of measures and evaluations to calculate the rise in, and effects of, industrial pollutants. Various industrial health institutes were created, and numerous publications also discussed pollution as a concern. In 1935, the first pan-Soviet conference dedicated to the fight against air pollution was held in Kharkiv, in northeastern Ukraine, followed by a second in 1938. There, representatives from the country's major health institutes and laboratories considered methods to determine air quality, and measures to be taken to protect the population. The backdrop to these explorations, of course, was the country's massive industrialization during which workers' rights were violated, so one might question the sincerity or centrality of such initiatives. Also around this time, specialized groups of health inspectors in numerous cities in the USSR were tasked with controlling air pollution. The Second World War and the Reconstruction period that followed it, under the rule of the Stalinist dictatorship, once again slowed down progress on pollution control initiatives. However, the 1940s saw Soviet authorities implement environmental legislation and standards for maximum admissible concentrations of toxic substances in air, soil, and water that were more stringent than those in the West. In 1949, for example, new factories could not be built, nor older factories reopened, unless health regulations were applied. A substantial amount of scientific work showed the harmful effects of pollutants on human health, and the Russian law of October 25, 1960, for the protection of nature included measures to combat pollution, comparable to those found in Western laws. In 1963, health monitoring became law, by federal order, in all republics of the USSR. During the Cold War period, in the authoritarian regimes of the East, like the GDR, pollutions and environmental problems were described and interpreted as the manifestation of the capitalist crisis and its obsession with profit. The technical progress associated with the socialization of the means of production must naturally solve the problem. In 1954, a law was passed in the GDR for the protection of nature, but it made no reference to pollution. Pollution controls were adopted in the 1960s. At that point, scientific research and study on pollution commenced in earnest. This included an extensive inquiry into SO2 emissions that was launched in 1965 and examined emission levels from 1,000 industrial plants in East Germany. In 1966, a decree from the cabinet stipulated measures to be taken to limit air pollution and, at the end of the decade, other inquests attempted to evaluate industry's pollutant waste and its cost for municipalities, agriculture, and forestry. In the absence of pollution abatement measures, polluters were required to compensate victims, agricultural producers and urban dwellers. However, rather than penalizing polluting industries and requiring that they install preventive measures in their works, companies found they could anticipate and plan for damage payments and integrate compensation into their budgets and management. As a result, the installation of filters moved slowly. Instead, local residents adapted to the presence of nuisances and to being compensated for them. This glut of legislation should not lead us into falsely thinking that environmental regulations became a priority. They remained on the back burner until the 1970s, and in the meantime tended to be very general, stopgap measures to address specific problems. In no way did they trouble themselves with hunting for the root of pollution problems or targeting dirty industrial sectors. In fact, the administrative framework that regulated industrial establishments was still a distant legacy of the 1810 law. In France, legislation had been reformed with a law on December 19, 1917, which gave more power to third parties through a system of increased sanctions against polluting industries. At the same time, however, the new law introduced the declarative regime, which allowed some industries to work outside the legislation's administrative scope. Technical improvement remained the focal point of French pollution measures. As a result, when European cooperation was enhanced, the fight against pollution was generally taken over by sectors responsible for promoting industrialization. The European Coal and Steel Community, ECSC, 1952, searched for ways to reduce industrial dust, but through technical means, since its overriding objective was to support the European coal and steel industries, to enable them to modernize, optimize their production, and reduce costs. It was not until the 1970s that the European Economic Community began to deal with the environmental problems caused by the industry. Table 10.1. European air pollution laws between 1956 and 1976. Year, country, title of law. 1960 USSR law for the protectee on of nature, including industrial pollution. 1961 France law regarding the struggle against atmospheric pollutions and foul odors. 1964 Federal Republic of Germany technical directives for air quality. 1964 Belgium law for the struggle against air pollution. 1965 Federal Republic of Germany Clean Air Act. 1966 Italy Law Against Pollution. 1967 Czechoslovakia Clean Air Act. 1968 Great Britain Clean Air Act. 1970 German Democratic Republic Law for the Protection of Nature. 1970 Ireland Decree on the Observation of Air Pollution. 1970 Netherlands Law for Protection Against Atmospheric Pollution. 1971 Belgium Decree for the Purity of the Air. 1971 Italy Decree for Emissions Thresholds. 1973 Denmark Environmental Protection Law. 1974 Federal Republic of Germany Federal Law for Protection Against Science and Technical Directives Regarding the Air. 1975 Belgium Royal Decree for the Struggle Against Air Pollution for SO2 and Suspended Solids. 1976 France Law Regarding Class E feed facilities on environmental matters. 1976 Luxembourg Law Against atmospheric pollution. 1976 Hungary Law for the Protection of the Human Environment. As was the case with asbestos, industrial companies were infrequently subjected to binding regulations. Accusations of responsibility were difficult to prove amidst the vague and general notions on the protection of nature and air quality. This left public authorities essentially powerless to stop the spread of harmful substances. Policies for the protection of public health failed on numerous occasions. In France, for example, the Eternit Company was founded in 1922, and from 1929 onward it provided 50% of asbestos cement, the principal use of the substance, consumed in the country, with production increasing tenfold between 1937 and 1974. Within 40 years, the company was one of the world's leaders in the sector, becoming an enormous international aggregate of factories and mines in France, mainly Corsica, in its colonies such as Algeria and Senegal, and also in India, China, and Brazil. Over the span of 50 years, this industry of death contaminated environments, local populations, and workers at every step in the production process. In 1962, the European Commission warned its member states of the dangers of asbestos, but no specific regulation to limit its use was introduced in France before 1975. Constructing uncertainty. The close relationship between states and increasingly powerful companies and their experts is a decisive factor in illuminating the continuing weakness of environmental regulations. Legislation and regulations are made in complex power relationships and are the product of discourse and acts, influences, and expertise that lead to decision-making. Within this rubric, the influence exerted by large multinational companies, whose power gradually exceeded that of the states, extended in tandem with their size. The rise of these large organizations with branches around the world, engaged in manufacturing in several countries, illustrates the quintessential challenges facing governments who would regulate against pollutions more stringently. In addition to their legislative influence through lobbying interests, these multinational companies are surprisingly nimble, and in the face of sterner pollution controls they relocate quickly and easily in search of raw materials and cheap labor. At the same time, these gargantuan corporate powers dispose of waste and pollutions from their production activities with impunity. Big American companies were especially responsible for initiating this internationalization. Their practices contributed to the continuing exploitation of poorer countries and the constant displacement of pollutions, while trying to frame the debate and influence the way they were regarded. In the world of production-oriented and modernizing engineers, these corporations were subjected to constant challenges. Faced with attacks and denunciations, companies invented the decontamination market and disseminated their technological solutions. In 1960, the trade union chamber of the French iron and steel industry created a commission for the fight against air pollution within its Steel Technical Association. Some sectors, such as oil, established their own measures to counter criticism against their emissions and environmental misdemeanors. In 1949, for example, the French information department of the Esso company created the quarterly magazine Pétrole Progress. Equivalent journals appeared in the main industrialized countries. Richly illustrated, this periodical lauded the infinite potential of fossil fuels and celebrated the wealth of oil nations, all while carefully concealing the industry's ecological transgressions. When the topic of pollution arose more vigorously at the end of the 1960s, Pétrole Progress focused on minimizing it by absolving the petroleum sector of responsibility and shifting the debate's attention toward the future of the clean combustion engine. Industrialist strategies to deny or obfuscate the reality of the pollutions they created were precociously and particularly well highlighted in the American case. Indeed, many polluters acquired their techniques directly from the tobacco industry, which became a master at deflecting and misdirecting attacks against its products. The historian Robert Proctor has demonstrated the existence of a deliberate policy of generating scientific ignorance in popular, mainstream discourse about the effects of smoking. As scientific studies began to correlate lung cancer with smoking cigarettes as early as the 1930s in Germany, tobacco multinationals organized a defense based on uncertainty surrounding the medical results. In the early 1950s, when American scientists confirmed the link between smoking and cancer, representatives of 4 major corporations formed the Tobacco Industry Committee for Research. Their goal was to frame the tobacco industry in a more positive light and confront the negative backlash. The Committee for Research challenged the scientific evidence upon which critical studies were based. It intimidated researchers and policymakers, funded and produced independent research, lauded the industry's clean products, muddied the chain of causality, and infiltrated regulatory authorities. These and its other strategies were varied, energetic, and forceful. The primary ambition was to challenge science as a final arbiter of truth and producer of formal proof. The tobacco industry's deliberate construction of ignorance, a practice since dubbed agnotology, bought it time by spreading doubt about the reality of the deadly effects of the products it marketed. Polluting industries followed the tobacco industry's lead, rejecting claims about the hazards posed by pollution or their products, and blocking any intervention that threatened their production model. The making or construction of uncertainty seems to apply to all of industry's harmful effects. When acid rain emerged as a problem in the 1960s, industry was accused of destroying American forests because of its introduction of smoke filtration systems in factories after the London and New York smogs in 1952 and 1953. Ironically, by filtering out the fuel particles, which had the power to dissolve the acidity by chemical combination, the sulfur dioxide suddenly increased, then condensed in the atmosphere, falling to the ground in rainfall. Local pollution problems turned into regional problems. Whereas between 1969 and 1975, a great many articles addressed this problem, explicitly linking industrial pollution and forest destruction, industrialists followed the manual provided by the tobacco industry, claiming that the scientific knowledge was insufficient to provide certainty on the issue or justify regulatory measures. Similarly, the destruction of the ozone layer, caused by chlorofluorocarbon, CFC, pollution and identified in 1970, witnessed the same strategies deployed the following year. Manufacturers asserted that the hole found over Antarctica was due to natural variations. Almost verbatim, challenges to the abnormal occurrence of epidemic diseases around chemical plants were framed in the same way. The Manufacturing Chemists Association, MCA, was frequently at the heart of networks that merged industrial expertise and lobbying. Founded in 1872 by sulfuric acid manufacturers, the MCA experienced considerable growth around 1900 after the American chemical industry took off. In 1902, DuPont moved toward chemical production, while Dow Chemical and Monsanto, founded in 1889 and 1902, respectively, and the multinationals Hooker Electrochemical and Union Carbide helped turn the United States into the world's leading producer of chemicals. After the First World War, as the chemical industry experienced a new boom, the MCA mobilized to counter growing suspicions that many of its products were toxic hazards. In the 1920s, confronted with claims that tetraethyl lead, the basis of the new leaded gasoline, posed an especially toxic threat, the MCA deployed its network of expert researchers, Robert Keogh, a university professor, and Anthony Lanza, who headed the Industrial Hygiene Division of the Public Health Service and was a consultant for the Metropolitan Life Insurance Company, dismissed concerns and vouched in turn for the product's safety. Both also insisted that tetraethyl lead's economic benefits be taken into account, and, above all, that chemicals should be deemed harmless until unequivocal proof of their toxicity was established. In 1964, thanks to its effective lobbying strategy, the American industry produced 224,000 metric tons of leaded gasoline, 3 times more than in the 1940s. Debates over the safety of CFCs, renamed Freons, by the industry, followed a similar trajectory. Thanks to the money from the MCA, Keogh founded the Kettering Laboratory in 1930, which established itself as the most influential research institute on the toxicity of industrial chemicals. However, historical studies show that these influential experts and the groups that backed them were perfectly aware of their products' deleterious effects. Cover-ups and obfuscations masked the real hazards in order to save time and avoid regulations. When a serious industrial incident occurred in 1931-931, the Hawk's Nest Tunnel disaster, As a result of digging a tunnel, nearly 1,000 workers, mostly black, died of silicosis. Industrialists created the Air Hygiene Foundation, AHF, which became a particularly effective lobbying body to deny the responsibility of industries in pollution and worker mortality. In the development of legislation, industries often ensured that their interests were preserved. In the United States, the 1947 Federal Insecticide, Fungicide and Rodenticide Act, the 1948 Water Pollution Act, and the 1955 Air Pollution Act were each diluted, their bite removed, at the behest of industry. Because of the chemical industry's growing influence, and despite numerous reports that demonstrated the toxicity of products, notably from the oncologist Wilhelm Huper, until the late 1960s manufacturers tended to enjoy legal success when their products were challenged. Thanks to its experts and growing lobbying clout, industry succeeded in blurring the meaning behind scientific results and imposing uncertainty about responsibilities, demanding additional time, and highlighting technical improvements as the inevitable solution. This was the paradigm, from the 1920s through the 1950s, for lead compounds in paint, considered by the Lead Industry Association, founded in 1928, as an acceptable risk to be weighed against their profits, and from the 1950s to the 1970s for plastics, particularly vinyl chloride, VCM, and polyvinyl chloride, PVC. For the latter, historians Gerald Markowitz and David Rossner uncovered how the chemical industry concealed from the general public what it knew about the hazardous nature of its products and their carcinogenicity right into the 1970s. The case of asbestos, however, was the most edifying. This magic fiber had been a primary health concern. Warnings prompted numerous branches of environmental research. At the same time, however, its manufacturers adopted commercial strategies to disseminate their products while banishing or disregarding their health and environmental impacts. With the opening of many mines and factories, world production rose from 31,000, 1900, to 570,000, 1940, and 2.2 million metric tons, 1960, reaching its peak in the 1970s. Nearly 3.5 million metric tons were produced annually, mainly in Canada, 1.5 million metric tons, the USSR, 1 million metric tons, and South Africa. Figure 10.2. Global asbestos production, 1900 to 2005. Source. Based on Jock McCulloch and Jeffrey Tweedale, Defending the Indefensible, the Global Asbestos Industry and Its Fight for Survival, Oxford, Oxford University Press, 2008, 14. The growth of the industry ran parallel with a growing body of medical knowledge that warned about the product's harmfulness. As early as 1898, a British factory inspector identified workers' pathologies associated with asbestos production, followed by similar information in 1906 from the French labor inspector Orbeau. In the 1920s, several medical descriptions pointed to asbestos as a pathogen, and in 1931 the British government introduced dust control across the industry. In the 1930s, doctors in Germany and Japan reported that the fiber was a primary catalyst for lung cancer. During the war, Germany even recognized cancer of the pleura, a thin membrane around the lungs, as an occupational disease. In 1955, an epidemiological survey of South African mines confirmed the indices and extended the risks to surrounding populations. Mesothelioma, or asbestos cancer, was highlighted in these studies. And yet, after 1945 production continued to grow. Governments strongly encouraged asbestos use, which enjoyed growth in fields as diverse as construction, agriculture, and the electrical and automotive industries. Some sites were particularly affected. The small town of Casale Monferrato in Italian Piedmont was one important example. A first asbestos plant was installed in 1906, after which it became the largest Eternit plant in the world. Asbestos was presented as a symbol of development and prosperity. Its dust was everywhere, in schoolyard slabs and corrugated roofs. Before it was closed and destroyed in 1986, the plant had long contaminated the environment and claimed thousands of victims. The paradox of inaction can be explained by the counter-activism inspired by industrialists that took advantage of the trust society and government placed in industry to be good citizens and neighbors. To counter suspicions against asbestos, manufacturers activated their research networks by creating various institutes. The Air Hygiene Foundation, renamed the Industrial Hygiene Foundation in 1941, commissioned scientists like Lanza to produce counter-reports and promote the notion of an acceptable exposure threshold, which became an essential tool for governing toxic substances and resolving the disputes they raised. Canada was a lodestone for the asbestos example. Although the hazard of asbestos was no longer in doubt after 1952-1953, industrialists ensured further increases in production by hiding and manipulating toxicity data. This obfuscation has since been established. Even after the scandals and revelations of the 1970s, denials persisted, and it was not until the late 1970s that the major industrialized countries timidly began to regulate asbestos, via a supposed controlled use. Inasmuch as it constituted a potent force, industry did not have a monopoly on toxic expertise. The deepening gaze on pollution was also shaped by the development of toxicology and ecological science. Historian Christopher Sellers has shown that post-Second World War scientific environmental thinking has its roots in the industrial toxicology of the corporate world. Moreover, between the founding of the British Ecological Society in London in 1913 and the media recognition of this science in the 1970s, ecology changed from a simple branch of botany and zoology into a full discipline, complete with a coherent lexicon and accepted systems and praxis among a growing body of practitioners. Ecology designated both knowledge about the natural world and its functioning, but also a set of techniques and knowledge enabling a more rational and effective exploitation of the environment. The study of natural imbalances and interactions between substances and living species was at the heart of this science. In 1935, Arthur Tansley defined ecosystems as the basic units of nature on the face of the earth, elements that are constantly changing under the impact of human intervention. There was tension, however, in the world of ecologists. Following the work of the American Eugene Odum and his famous treatise Ecology, published in 1963, a branch of militant ecology, typified by the bestsellers of biologists Rachel Carson and Barry Commoner, specialized in highlighting disturbances introduced by human activities into ecosystems. For other ecologists, on the other hand, anxious to justify the scientific character of their discipline while resisting any militant, or political, anti-industrial, perspective, ecology was first and foremost a natural science, neither the science of pollution nor the science of the environment, but that of the global march of the living world. In addition to the new ecological science, medicine remained a key source for toxic expertise. In industrialized countries, in Los Angeles, London, and Paris, many doctors began investigating the effects of air pollution, and helped to build a case against pollution by reinforcing its public visibility. However, the situation varied greatly between the United Kingdom, where regular measurements of air quality were required starting in the interwar period, and France, where this type of scientific measure was slow in coming. In the 1950s, French doctors learned about the work of their colleagues in the English-speaking world, such as Professor Paul Coton of Los Angeles, who identified early on the potential for cancer risks from prolonged exposure to carcinogens at low doses. From the 1950s onwards, scientific measures and assessments of pollution became more pronounced, as shown by the creation in 1958 of the Association for the Prevention of Air Pollution, APA, which opened branches in the major French provincial cities, including Lyon and Marseille, but also at particularly polluted sites such as Lac. However, scientific surveys spread slowly, their regulatory influence was also slow. Industry was more agile. In France, spokespersons for major polluters quickly integrated themselves into the bodies responsible for investigating pollution. Major energy companies, such as EDF and the Charbonnages de France, were represented on APPA's board of directors. Industrialists began organizing their own association in 1960. The Comité d'Action Technique contre la Pollution Atmosphérique, CATPA, Committee for Technical Action Against Atmospheric Pollution, whose first president, the engineer Louis Armand, was also the president of the highly polluting Houillères de Lorraine, was also joined by a more technical body, the Interprofessional Technical Center for Air Pollution Studies. In fact, even if the medical professions were divided and not very homogeneous, the medical vision was often imbued with a technological approach that was based on chemistry and engineering sciences, relegating epidemiology to the background. That hierarchy hindered the accountability surrounding factories' pollution. Mobilizations, ideas about nature, pristine or polluted, evolved a great deal during the 20th century. Incongruous interpretations persisted, nevertheless. On the one hand, nature was viewed as an infinite, inexhaustible resource, whose very presence justified human exploitation and sacrifice on the altar of industry. On the other, nature was perceived as fragile and limited. Pollution and overexploitation threatened its sustainability. Such incommensurable readings of nature had profound impacts on how pollutions were understood, especially as pollution entered the popular lexicon during the 1960s.
Between the two world wars, pollution continued to be a sign of prosperity, full employment, and modernity, a continuation of ideas created in the great industrial basins of 19th-century Europe. Chimneys spewing black plumes were a common, and positive, feature of publicity that championed growth. That vision did not change until the late 1960s, when the factory began to be associated with aggression and harm, and blue skies gradually supplanted the images of darkened industrial clouds as a more desirable aesthetic. Former senior officials, such as Philippe Saint-Marc, who were active in planning policies after 1945, turned to environmental issues. In 1972, Saint-Marc drew up a widely publicized Charter of Nature, which collected 300,000 signatures, before publishing in 1975 a book on pollution that received a great deal of attention. Even if many scientists were bound to the protection of big and polluting industries, many other scientists denounced polluting practices. Whistleblowers contributed significantly to popular media's access to questions of industrial risks and pollution throughout the 20th century. In the USSR, some scientists warned against the scale of environmental pollution and destruction produced by forced industrialization. In spite of the repression they endured, they formed the embryo of a community of naturalists who pushed for the preservation of nature. In the United States, where scientists enjoyed greater social standing and the support of a powerful media regime, some of them worked extensively on the recognition of pollution and were vocal about changing regulations. For example, while the oncologist Hooper contributed to the banning of many chemicals whose role in the onset of cancer he denounced in the 1920s, Dr. Alice Hamilton, the first female professor at Harvard University, became a prominent public intellectual as her work on public health in the workplace galvanized important changes in labor laws. Hamilton was also a catalyst in launching professional epidemiology as a critical means of analyzing environmental pollutions. She denounced the use of white lead in paint and tetraethyl lead in gasoline by combining clinical examinations, toxicology, and epidemiological field investigations from 1910 onwards. She also showed that the mortality rate in most American industrial sectors was higher than their European counterparts. At the same time, in Great Britain, the first medical inspector of factories, Thomas Morrison Legge, popularized the notion of industrial diseases, and contributed to a certain recognition of the relationship between industrial diseases and pollutions. The Taylorist organization of British industry ensured, however, that much of his legacy was forgotten after his death in 1932. During the Glorious 30, the industrial boom provoked resistance to and questioned the benefit of controlling pollutions. Henry Fairfield Osborn's pioneering work, Our Plundered Planet, offered some resistance and rationale. The Frenchman Roger Heim also weighed in with destruction and protection of nature, a few years later, in 1952. The work of these two renowned scientists testified to the important role that naturalists played in the fight against pollution. But the most decisive milestone was the work of biologist Rachel Carson. In the late 1950s, inspired by cancer research, including the work conducted by Hooper, Carson focused on the impact of pesticides, which led her to demonstrate unusual bird mortalities as a result of pesticides in the environment and the spread of these products in agriculture. In her resounding book, Silent Spring, 1962, she accused the chemical industry of misinformation and explained how pesticides contributed to human cancers. The book quickly became a touchstone for the prohibition of toxic substances in the environment. In short order, it was translated worldwide. Carson was strongly attacked by the chemical industry, especially by DuPont de Nemours, the main manufacturer of DDT, but she nevertheless managed to convince the public and policymakers. Political momentum against pollutions began to hold sway. Carson's work was instrumental in the 1972 ban of DDT in the United States, which was followed by concomitant bans in most Western countries. At the same time in the United States, probably the country most affected by industrial pollution between 1945 and 1970, other scientists introduced new charges against pollutions. In the late 1950s, the geochemist Claire Patterson began to study the concentration of lead on the Earth's surface and showed that it had greatly increased since the dawn of the Industrial Age. Leaded gasoline, insecticides, food consoliders, water service pipes, kitchenware glazes, and paints were especially responsible for its spread. In 1965, Patterson published an article in which he tried to warn the public about the hazards associated with lead additives and launch a public opinion campaign against their industrial use. Naturally, Patterson ran up against stern opposition from the lead industry, and he fell victim to their lobbying and smear tactics. In 1971, he was excluded from the National Research Council research group that investigated lead in air pollution. Nevertheless, Patterson's warnings prompted the Environmental Protection Agency, EPA, to announce in 1973 the reduction and elimination of all lead additives in consumer products. During the 1960s, pollution was an inextricable feature of technological discourse. Authors such as Ernst Schumacher and Ivan Illich developed a concerted case for appropriate, user-friendly, and clean technologies, as distinct from authoritarian and polluting technologies. This debate enjoyed considerable intellectual fervor. Innumerable publications and experiments fostered transformative practices, and in the face of the flood of consumer goods, people turned to simpler, handmade tools. Many advocates contended that these soft technologies would break free of the marginal ghetto and conquer the world. Large-scale systems required a kind of centralized authoritarianism in their manufacture and implementation. Their control demanded standardization and their widespread adoption and acceptance. In contrast, smaller, unstandardized technologies represented a kind of social chaos, a decentralization of control, power, and wealth accumulation. As a result, large-scale systems opposed democratic technologies, ones that were soft, appropriable, and produced little pollution. During this period, technological gigantism was widely denounced in numerous contexts. In airports, for example, whose construction inspired more and more opposition and conflict, as their number increased after 1950. In addition to noise, airports' environmental impacts introduced new branches of expertise to assess the extent of their nuisance. Major airport construction projects in Roux, near Paris, and London, as well as in Tokyo and Osaka, encountered considerable opposition. In 1975, an OECD report compared airport emissions to factories, creating pollution, nuisances, and environmental risks through their expansion. Some economists also denounced the fallacy of perpetual growth. Whereas economic theory inherited from the 19th century did not reckon with growth's deleterious effects on nature, new interpretations wrestle with the question of negative externalities, their costs, and their role in market disruptions. In the context of capitalism's crisis during the Great Depression of the 1930s, pollutions emerged not only as a cost, but a cost that distorted the realities of economic growth, multiplied the negative externalities, and favored the polluters to the detriment of others. For example, the British economist Arthur Cecil Pigou proposed introducing taxes on pollutions in order to restore market equilibrium and price truth, by internalizing the external effects in the price of products. Similarly, in 1950, the German-American economist Carl William Kapp showed how the activity of private enterprises induced social costs not taken into account by the prevailing economic theories and their price systems. Air and water pollutions, the decline in biodiversity, and the deterioration of working conditions and living environments never appeared on the balance sheet beside the production methods that birthed them. Instead, those costs were carried by society. This debate gained traction at the end of the 1960s. In 1967, the English economist Ezra J. Mission published The Costs of Economic Growth, an ambitious treatise that publicized Nicholas Georgescu-Roegen's and Herman Daly's heterodox theories of the bioeconomy. Pollutions were analyzed as a brake on further development, a threat to the economic system itself. In a few years, the question received widespread analysis from economists. Even critics had to contend with pollution as a burden to growth. Some economists, such as Jean-Philippe Bard, sought to construct an environmental economy that would take the form of an extension of the dominant neoclassical economy. On the contrary, others believed that the scale of pollution and the environmental issue made it necessary to deconstruct this analytical framework in order to build a new economic science. This was the point of view of René Passet, Georgescu-Roegen, and Bertrand de Jouvenel, who proposed replacing political economy with political ecology. Their work stressed the importance of analyzing limits to growth and adopting lessons from the life sciences to construct what some economists called a bioeconomy, what others called ecological economics. Ignacy Sachs proposed building an environmental political economy that would make it possible to identify the winners and losers of the ecological game and the deterioration caused by the circulation of pollutions. The publication in 1972 of the famous Club of Rome report contributed to the media and political visibility of these debates, which had previously been restricted to specialists. The limits to growth and the entry of ecological economics into mainstream discourse forced many economists to turn to the environment and integrate pollution into their analysis models. In the United States, Wassily Leontief was one such example. Ambitious studies analyzed and modeled the economic costs, influence, and impact of pollutions. Jacques Thys, then a young sociologist, embarked on a study on the impact of automobile pollution. He was not alone in treading new paths, modeling air pollution in Lorraine, studying the hierarchies of costs associated with pollutions, and so forth, spurred many inquiries into pollutions and the economy during the 1970s, although curiosity and commitment to addressing these concerns ebbed in the following decade. Post-World War II globalization meant that this evolution in economic thought did not affect only Europe and the United States. As Japan rapidly converted to chemical agriculture, after its introduction by the American military, farmers readily adopted pesticides and herbicides as solutions to increasing yields and reducing intractable challenges to healthy crops. At the same time, Japanese doctors and consumers raised concerns about the chemicals' effects. Pursuing the first moves toward agriculture without chemical inputs since before the war, the Buddhist doctor Gyo Yanase unsuccessfully warned authorities about the dangers of the new chemicals in the 1950s. Similarly, Masanobu Fukuoka, a training microbiologist employed in the plant inspection division of the Yokohama Customs Office, resigned from his post to protest against agricultural pollution. He subsequently turned to cultivating the land. In his 1975 book, The Revolution of One Strand of Straw, he invented natural agriculture. The book's denunciation of scientific agriculture and its pollutions was based on a unified concept of man and nature nourished by Zen, Taoist, Shinto, and Buddhist traditions. During the 1970s, movements for organic farming were emerging. The writer Sawako Ariyoshi supported them by publishing in the major daily Asahi a serial novel titled Fukugo Osen, Complex Pollution. It was also at this time that the system of teikei, or direct sales, was introduced by urban middle-class consumers to access healthy food products. In addition to scientists and consumers, certain professional societies or community groups who were victims of pollutions organized to defend themselves against environmental aggressions. In 1920, French beekeepers published the newspaper L'Abeille de France, the French Bee. After 1945 it appealed to the state against what it perceived as the new agricultural chemistry's transgressions. On all sides, it proclaimed in 1946, "We hear the cries of alarm that have been rightly raised by beekeepers against the increasing use of agricultural insecticides." French beekeepers demanded standards, labeling, and education to teach better spraying methods. But beekeeping, considered an archaic, anachronistic practice, an unprofitable activity mainly practiced on a small scale by amateurs and, as such, devalued by the weight of large agricultural producers, was voluntarily sacrificed in favor of increasing rapeseed yields. In the same way, fishermen's complaints were constantly resisted and marginalized after 1945 in the name of industrial production. As with beekeeping, industrial prosperity was a question of scale. Big industries enjoyed big concessions from regulators. Sport and recreational fishing lacked the same kind of political clout. However, in keeping with 19th-century historical traditions, fishermen's associations often played a pioneering role, learned to assess links between pollutant discharges and fish mortality, and were empowered to manage the damages and interest paid by river polluters. Meanwhile, the number of fishermen rose to nearly 3 million in France in the 1960s. From inequalities to environmental injustices. At the intersection of regulatory inertia and polluting industrial activities, the question of environmental inequalities emerged. Urban dynamics, shaped by the automobile and large development projects, disrupted ecosystems and led to new spatial and social reconfigurations. The impacts of pollutions were played out on various scales, which increasingly sacrificed vulnerable classes and regions. Although it is difficult to draw up a complete overview of industrial infrastructures and how their relocations related to pollutions, since there are other factors, such as the cost of labor and changes in transport infrastructure, there is irrefutable evidence to suggest that some areas were sacrificed by hosting concentrations of the most polluting industries. This was particularly the case in the United States, where segregation is especially strong. Chicago and Pennsylvania's industrial cities serve as poignant examples. In an attempt to understand the social dynamics of environmental inequalities, Andrew Hurley traced the manner in which industrial pollutions exacerbated inequalities in Gary, Indiana. After the establishment of U.S. Steel in 1906, Gary began to grow rapidly. At the beginning of the 20th century, Gary was a small town on the shores of Lake Michigan, a few miles from Chicago. U.S. Steel built the largest steel plant in the world. Gary became one of the most polluted cities in the United States. In 1939, an industrial front of more than 10 kilometers was built along the lake. The heavy pollution that came from its works unevenly affected the population.
It mainly affected the workers, almost all of African American origin, but pollutions and their harm trickled out from there to the working class neighborhoods around the factory, composed of immigrants, then to communities populated by white workers, and finally to middle class, white neighborhoods. Gradually, from 1945 to 1980, avoidance strategies were implemented by the richest sectors of the population, much to the detriment of the poorest who remained close to the sources of pollution. In Hurley's reading, the rise of environmental consciousness was a class-specific process. If such research empirically demonstrates environmental injustice as an historical phenomenon, it is not easy to document it precisely. There are many examples, such as the Love Canal case revealed in 1976. After the closure of the Hooker chemical plant in 1953, working-class subdivisions and a school were built on the site of a former toxic landfill. As the chemicals leached into people's homes, contaminations became commonplace. Air quality measurements in the Louisiana Chemistry Corridor, Cancer Alley, between Baton Rouge and New Orleans, also indicate the incidences of higher levels of pollutions that align tidally with class geographies. The poorest populations live in the most polluted places. Many works confirm that populations who benefit the most from industrial production suffer the least from its pollutions. In the same vein, those most exposed to environmental hazards tend not to benefit from its riches. There is a long-standing relationship between inequality and pollutions. The management of nuisances follows a differentiated topography that subjects the most vulnerable social groups to the most deleterious environments. Wealthy classes, who enjoy greater social and geographical mobility, manage to segregate themselves from harm through the construction of income-based enclaves in safer fringes of the city, industrial reorganizations, and access to open spaces. This phenomenon can be analyzed at different levels because municipal, regional, and national variations offer different perspectives, which have become all the more pertinent since the post-1945 globalization of the economy. Indeed, environmental inequality trajectories transcend even national boundaries. In colonial and post-colonial relationships, it became possible to transfer the most unhealthy and dangerous industries to countries which do not set such stringent environmental standards of production as the Western, or Northern, countries now do. Table 10.2. Rate of pollution scaled geographically and stressing the exorbitant exposure burden suffered by the African American population in Convent, Louisiana. Location: African Americans as percentage of population discharges of pollutants, kilogram per person. United States 12.13. 2. Louisiana 30.89. 5. Cancer Alley, parishes, Louisiana 36.812. 2. St. James Parish, Louisiana 49.6163. 3. Convent, Louisiana 83.71032. 8. Data drawn from the 1995 Toxic Release Inventory. Source: based on Gerald Markowitz and David Rossner, Deceit and Denial, The Deadly Politics of Industrial Pollution, Berkeley, University of California Press, 2002, 265. Developing countries frequently surrender their subsoil to the control of large Western groups, whose mining operations, under looser controls than they might experience at home, have become critical sources of highly polluting activities and bereft lands. For example, the Belgian Congo, which became Zaire after independence, and now the Democratic Republic of the Congo, is the archetype of a colonized country pillaged for its mineral wealth and the continuity of that exploitation after decolonization. In this model, unsafe and unsavory extraction practices sacrifice workers' health and the health of neighboring populations. From the beginning of the 20th century, Belgian, British, and American companies set out to conquer the many geological riches of its best-endowed region, Katanga, where tons of copper, cobalt, gold, diamonds, manganese, uranium, tungsten, tin, and tantalum were extracted. The cruelest form of extraction capitalism was deployed in Katanga's mines, semi-forced labor in appalling conditions. The mine's African workforce grew from 8,000 miners in 1914 to 42,000 in 1921, while the other regions of the Congo employed close to 100,000 miners under conditions that approximated slavery. Exploitation intensified during the Second World War. The number of laborers rose from 500,000 to nearly 1 million between 1939 and 1945. After the war, Congo became the world's third largest producer of copper, contributing to the devastation of the environment. The conditions in the Congo were hardly an exception. Similar conditions existed in most of the raw material extraction areas of the developing world. The uranium mines of the French African Empire, Niger, Madagascar, Gabon, for example, offered comparable conditions. In Vietnam, specific rights were accorded to extractive international corporations that permitted the exploitation of resources in complete disregard of workforce health and the pollution caused by the extraction and processing of ores. From 1889 to 1930, mining law, derived from the Mining Act of 1810, was amended to ensure maximal resource exploitation despite significant environmental damage, including to the water system. In addition to inert waste, the devastation of mining regions came from heavy metal dusts, considerable volumes of cyanide, hydrochloric acid, and quicklime discharges. Mortality rates linked to these pollutions were considerable. Independence did little to reduce the high death rates in the mines. Mining typically occurred out of sight of larger populations, but it was also not limited to colonial or post-colonial spaces. Removed from centers of power and attention, mining was also prominent in developed countries. In the United States, mines caused irremediable pollution that affected the health of local populations and irreversible damage to ecosystems. In South Africa, the apartheid regime after 1948 took race, class, and environmental exploitation to its logical extremes, which translated into stark environmental inequalities. Pollutions were concentrated where vulnerable populations lived. In spite of environmental laws that followed in the technical spirit of those passed in Europe or the United States, in 1956, water law, and 1965, law on air, the South African variants established differentiations on their stringency and enforcement that followed spatial lines. Public health and ecosystem protection were prioritized in some areas and rejected in poorer, black areas. As a result, in spite of numerous regulations, pollutions persisted because they were knowingly permitted in areas of social and political vulnerability. Apartheid ensured that these inequalities, and the severity of the pollutions, were kept more or less invisible, at least until the beginning of the 1970s, when the scale of pollutions and their deleterious effects affected the country as a whole. The geographic dispersion of pollutions and class reinforced social inequalities and the dynamics. Environmental well-being was long considered a post-materialist issue, a luxury afforded only to more affluent sectors of society. The historical record suggests otherwise. Pollutions also appeared in the preoccupations of the workers and the working class, in both urban and rural settings. This pioneering field of environmental history research draws attention to the existence of many historical social struggles by subordinated groups keen to protect the environments in which they lived. It is not always easy to reconstruct popular representations of pollution. Voices of the grassroots instigators were frequently drowned out by the deluge of propaganda, advertising, pro-chemical demonstrations, and the like, that denied or dismissed their suffering, while the pollutions were hailed as symbols of progress. However, several life stories and autobiographies illustrate the manner in which the poor and disenfranchised were not at all indifferent to the environmental nuisances that surrounded them. In France, the study of workers' writings published during the interwar period shows a strong anxiety about the contaminated air, and the desire to regain contact with an unsoiled nature. For example, Maurice Lime recounted the story of the life of a child in Metz during the Great War. He was the son of a railway worker who became a miner. From here to the Moselle River, Lime wrote, the mines first, then the steelworks, sully the Orne River, and kill its fish, while the emissions from the blast furnaces kill the vines and make the forests languish. In Faubourg, published in 1931, Lucien Bourgeois presented the trajectory of a young working-class couple who settle in the suburbs, where they breathe the pure air with joy, because the air from the town from which they came had been foul. In the story of his youth in Lyon in the 1920s, the libertarian writer and worker Georges Navel also described the ugliness of working-class neighborhoods, with their high chimneys and line of leprous facades, shutters, shop fronts, blackened by smoke. The proletarian and socialist writer Albert Soulelou recalled the landscapes of the industrial suburbs of Paris, home of the ugliest plain in the world on the side of La Courneuve and Staines. Soulelou described the riverways sacrificed to industry, a disgusting brook which killed its beautiful grasses, and which, once arrived at St. Denis, came out black, thick, bloody, ashamed, so ashamed that it was no longer moving. Even if trade unions and their struggles played a decisive role in improving the working conditions inside French factories, as recognized by the establishment in France of the Committees of Hygiene, Safety, and Working Conditions, CHSCT, 1947, they seemed, on the other hand, to have been less interested in outside pollutions or the more global ecological stakes associated with industrial production. This observation can, however, be put into perspective as the concerns of the trade union organizations varied according to the context, the economic situation, the extent of the social conflict, or even the political opportunities that were presented. In many cases, union struggles cut across environmental struggles and created a real labor environmentalism. During the 1960s and 1970s, the United States experienced many conflicts led by oil, chemical, steel, and agricultural labor unions against the threats that waste and pollutions posed. In 1973, a big strike against Shell was supported by conservation organizations. Workers' health and the fight against pollutions made common cause in the face of a large company deemed to be predatory, both against the environment and against its labor force. Indeed, American labor and environmental movements forged an early alliance. That bond only started to fray in the 1980s at the height of Ronald Reagan's presidency. Alliances between environmental and worker organizations were also established in the fight against pesticides. Anthony Mazzocchi, a prominent labor leader, embodied this rapprochement between environmentalism and trade unionism in the United States. Starting in 1953, his continuous and determined action to combine occupational health and environmental health within the chemical industries helped to force the subject of workers and environmental health onto the government's agenda. In no small measure did his efforts, and those who worked with him, spearhead the move toward the monumental Occupational Safety and Health Act of 1970. Similar forms of labor activism that mobilized against pollutions occurred in Italy, France, and Canada, where they also won some hard-earned results. A brief case study of vinyl chloride illustrates the alliance that was built between occupational health and pollution. Internationally, the International Federation of Chemical Workers Unions, and in particular its secretary Charles Levinson, had been raising concerns about PVC since the early 1970s, while in France doctors had expressed worry. For example, Groupe Information Santé, followed by the chemistry federations of the CGT and the CFDT. The protection of health in the workplace and the denunciation of pollutions were also raised by other trade unions, who increasingly challenged industry's tactics of monetizing risk. Occupational health was regarded as an employer's medicine. Instead, trade unionists wanted to invent another expertise, one that worked more closely with and directly for laborers. Such tensions came to a boil in a number of social and environmental struggles, such as those of Roane Poulenc in Vitry, 1970, and Udine Kuhlmann in Pierre Benite near Lyon, 1971, as well as that of migrant workers in the Penaroya lead factory in Lyon, 1971-1972, and another that began in the asbestos company Amasol in Clermont-Ferrand in 1974. In all cases, these struggles led to demands for the invention of another expertise, in partnership with the workers. In the early 1970s, after decades of fruitless dialogue, Japanese trade unions also succeeded in teaming up with neighboring communities to confront the chemical pollution that had caused Minamata disease. Rejecting industrial corporatism, unions ended up denouncing the chemical industry's misdeeds. They supported public complaints against pollutions, and pushed employers to recognize and pledge assistance for occupational diseases and to diminish industry's environmental transgressions. Indeed, Japanese society was more than ready to demonstrate greater regulatory awareness and responsibility for industrial pollutions. By the 1970s, a number of cases had become mainstream issues and causes of considerable concern. Mercury poisoning at Minamata, 1973, the cadmium river in the Toyama Prefecture, 1970, and the asthma epidemic suffered by the population in Yokkaichi, 1972. The expansion of trade union mobilizations against pollutions was indicative of a groundswell that gained widespread support around 1968 and the years that followed. A plethora of disasters captured media and public attentions. The oil spill caused by the sinking of the Torrey Canyon off the coast of Cornwall in 1967, the massive insecticide spill in the Rhine in 1969, which spanned more than 600 kilometers and killed about 20 million fish, prompting outrage, and others. Both in the Soviet world and in the West, mobilization spread as vast campaigns against urban fumes, pesticides, and discharges of hydrocarbons, lead, or asbestos all emerged. The first major mobilization of public opinion in the USSR, spurred by scientists and writers, occurred in the early 1960s against the risk of pollution in Lake Baikal. In France, radio journalist Jean Carlier galvanized opinion to prevent a large tourist project in the Vanoise Park that threatened to defile the majestic alpine sites. Backed by the brand new French Federation of Conservation Societies, FFSPN, this green campaign was a success. Publications criticizing environmental threats attracted more and more attention. A veritable militant ecological press emerged in the major industrialized countries around 1970. In the United States, the Earth Day celebrations systematically referred to air pollution. Conferences on the subject attracted people from all over the country. Opinion polls showed that the proportion of those who considered air pollution a very serious problem grew from 28% in 1965 to 55% in 1968 in the United States. More than an awareness or awakening of ecological consciousness, which heralded pollution's mainstream arrival in public discourse, the 1960s corresponded to a more explicit shift in the approaches toward environmentalism. Where earlier conservation sentiments tended to be framed in an elitist tradition and worked for local regulations, the new environmentalism was more militant and rejected the siting of polluting industries anywhere. More militant approaches were evident in new publications such as the French journals Survive et Vivre, Survive and Live, founded by the mathematician Alexandre Grothendieck. Its contents mixed radical discourse and satirical denunciation of modern societies and their pollutions. Beginning in 1970, the series of children's Barbapapa books, for its part, proffered a very ecological vision of society, and mounted an implicit, and often explicit, challenge to technical productivism. Polluting industry was frequently portrayed as a mortal predator. See Figure 10.3. Figure 10.3. Satirical denunciation of air pollution. Source: Survive et Vivre, No. 10, October to December 1971. As new environmental issues transformed the political landscape, the movement's vocabulary underwent considerable transformation. The word environment itself changed meaning and forced its way into ever more discourse, especially among North American planners and forecasters confronted with the proliferation of waste and pollution. The English verb to recycle, coined in 1926, spread after 1945. Its French counterparts, recycle and recycling, recycler and recyclage, appeared in 1959 and 1960. Their use extended in both languages during the 1970s, precisely at a time when the amount of waste on a global scale was growing exponentially. This change in language was also accompanied by a broader restructuring of the intellectual and political understanding of the environment and an institutional reorganization that initiated something of an ecological revolution in many countries. The increasing concern over pollutions and their effects led to the admittedly slow, punctuated, difficult, and marginal emergence of intellectual currents that can collectively be understood as the incipient stages of a new and united notion of political ecology. This was by no means a homogeneous and unified theoretical corpus. Rather, it constituted a complex nebula ranging from liberal and centrist positions to anarcho-libertarian approaches that assumed and sometimes combined, even within the same author's work, strands of nostalgic romanticism and anti-capitalism. In the intellectual and political ferment that accompanied the 1968 revolts, political divisions became strained. Pollutions inspired new debate over the boundaries between nature and culture. A new militant world emerged around pollution issues. Many new organizations operated on a scale that reached well beyond local concerns. Greenpeace, a non-governmental organization founded in 1971 in Vancouver, Canada, made important connections between its two complementary bases: the fight against pollutions and the protection of the environment on the one hand, and anti-nuclear militancy on the other. An increasing number of environmental groups were responding to the growing audience for their message. In 1971, Friends of the Earth was formed. A section of this international network quickly established in France on the initiative of the journalist Alain Hervé, who was also founder of the magazine Le Sauvage, 1973-1980. Pollution's entry into mainstream politics also took place through more traditional electoral and institutional dynamics. In December 1971, the People's Movement for the Environment, the first explicitly environmentalist party, was created in Neuchâtel, Switzerland. It won 8 seats in the 1972 communal elections. The Australian Green Party, United Tasmania Group, was also formed in March 1972. In the following years, Green parties sprang up in most industrialized countries. Their presence transformed the political landscape, bringing the issue of pollution squarely into the public arena. In France, the Ecology and Survival movement was launched in 1973 by Solange Fernex, a pacifist and feminist. Its candidate in the 1973 legislative elections in Mulhouse was the first French Green to stand for a national election. He too won on 70% of the vote. The following year, René Dumont, who was honorary president of Friends of the Earth, became a Green candidate for the presidential election. Dumont, who began as an agronomist but turned to third worldism and then to environmental issues in the 1960s, published Utopia or Death in 1973. It sold 150,000 copies. Dumont laid out his radical criticism of wasteful society, castigating the selfish rich countries, the automobile as symbol of our aberrations, the mechanized industries that ruin local crafts and disrupt ecosystems. Pollutions occupied a central place in his work, which championed a radical and emancipatory conception of politics. Dumont obtained only 1.32% of the votes cast, but he came to embody pollution's new visibility in media and in political affairs. This politicization of pollution issues around 1970 led to a major reorganization of administrative and regulatory structures. Willy Brandt, mayor of Berlin and Social Democrat candidate, SPD, in the German federal elections of 1961, insisted to members of his party in a convention speech that the sky over the Ruhr region must be blue again. Brandt's call, which initially aimed to extend the party's electoral influence beyond its usual circles of the working class, took important root. In 1965, a new Air Pollution Act, albeit endowed with a weak means of enforcement, initiated a national framework for environmental institutionalization. By the beginning of the 1970s, states were creating new administrations that were supposed to provide answers to now widely accepted environmental problems. A flurry of environmental legislation came out of the United States, under the presidency of Richard Nixon. On December 2, 1970, in the wake of the adoption of the 1969 National Environmental Protection Act followed by the organization of the first Earth Day, Congress established the Environmental Protection Agency, EPA, whose purpose was to coordinate government action on environmental protection, set up and manage environmental standards, support research, and inform the public about risks related to pollution. The creation of a motor vehicle certification system that imposed pollution emission thresholds and the 1972 prohibition of the use of DDT, except for products intended for export, constituted a first wave of the EPA's agenda. The agency also restructured the management of watercourse pollution in order to centralize actions of public authorities to enable riverine ecological restoration. This type of public organization subsequently spread throughout the English-speaking world, where environmental protection agencies became commonplace. New ministries of the environment were created in countries around the world after 1971. They became new tools of intervention at the heart of the state apparatus. They ensured that there existed a dedicated home and central authority within states for environmental issues. The environment ceased to be torn between several competing branches of government. From this institutional base came the slow emergence of a new specific legal domain. In France, for example, the regulation of establishments requiring environmental oversight had been previously carried out by the Labor Inspectorate. Such responsibilities were entrusted to the Mines Department at the end of the 1960s before being transferred to the new Ministry of the Environment, under Robert Poujade. But many soon realized that these changes were more talk than action, and that far from breaking with previous legislation, the reforms became part of their continuity. The French law of July 19, 1976, which reformed the regime of classified industrial installations, appeared to backtrack on Labour's hard-won gains during the previous decades. The new law maintained preference for technical solutions and determined that industrial improvements adopt the best available technologies at an economically acceptable cost. Rather than punishing polluters, inspectors' powers were limited to encouraging them to modernize their production facilities, often while drawing on large state subsidies. In this respect, the new reforms marked a certain regression in French environmental legislation. Before the 1960s, Japan was a polluter's paradise, but the environmental crescendo of the late 1960s brought significant changes. In 1964, the city of Yokohama, near Tokyo, formalized emission standards with local industries, while involving the population in the development of regulation. In 1967, the governor of Tokyo set up a pollution research bureau and, in 1969, promulgated an ordinance on pollution, with even stricter standards. Pressured by social and environmental movements, the Ministry of Health recognized the industrial diseases of Minamata in 1968, which paved the way for a process of recognition of victim status. In an exceptional session of Parliament in 1970, called the Pollution Diet, 14 environmental laws were approved, putting Japan at the global vanguard of regulations against pollution. Completing the system, an environmental agency was created in 1971. 2 years later, a law on compensation for pollution-related damage, backed by significant means. In less than 10 years, Japanese legislation against pollution had radically changed perspective. Outside the industrialized world, some institutional changes occurred in countries under Western influence. In 1976, the government of Félix Houphouët-Boigny in the Ivory Coast, a former French colony that became independent in 1960, created a ministry for the protection of nature and the environment. Its existence was, however, very precarious and short-lived. In 1974, China also attempted to address its pollution problem. A body of the Council of State set targets for reducing pollution, but its success was negligible. Inasmuch as national legislation seemed to dominate environmental policy at the end of the 1960s and into the early 1970s, the fight against pollution was prominent on the agenda of international institutions at the beginning of the 1970s. Certainly, the Cold War had already inspired some actions concerning environmental expertise and standards in numerous international organizations. The WHO, for example, had been dealing in particular with health problems caused by air pollution at least since 1963. But one of the defining moments in the history of international environmental engagement came with the 1972 United Nations Conference on the Human Environment, known as the United Nations Stockholm Conference, or Earth Summit, which resulted in the establishment of the United Nations Environment Programme, UNEP. The United States was pivotal in coordinating and funding this international reconfiguration of environmental action. It insisted on making the environment a thematic, central issue in North Atlantic Treaty Organization, NATO, discussions. Research for the famous Club of Rome report was based at the Massachusetts Institute of Technology, MIT, and its American authors were leaders of that collaborative team. The United States also initiated the Global Environmental Monitoring System, GEMS, in the mid-1970s. In Europe, alongside the first dust programs of the ECSC, 1958, the Council of Europe launched several initiatives such as the Strasbourg Conference on Air Pollution, which convened in 1964, and the adoption in 1968 of the Water Charter and the first international convention limiting the use of certain toxic detergents in product maintenance. For its part, the FAO organized the December 1970 Technical Conference on Marine Pollution and its effects on biological resources and fisheries in Rome. For the first time, an international organization managed to bring together scientists, engineers, lawyers, and administrators under the same roof to discuss the problem of marine pollution. For the biologist Jean-Marie Perez, then director of the Ndoume Marine Station in Marseille and a specialist in marine pollution, this initiative showed the considerable progress made in a very short time frame, compared to the time when we considered that all that was dumped in the sea disappeared forever in its immensity, without harming anyone. The International Maritime Organization also played an important role in the adoption of the first major conventions, including the Convention for the Prevention of Marine Pollution by Dumping of Wastes and Other Materials from Ships, 1972, and the Convention for the Protection of the Mediterranean Sea Against Pollution, adopted in Barcelona in 1976. Although 20th century regulations largely followed in the spirit of those of the previous century, the new magnitude of pollutions and their increasing reach resulted in regulatory and legislative innovations to reduce nuisances. Especially after 1968, political ecology, social struggles, and the beginnings of a voluntarist international cooperation seemed to be changing the scope of environmental concerns and implementing major policies. The more systematic reprocessing of industrial wastewater made it possible to improve the ecological situation in certain rivers, such as the Rhine, and in more affluent countries, and urban pollution from sulfur dioxide undeniably decreased in cities. Yet these ecological gains were limited, tenuous, and temporary. They were also unevenly distributed. Reductions in pollutions frequently corresponded to a displacement more than real elimination. For the affluent nations, anyway, the spread of globalization became a valuable vehicle for relocating unwanted contaminants far and away from informed gazers. Britain's success in reducing sulfur pollution in the 1980s was due to the fact that Conservative Prime Minister Margaret Thatcher's neoliberal policies, which promoted free trade and import dependency, elected to abandon the coal industry as a means of weakening trade unions. During the 1970s, pollution was undeniably at the center of many debates. But, far from disappearing little by little thanks to wise regulations and technical progress, as many authorities claimed, pollutions were simply displaced, or reappeared in other forms at the end of the 20th century. Epilogue. Charging headlong into the abyss. Since the 1970s, pollution has become a fundamental category of analysis and action in contemporary societies. As political ecology has emerged, Environmental contaminations have never been as numerous as they are today, leading to major public health problems. In a world now populated by more than 7 billion people, compared to just 4 billion in the mid-1970s, who continue to consume more and more, environments and bodies are saturated with toxic substances. Nothing seems to be able to slow down this process. Today, the word pollution is omnipresent, and the semantics around the word continue to expand to keep pace with new forms of pollution. It can be light, visual, noise, electromagnetic, even mental, or genetic. Electronic mail servers are full of spam that clogs and contaminates the internet. In French, the word spam translates as pourriels, France, or pollureal, Quebec, and pollupostage has been created to describe the act of spamming. This metamorphosis of language reflects the globalization of the stakes in play. Pollutions have emerged as one of the great obsessions of our time, a near-constant and unavoidable topic in the media. Countless scientific publications now warn against the collapse of biodiversity, health risks, and global environmental imbalances. Therefore, how can it be explained that, despite pollution's full-fledged integration into the mainstream political agenda, pollutions are increasing and diversifying, and the modes of public intervention have changed so little? Faced with the many communities of experts and scientists, doctors, chemists, epidemiologists, sociologists, and geographers, who explore all the implications of the problem, what can the historian contribute? Because our historical exploration stops in the years 1970–1975, a pivotal moment in the evolution of world economic structures and the conceptualization of the environmental sciences, this epilogue will attempt to highlight the principal elements of contemporary changes. The global context has changed considerably. Exponential population growth, the rise of neoliberalism in most of the world's economies, the spread of globalization, and the unprecedented importance of finance and new information and communication technologies have induced structural changes in the industrial world, its geography, and hierarchies among sectors. At the same time, global environmental threats, such as climate warming or mass extinction of species, are changing the way we think about pollution. Figure 11.1. The Global Exchange of Electronic Waste, 2012. Source: based on Karen Lundgren, The Global Impact of E-Waste, Addressing the Challenge, Geneva, Organisation Internationale du Travail, 2012, 15. The spread of computing objects and networks is typically lauded as the triumphant condition of a dematerialized, or post-material, world that generates less pollution. However, this fallacy rests on the necessary disappearance of the increase in toxic waste that these tools create and reflects the inequality of global ecological exchanges. The waste trade is just one of the many examples that show that the burden of pollution is mainly borne by the poorest people in the poorest countries on the planet. This epilogue, which examines the present, is less intended to provide an exhaustive picture of pollution over the last 40 years. One book would not suffice, and is it even possible in so few pages? Rather, it means to reflect, with regard to history, on recurrences and inflections, volumes of contamination, and the emergence of new polluting cycles. It is clear that despite countless warnings from the 1970s, little has changed. Interest lobbies and the merchants of doubt have steadily grown stronger and more organized, creating a sclerosis of uncertainty, slowing down any effective measure. The requalification of the categories used to analyze and engage with pollutions is a first step to take into account, as well as the frenetic pace at which technology has developed over the last few decades to create new, and, as ever, unforeseen and unanticipated, risks and contaminations. But the preeminence of the old forms of pollutions, which prolong 19th-century trajectories of industrial capitalism, must also be underlined because they perpetually reiterate themselves in new places. Inasmuch as new hazards attract attention, polluting sediments cause more damage through accumulation than through substitution. In addition to the industrial and commercial lobbies, the organization of awareness and knowledge, which have never been so pointed and specialized, contributes to the confusion and reinforces this conundrum. For all its good intentions, increased specialization has meant losing sight of the forest for the trees. Could there be signs of hope for a world that would put the eradication of pollution front and center? Requalifications. Many new concepts were forged, which characterized the new period of pollution that began in the 1970s. Both French and American sociologists Alan Touraine and Daniel Bell theorized about the dawning of post-industrial societies. Others preferred the idea of postmodernity. In either case, both invoked a paradigm shift that would see the subordination of material elements to immaterial elements, knowledge and information, and the organization of the economic system through complex networks rather than pyramidal hierarchies. In Western societies subject to waves of deindustrialization and driven by the ever-increasing weight of financial services and capital gains, the concept remains highly debated. At the current juncture, the American futurist Jeremy Rifkin defends the thesis of a third industrial revolution, based on the scientific and technological potentialities of our world, for example, so-called intelligent networks, and their supposedly positive impacts on the environment. The proponents of this third industrial revolution, and all those who extol digital capitalism, start from an apparently just observation: the laws of energy govern economic activity. But the current crisis marks the loss of impetus for past energy trajectories. Fossil energy and the rare earths that drove industrial civilization's economic success are depleted. The entropic debt from these extractions, resulting from past economic activity, is accumulating much faster than the biosphere is able to absorb it. But these approaches remain locked in a somewhat simplistic vision that technology can once again release civilization from its material shackles. They testify to a refusal to see the world as a holistic unit, or to confront the heart of the productive system. Because, at the global level, it is industry's ever-growing power and importance, and its effects that must be considered. Another perspective held by the German sociologist Ulrich Beck in the mid-1980s was that of the risk society. According to Beck, where old pollutions were perceptible to the senses, but marginalized by the urgency to manage and overcome resource scarcity, new pollutions were now largely hidden from perception. While past environmental risks could have appeared as the result of a lack of technology and hygiene, now their causes were blamed squarely on industrial overproduction. Risks became a wholesale product of industrialization, and were systematically intensified as modernization became global. From Beck's risk society, we would have entered into an era of reflexive modernity, increasingly aware of the threats provoked by human action. In this reassuring reading of our time, the last decades would have seen an unprecedented awareness of the dangers of pollution and an increase in actions to confront and reduce them. But this analysis fails due to its historical myopia. The industrial and techno-scientific changes of the past 2 centuries have not been unconscious. Warnings and debates have continued to accompany them. Our contemporaries favored industrialization and power despite their inherent risks and threats, and at the cost of environmental pollution. History shows how much environmental reflexivity was already present in previous centuries, while recent periods largely belie the hope that a new technological democracy might be found to solve its deleterious effects. To reconcile industrial growth and pollution control, the concept of sustainable development has been coined. The term appears to have been used officially for the first time in the 1987 United Nations report drafted by the Norwegian Gro Harlem Brundtland, but the concept had already been debated for several years in environmental circles. It appears as early as 1980 in a joint report by UNEP and the World Wildlife Fund, WWF. Sustainable development must respond to the needs of the present, without compromising the ability of future generations to meet their own needs. It offers a wide vision in which everyone can recognize themselves, but it is also a kind of paralyzing oxymoron. A propaganda tool for companies engaged in greenwashing, sustainable development is also regularly invoked by policymakers whose rhetoric lauds the virtues of compromise while cloaking their decisions in actions that are hardly ecological. As a result, the concept is often heavily criticized. Where sustainable development represents the model of good governance intent on reconciling ecology and capitalism, it in fact resembles more and more an empty promise used to maintain the status quo. It is in this context that the most important contemporary requalification of pollutions emerges around climate issues and debates. Indeed, the study and profiling of pollutions is now evolving in a world where global warming has emerged as the ecological emergency of primary significance. The greenhouse effect provoked by atmospheric gases, already brought to light by the French physicist Joseph Fourier in 1824 and which Arrhenius had hypothesized was exacerbated by carbon dioxide, 1896, began to mobilize the community of scholars in the post-war period. Consensus around the possibility that the large-scale combustion of fossil fuels could dramatically disrupt the planet's climate gradually emerged. Therefore, this harmless gas, even beneficial for the growth of plants, entered into the spectrum of polluting substances. In 1965, a report submitted to the American President Lyndon Johnson on the risks associated with increased pollution pointed to the responsibility of human activities for CO2 emissions. 10 years later, one of the report's authors, the American geochemist Wallace Broecker, announced in the journal Science the imminent eruption of global warming. His article predicted that the symbolic CO2 threshold of 400 ppm would be reached in 2010. At the time, global CO2 levels were at 330 ppm. Broca was not far off. 400 ppm was reached in 2013, an increase as important as that calculated for the period 1750–1975. Broca also believed that the present trend will, within a decade or so, give way to a pronounced warming induced by carbon dioxide. The expression, global warming, was subsequently challenged. For some it was too blunt in blaming human actions for climatic harm. For a few years, the National Aeronautics and Space Administration, NASA, preferred inadvertent climate modification, which allowed the phenomenon to be euphemized. In 1979, UNEP and the World Meteorological Organization, WMO, considered the situation to be of sufficient concern to convene the first World Climate Conference in Geneva. What followed was the launch of a global research program involving the largest international scientific bodies. Experts began to demonstrate the correlation between rising temperatures and CO2 levels and other gases such as methane, CH4. On June 23, 1988, as the United States was overwhelmed by a scorching early summer, James Hansen, director of a NASA lab, testified in front of a U.S. Senate committee, and declared that global warming was not caused by the natural variability of climate but by human activities. He added that the trend was expected to increase, and that he was 99% sure of his claims. The climate issue was born. In the same year, at the G7 summit in Toronto, the concept of sustainable development was adopted and the Intergovernmental Panel on Climate Change, IPCC, was created. Consequently, many diplomatic negotiations were established to understand and stop the phenomenon. The United Nations Framework Convention on Climate Change, UNFCCC, was adopted in 1992 at the Earth Summit in Rio de Janeiro. That framework culminated in 1997 with the drafting of the Kyoto Protocol, which was supposed to reduce emissions of anthropogenic greenhouse gases to 1990 levels. Now meeting under the Conference of the Parties, COP, these major international meetings have consistently failed to install restrictive devices. If the 2015 Paris Conference, or COP21, realized agreement and common cause amongst nations around a minimum agreement, none managed to significantly slow the increase in the concentration of greenhouse gases entering the atmosphere. The debates focused first on the reality of the phenomenon, then on the question of whether or not greenhouse gases should be considered as pollutants. The controversy was particularly acute at the beginning of the 21st century, pitting climate scientists against climate skeptics, environmental groups against oil lobbies. Many studies show how climate skepticism was bought and paid for, subsidized by the petroleum and coal industries, or closely linked to conservative think tanks. Some of its authors were former confederates of the tobacco and chemistry industries, commissioned to minimize the dangers of their products. As professional doubt merchants, they artificially maintain public ignorance in order to prevent any measure of reduction in greenhouse gas emissions. Obfuscating over whether or not carbon dioxide is a polluting substance, they have gained traction in grinding climate action to a relative halt. In the fight against real pollution, and because CO2 is vital for plants, the Belgian chemist Istvan Marco stated that CO2 is neither a poison nor a pollutant. It has never been and never will be. Conversely, climate specialists and environmental movements claim it is the major source of pollution of the industrial age. The WHO, for its part, endorses the notion of climate pollutant for CO2 insofar as, beyond a certain threshold, it contaminates the environment and modifies the chemical composition of the atmosphere, resulting in health effects and ecological imbalances. As the case of greenhouse gases shows, the boundaries that define what are considered pollutions are, more than in the past, porous. For example, chemical contaminations, with poorly understood cumulative effects owing to the longevity of their molecular makeup, are on the rise. Not only are yesterday's persistent organic pollutants still widely present in the environment, such as DDT or lindane, another organochlorine-based insecticide, but hundreds of thousands of new ones continue to be marketed. But how to evaluate the extent of pollutions, or evaluate changes when scales of contamination and contextual situations are so diverse? And how to evaluate effectively when every indicator hides as much as it reveals? Contrary to previous centuries mentioned in this book, fumes and blackened waters, perceptible by the senses, no longer constitute the most dangerous pollutions. Instead, the innumerable complex molecules whose minute doses and uncertain effects are more difficult to spot pose the more significant threat. According to the toxicologist Andrei Ciccolella, the proliferation of synthetic products, developed to meet uses as diverse as cleaning and cosmetics, produces an invisible scandal of chronic diseases. Endocrine disruptors serve as a useful illustration of this process of the contemporary requalification of pollutions, just as they highlight certain continuities in the apprehension of toxic substances. In her 1996 survey, Our Stolen Future, the American zoologist, epidemiologist and environmental activist Theo Colborn theorized and popularized the notion of endocrine disruptors to refer to any molecule or compound chemical agent that upset the hormonal system, resulting in abnormalities. Through her work, Colborn was especially concerned about such impositions on the reproductive system. Our Stolen Future asks, what if pollution made people less intelligent? Colborn suggested that the effect of chemicals on hormones could lead to concentration difficulties for children and even forms of aggression and violence. This type of warning, initially rejected as part of a catastrophist imaginary or socio-biological drift, and condemned as a form of demagogic dramatization, likely to drown the real issues, nevertheless managed to play an important role in the redefinition of chemical pollutants at the end of the 20th century. Poison is a little too black and white as a descriptive term. These new hazards are substances that can disrupt the body in subtle, discrete ways. The presence of endocrine disruptors in products as abundant as pesticides, plastics, and certain car emissions made them a public health problem, especially since they made clear that dose or exposure level was no longer the central metric for ascertaining harm. A very small dose could have a major effect. Epidemiologists and public health workers also needed to determine the moment of exposure, especially in utero, and the prospect of multiple exposures and their famous cocktail effect. In the very wide range of these new compounds, bisphenol A, synthesized at the end of the 19th century but mainly used by the plastics industry after the 1960s, offers an exemplary case. Now mass-produced, 6 million metric tons a year, it is used in the manufacture of plastic and is found in many products of everyday life, from sunglasses to CDs to baby bottles. At the beginning of the 21st century, doubts began to circulate about exposure to low-dose bisphenol A. More in-depth studies and research led to Canada banning it in baby bottles in 2008, followed by a European directive in 2011. After bisphenol A, pH phthalates became the new focus of attention. More than 3 million metric tons are produced each year around the world. These synthetic molecules are present in plastics, cosmetics, paints, and clothes, among others. Some of them are highly toxic to human reproduction. More and more surveys confirm how invisible chemical contaminations at low doses are dangerous. After the reproductive system, they could affect the brain and damage cognitive and cerebral faculties, especially in children. Dioxin contamination also reveals new ways of understanding pollutions. Although already present during the Vietnam War, the issue of dioxins made a sensational debut in the public sphere with the Seveso disaster in 1976, when a toxic cloud escaped from a reactor of the Icmesa chemical plant, which manufactured trichlorophenol. The cloud spread across the Lombard Plain in Italy. Locals experienced immediate health problems, including skin disorders such as chloracne. As well, 20,000 hectares, about 49,000 acres, of soils were contaminated, and 80,000 poisoned cattle had to be slaughtered. Dioxins are persistent organic pollutants that remain in the environment for many years. Considered as carcinogenic substances by the WHO, the dioxin family actually comprises several hundred different molecules, about 30 of which are particularly toxic. They are manifested during thermal processes, which is why they are regularly found in higher concentrations around incinerators. Apart from accidental causes, dioxins infiltrate the food system, accumulating especially in animal fats. Since the Seveso accident, many cases of dioxin pollution have hit the headlines. The case of the dioxin drums at the Ciba chemical plant near Basel, Switzerland, 1982-1985, cow's milk containing dioxins around an incinerator near Albertville, France, 2001, contaminated greases delivered to feed producers in Germany, 2011, and so on. Although dioxins are produced locally, they are spread all over the planet and are particularly concentrated in PCBs, whose pollutants are also recurrent due to the large quantity of stocks that require disposal. Invisible molecules, biotechnologies, and digital worlds. The dispersion of invisible contaminants into the environment did not only come from innumerable chemical molecules, but also from new genetic, nano, and digital technologies. Often presented as solutions to the pollution of the old industrial world, the new technological regimes that emerged at the end of the 20th century in reality introduced a new series of polluting cycles. Thus, from the 1980s, the first genetically modified organisms, GMOs, that is to say, whose genetic heritage is modified by human intervention via transgenesis or insertion into the genome of one or several new genes, were developed by industry and seed companies, including Monsanto, in the name of the fight against world hunger and agricultural pollution. Since certain GMOs were designed to include pesticide substances, their adoption was supposed to lead to a more tempered and rational use of insecticides and herbicides. After the first transgenic plant was obtained experimentally in 1983, an herbicide-tolerant plant appeared in 1987. In 1990, the first transgenic plants were marketed. At the end of the 1990s, nearly 40 million hectares, about 99 million acres, of transgenic plants were cultivated worldwide. Transgenic-based agriculture expansion accelerated despite regulations and numerous controversies. By 2006, 102 million hectares, about 252 million acres, were cultivated, with nearly 200 million hectares, about 494 million acres, 10 years later, especially in the United States, Argentina, Brazil, India, and China, where GM fields have reshaped agricultural models. Because of cross-pollination from genetically modified plants that transmit their new genes to neighboring non-transgenic plants belonging to the same species, it is possible to speak of genetic pollution. In Canada, for example, there is almost no natural, uncontaminated rapeseed in cultivation. Touted as rational, technical solutions to fight against the use of chemicals, genetically modified plants ended up producing quite the opposite effect. Because many GMOs are specially designed to resist herbicides, which makes the spraying of fields with chemicals less problematic, more, rather than fewer, chemical applications took place. New generations of GMOs produced drought-resistant plants, or trees with a modified cellulose-lignin ratio to meet the needs of biorefineries and the paper industry. GMOs ushered in a definitive spectre of boundless proliferation, threatening to add to the old, grey pollution, industrial pollution, and augmented, green pollution, genetic pollution, leading to more controversy and resistance around these new products. With nanotechnology, a term coined by the Japanese physicist Norio Taniguchi in 1974, which produces elements less than 1/1,000,000th of a millimeter, the order of magnitude of the distance between two atoms, and therefore smaller than cells, it is their size that becomes a source of pollution. At this infinitesimal level, biological barriers are easily crossed, a property currently exploited by the cosmetics industry. Nanotechnology emerged in the late 1980s, and followed a development parallel to that of GMOs, both chronologically and epistemologically. Obtained through molecular manipulation, these nanomaterials posed fundamental ethical questions. Many nanomaterials were recognized as toxic, inducing oxidative stress, cytokine inflammations, and cell necrosis. In addition, they could be absorbed by mitochondria and the cell nucleus. As a result, they could cause DNA mutations. In addition, by incorporating these minute metal particles into products without any hope of recovering or recycling them, there is no way to know where they will end up. For example, nanosilver contained in clothing for its antibacterial properties was leached into the environment when laundered, without any means of recovery. Worse still, titanium nanoparticles are ingested, since they are a food additive, E171, that whitens yogurt and adds shine to confectionery. Since 2007, a journal dedicated to these new risks, Nanotoxicology, has appeared regularly. Beyond these controversial pollutions, the incessant production and renewal of high-tech objects has increased pollutant waste and new, more or less hidden nuisances. These new digital tools, now ubiquitous, promise to open an era of less polluting practices by promoting the dematerialization and pooling of certain services, such as carpooling, but they have actually caused many side effects whose study has only just begun. Electromagnetic pollution, electrosmog, is recognized by many experts. Electromagnetic fields produced by mobile phones and relay antennas are classified as possible carcinogens for humans by the International Agency for Research on Cancer, IARC. In May 2015, 190 scientists from 38 countries called on the UN and the WHO to take measures to limit exposure, confirming the reality of the phenomenon. Public authorities, however, felt reassured that monitoring emission norms and exposure thresholds would suffice to continue expanding the new digital world's reach and access. No prospect of restrictions was ever seriously envisaged.
Computers were virtually non-existent in 1970 but have now invaded the daily lives of the majority of the world's population. It would be a mistake to consider this an immaterial phenomenon because the computer is first and foremost made of silicon, plastics, and metals. Life cycle specialists of material goods have been trying to assess how much energy and resources are needed to produce electronic readers, smartphones, and computers, which in a few short years have become mass consumer goods, and how much toxic residues they produce. The number of mobile phones, first created in the United States in 1983, increased from 300,000 in 1985 to more than 200 million in 2006. Smartphones, virtually non-existent at that time, are growing at an even more dramatic pace. 1.5 billion units were sold worldwide in 2016. To produce these quantities, the electrical and electronics sector consumes 12% of global gold demand, 30% of silver, 30% of copper, and up to 80% of rare metals such as ruthenium or indium, whose extraction and refining cause significant environmental damage. Some sectors, such as coltan, tantalum ore, feed wars in Africa, while rare earths, a group of metals with electromagnetic properties, such as scandium and yttrium, require removing vast quantities of the Earth's crust for their extraction. China currently dominates global production, resulting in the local release of many toxic elements, such as heavy metals or sulfuric acid, as well as radioactive elements. In mining sites, cancer incidence can reach 70%, all while local agricultural yields drop. For example, in Baotou, the rare earth capital, factories process 70% of the world's production and dump thousands of liters of toxic waste into a lake that today extends over 10 square kilometers. Another facet of the digital world's pollutions that should be taken into account is the industry's energy consumption, which is already reaching the levels of air transportation. While the equipment's energy efficiency is progressing, like 19th-century furnaces, the rebound effect offsets any positive results. The exponential growth of data production and the proliferation of screens and general digital usage are increasing the demand for energy and the consumption of materials. Moreover, data centers consume massive quantities of energy to process queries and run data storage servers, which need to be constantly cooled, which also consumes energy. In France, data centers consume 10% of the country's electric energy. Though individual usage may seem trivial, a simple internet request on Google equals the consumption of a 12-watt light bulb for 2 hours. Sending a 1 megabyte attachment to 10 correspondents requires the energy needed to move a car 500 meters. In an hour, around the world, 10 billion emails are sent, which corresponds to 50 gigawatt-hours, or 4,000 Paris-New York round trips by plane. Waste from cutting-edge technology has also become a significant source of ecological pollution and exchange which is unequally distributed around the world. Debris from the conquest of space also deserves mention, albeit, unfortunately, much too briefly. Since the launch of the first satellite, Sputnik 1, by the USSR in 1957, the number of objects sent into space has skyrocketed, especially since the 1980s with the rise of telecommunications. They are either left to drift in orbit around the Earth, unwanted satellites traveling at nearly 30,000 kilometers per hour, or they eventually fall back to Earth. According to NASA, in 2013 these debris consisted of 29,000 objects of more than 10 centimeters, 670,000 of more than 1 centimeter, and 170 million objects that were more than 1 millimeter. At the 7th European Space Debris Conference held in Darmstadt, Germany from April 18 to 21, 2017, scientists once again expressed concern about the significance of this debris, which poses safety problems because of collision risks. High-tech waste is mainly the result of daily consumption. Due to the constant renewal of equipment and its increasing obsolescence, 750 million mobile phones are discarded each year. The amount of electronic waste has been growing at a steady pace of between 3% and 5% per year since the 1990s. This waste contains compounds that are extremely toxic to human health and the environment. Mercury, lead, cadmium, and cyanide, for example, are all present, and the workers responsible for their disposal or recycling are particularly exposed. For example, it is estimated that the 315 million computers that became obsolete between 1997 and 2004 contained more than 500 million kilograms of lead. The recycling of this waste is the subject of international trade, described by some as toxic colonialism. Waste, which comes from electronic devices that are mainly used by consumers in rich industrialized countries, is sent to Asia, Africa, and Latin America for recycling or storage in landfills that cause significant pollution. In 2007, nearly 80% of US computer waste was exported to Asia. While the Basel Convention, signed in 1989, and ratified by nearly 190 countries, but not the United States, officially bans this traffic, millions of metric tons are transported each year to open dump sites, such as those in the suburbs of Accra, the capital of Ghana, as recently filmed by German documentarian Cozy Madanoritza in the E-Waste Tragedy, 2014, the tagline for which asserted that the illegal recycling of electronics is a toxic business on a global scale. China and India are currently importing most of the world's electronic waste. The Giyu dump site, opened in the late 1970s, is now the largest in the world. In 2005, it employed 100,000 people, but that number has undoubtedly grown since then. Many environmental organizations denounce these pollutions and the social, health, and environmental ravages they cause. These waste sites, though, serve as symbols of a globalization of pollution and hardening of environmental inequalities in recent decades. Globalization and unequal ecological exchange. Unequal exchange and expanding transfer distances have continued to be a part of polluting dynamics. With globalization, the process has become even more entrenched and compounded. As a result of globalization's new mobilities and their capacity to radically alter the scale of these transfers, it is now possible to speak of an unequal ecological exchange on a global scale. In the cities of the global north, it is undeniable that the atmospheric concentration of certain well-known molecules, such as sulfur dioxide, carbon monoxide or lead oxides, has decreased. Such successes have reduced the volume of acid rain. On the other hand, emissions of nitrogen oxides and sulfur dioxide have increased significantly elsewhere. In China they are nearly 10 times higher than in developed countries. And while fine particles have increased everywhere, especially because of automobile traffic, this increase is mainly affecting the countries in the global south. Historical analysis shows that the new pollutions of the so-called post-industrial world constitute additions, rather than substitutions for older contaminants, to the planet's pollution burden. The notion that new, post-industrial technologies and their pollutions work as improved substitutions comes from a form of myopia induced by globalization that unevenly redistributes risks. Globally, lifestyles the world over demand ever more resources, in spite of the considerable disparities between countries and social groups. Emerging economies, and their hunger for the resources and affluence enjoyed by the globe's fortunate haves, demonstrate this uncontrollable snowball effect on the world system's horizon. Each year, the symbolic date of exceeding the threshold for the consumption of resources that the planet can renew comes a little earlier. According to the current calculation method, the Earth's biocapacity was exceeded in 1976 on November 19, it came on October 25 in 1986, October 4 in 1996, August 24 in 2006, and August 8 in 2016. If all humans lived as the inhabitants of Australia, it would take 5.5 Earths to provide for their needs, 3 Earths if they lived as in France, 2 Earths if they lived as in China, and 0.7 Earths if they lived as in India. In cities in the north that are heavy consumers of goods and services, infrastructures are sufficiently developed to evacuate waste and provide a degree of urban hygiene, which leaves the impression of a world without pollution, even though consumption is based on a productive chain, including mines, transport, and industry, that causes many contaminations. At the other end of the chain, there are still shanty towns, where about 1/3 of the world's urban population lives, far more than in the 1970s, and where countless modern proletarians live in and with wildly insalubrious conditions. The lack of sanitary infrastructure, the pervasiveness of toxic industries, and uncontrolled car traffic defy imagination throughout Central Asia and Sub-Saharan Africa. At the beginning of the 21st century in a megacity of 10 million inhabitants like Kinshasa, there is no mains drainage. In Manila, only 10% of dwellings are connected to it. Mike Davis observes that most of the big cities of the Third World have a Dantesque district of slums shrouded in pollution and located next to pipelines, chemical plants, and refineries. Mexico's Iztapalapa, Sao Paulo's Cubatao, Rio's Belford Roxo, Jakarta's Cebubo, Tunis's Southern Fringe, southwestern Alexandria, and so on. The discharge syndrome, which characterized many 19th-century industrial cities in Europe, existed on a considerable scale in the global South slums in the 1980s. In a Bangkok shanty town, chemical plant explosions in 1989 and 1991 caused the deaths of hundreds of inhabitants and extensive pollution. The city of Cubatao, near Sao Paulo,
constructed on ancient banana plantations, reached 100,000 people in the early 1980s and was home to huge industrial complexes that produced nearly 40% of the country's steel and fertilizers. It became a valley of death. The infant mortality rate was 10 times higher than the rest of the state. Soot and suspended particles were so prevalent that birds and insects simply disappeared and vegetation died inexorably. Recently, however, the situation has begun to improve. For much of the current pollution regime, China, the new workshop of the world, provides a terrifying illustration, demonstrating that the old pollutions inherited from past practices have not disappeared. In just a few years, the country has become the most polluted in the world. In 1979, China launched the socialist market economy and opened up to international trade. It engaged in rapid industrialization, particularly in labor-intensive industries such as textiles and low-quality manufactured goods. Its growth rate was close to 10%, and the special economic zones, SEZs, offered multinational companies tax incentives and low-cost docile labor that instigated a massive relocation of production to these territories. The social and ecological cost was significant. China accounts for nearly 40% of global coal consumption per annum, which supplies 68% of its energy needs and 80% of its electricity. In 2008, the country became the world's largest emitter of greenhouse gases, responsible for nearly 23% of total emissions. In industrial areas, coal pollution became so bad that it caused serious health problems, rendered agricultural land sterile, and forced the authorities to displace the population. In 30 years, China's industrialization and agricultural modernization has contaminated 20% of its arable land, or 20 million hectares, about 49 million acres, and 40% of its rivers. Some 300 million rural people consume water with heavy metal levels dangerous for health. Air pollution is just as dramatic. Acid rain is increasing, and incidences of lung disease are off the charts, a situation that could kill 1.6 million people every year in the country. The media regularly reports on the magnitude of the smog and the distress of the population in the face of what is regarded as an uncontrollable phenomenon. Even the Chinese Ministry of the Environment admits the extent of the problem. In 2013, after the ministry ignored journalist Deng Fei's map of the main polluted sites in China, it published a list of contaminated villages where the proportion of people who were sick, especially with cancer, was particularly alarming. There were nearly 450 such cancer villages, all located in industrial areas. Beyond China, the whole of Asia is the victim of massive pollutions caused by continuous industrial expansion. Since the 1990s, global coal consumption has steadily increased, particularly because of the construction of electric power plants. By 2013, the Asia-Pacific region was billowing more than two-thirds of the 36 billion metric tons of carbon dispersed into the atmosphere by the burning of coal and hydrocarbons, a doubling since 1975. The so-called Asian brown cloud, a huge sheet of soot particles and polluting gases produced by industry, road traffic, and also agricultural practices such as slash and burn and waste incineration, has been a prominent feature of satellite photographs for 20 years. It is arguably the largest pollution in the world, extending from Pakistan to India and China, disrupting the local climate and threatening already fragile populations. Water pollution is another major problem in the region. Large dams, such as the Three Gorges on the Yangtze in China, overconsumption, and massive agricultural and industrial waste emissions result in river salinization and pollution. Since 2007, the American NGO Pure Earth has published a list of the most polluted sites in the world. Sub-Saharan Africa and Southeast Asia consistently rank first as the most contaminated regions. The relocation of wastes and pollutions to southern countries goes hand in hand with the uneven distribution of risks. One such example was a large pesticide factory built in 1978 in Bhopal, the capital of the Indian state of Madhya Pradesh, with a population of 300,000 and located 600 kilometers south of New Delhi. In 1984, following a series of technical failures, a toxic cloud escaped and spread over an area of 25 square kilometers, causing thousands of deaths and hundreds of thousands of illnesses. More recently, fires in textile factories in Bangladesh and Pakistan have resulted in hundreds of casualties, demonstrating the inadequate security conditions in these countries. In China, there was a 98% increase in industrial accidents between 2010 and 2013, especially in mining. In order to fully grasp the magnitude of regional differences in terms of pollution and risk, it is necessary to distinguish between places of consumption and places of production, especially since a large part of the toxic production in the south exists to meet the demand from rich countries. In other words, it is necessary to refine the analysis according to social classes and their consumption patterns, thus shifting the blame for the causes of pollution solely from emission sources to include the consumerist practices that inspire them. Consumption is the real source of industrial pollution. As journalist Hervé Kempf notes, it is the rich who destroy the planet and externalize the damage. If China has become the world's leading polluter, it is because it has transformed itself into a huge workshop serving the consumers of the North. Its toxic productions are the result of meeting the needs of North American and European consumers more than from satiating its own domestic market. The outsourcing of pollution is particularly apparent in the treatment of waste. Even if it was practiced before, the 1970s saw the export of hazardous waste become a truly international activity. Mexico began to accommodate American waste on a massive scale, Southeast Asian countries agreed to stockpile waste from Japan, and Morocco and some other African countries received waste from Europe and the United States. By the end of the 1980s, the international trade in toxic waste amounted to millions of metric tons per year. Some cases illustrate this phenomenon, and some of them are difficult to believe. In 1987, for example, the media reported on a barge loaded with residues from a toxic incinerator in the United States that was sailing aimlessly around the Atlantic for lack of a country ready to receive it. Such incidents, accompanied by pressure from various protest movements, spurred the first protocols and conventions aimed at regulating this toxic and illegal trade. Yet, as with computer and electronic equipment residues, exports from the north to the south continue to grow at a steady pace, even though most of the recipient countries do not meet the sanitary standards that are in place in the countries of origin. Thus, a blatant, worldwide environmental injustice, which is even explicitly criminal in the case of some banned poisons in developed countries, is being promoted. This was the case, for example, in Côte d'Ivoire in 2006 during the Probo Koala disaster. The Probo Koala was an oil tanker belonging to Trafigura, which transported 581 metric tons of highly toxic hydrocarbon wastes, a mixture of petroleum, hydrogen sulfide, phenols, caustic soda, and organic sulfur compounds, to the African coast. The cocktail of contaminants produced deadly gases. Tens of thousands of people were poisoned. More generally, the toxic exchange is more mundane. Diesel fuels sold on the African continent are much more toxic than those in Europe, even though it is Western petrochemical companies that organize this trade. Thus, most developed countries continue to favor, as in the past but on a whole new scale, the outsourcing of pollutions, via the relocation of the most polluting factories or the export of dangerous substances, without ever calling into question the potential impact elsewhere. Out of sight, out of mind. The transport revolution made possible by gigantic container ships enables this type of global traffic, while itself becoming a source of pollution through its diesel consumption or the abandonment of ships in southern countries. Whether it is the highly polluting activity of tanning or heavy industries such as metallurgy, polluting factories have left Europe for countries with less stringent environmental, health, and labor regulations. The whole world is now organized to manage this differentiation of risk and the ecological inequality of global production. The problem of environmental injustice has been renewed on a global scale. Recrudescence of an energy-consuming industrial world. The new types of pollution and the new logic behind where to locate polluting industries did not replace the old dynamics, they added to them. Even today, it must be remembered that most of the electricity produced in the world still comes from fossil fuels. 40% of electricity is still produced from coal and about 75% of coal is used for electricity. Coal remains a major fuel, especially when the price of oil starts to climb. For its part, nuclear energy was called into question after the Fukushima accident in 2011. Coal remains the basis for industrial development in China and India. The extraordinary growth of India's coal exploitation has left ecologically ravaged enclaves in its wake, destroyed forests, ground subsidence, air and water pollution. In the Meghalaya basin, the multitude of artisanal mines, dubbed rat holes, are worked by migrant workers from Bangladesh and Nepal. Here too, the land is devastated by this exploitation. Despite the development of renewable energies, regardless of their permanent growth, neither coal nor oil production has declined. Indeed, the contrary is true. Rather, since the 1990s, the exploitation of oil sands and shale gas deposits have become prominent features of the global energy regime. With the depletion of oil reserves, the exploitation of these unconventional hydrocarbons has become financially attractive, even under conditions previously considered difficult. Oil sands in Canada, Venezuela, and Madagascar are driving a relative boom of activity. Exploitation of the northern Alberta, Canada, oil sands began in 1967, but production accelerated markedly after 2002. The oil, or tar, sands are composed of a mixture of sand, water, clay, and crude bitumen, whose extraction causes much greater environmental damage than conventional oil. To extract the pure material, it is necessary to heat the bitumen with solvents. The surrounding region is literally devastated, and doctors have noted the appearance of rare cancers. Shale gas, which is a natural gas contained in clay layers rich in organic matter, can only be exploited by hydraulic fraction that requires the injection of water at high pressure and various chemical additives, including lubricants, biocides, and detergents. Its large-scale operation began in the 2000s, especially in the United States. In addition to groundwater contamination, it is also an industry that emits high levels of greenhouse gases while adding to seismic risks. The American landscape is now dotted with areas polluted by this exploitation, especially in the pioneering states of North Dakota and Montana. This extension of the hydrocarbon range does not detract from the more traditional oil pollution. The years 1975-2000 were marked by major oil spills, which led to increased regulations on supertankers and the containment of their cargoes. Double hulls became mandatory. Accidents were often highly publicized. The Torrey Canyon in 1967, the Amoco Cadiz off the coast of Brittany in 1978, 223,000 metric tons, and the Exxon Valdez off Alaska in 1989, 37,000 metric tons of oil spilled. Many other, less publicized accidents occurred off the African and Latin American coasts with even greater spills. For example, in Trinidad and Tobago the Atlantic Empress spilled 280,000 metric tons in 1979, the Abd Summer in Angola lost 260,000 metric tons in 1991. There is a long list of such accidents, which should not overshadow the chronic, much larger volume, estimated by the WWF at 4.5 million metric tons per year. In addition, leaks or accidents on platforms or oil fields are widespread and frequently underreported. The 2010 explosion of the Deepwater Horizon oil platform, operated by British Petroleum in the Gulf of Mexico, caused the worst oil spill in history. 835,000 metric tons of oil escaped into the waters, and contaminated more than 2,000 kilometers of coastline. Less publicized, because it remained largely invisible, a huge methane leak from the Southern California Gas Company near Los Angeles at the end of 2015 also reflected the fragility of energy infrastructure. Similarly, some landscapes were affected by chronic leaks and releases that destroyed whole regions, such as the Niger Delta in Nigeria. War-related oil spills are also common, particularly those affecting the Near and Middle East region since the 1980s, the Iran-Iraq War from 1980 to 1988, the First Gulf War in 1990-1991, the invasion of Iraq by US-led troops in 2003, and ongoing conflicts in Syria and the Middle East. For example, in 1991, when it withdrew from Kuwait, the Iraqi army sabotaged a large part of the country's oil wells. More than 1 million metric tons of oil spilled into the sea, precipitating immense contamination of coastal areas and significant health problems for the populations. The oil boom is still current, and it feeds the ever-growing petrochemical industry, a part of which is plastics. If plastic consumption has shown signs of stagnating in Europe, it has exploded around the rest of the world. Less than 50 million metric tons of plastics were manufactured each year in the late 1970s. 40 years later, that number has swelled to more than 300 million metric tons. Millions of metric tons end up in the oceans. This undecomposed waste constitutes the origin of the vast, plastic continent, which obviously is no continent at all, discovered in the 1990s, and dubbed the Great Pacific Garbage Patch. When he made his documentary about the Pacific Ocean's Midway Islands, Midway Journey, 2011, one of the most isolated archipelagos in the world, photographer Chris Jordan was struck by the amount of plastic waste that was there. It was responsible for high incidences of albatross mortality. The birds ingested the plastics. He returned with photographs that caused stupefaction, birds, whose entire innards were filled with plastic detritus. More worryingly, the ocean is now shrouded, up to 10,000 meters deep, with persistent organic compounds, such as PCBs, and plastic microparticles that are undetectable to the naked eye. The latter come from the residues of laundering synthetic fiber clothing, and brake wear and car tires. The contemporary extraction of metalliferous resources follows the same trajectory as hydrocarbons, as it continues to grow in tonnage. However, mining excavation requires digging ever deeper for fewer rich mineral deposits. For example, for copper, the average metal content in the ore dropped to 0.5% at the beginning of the 21st century, and this downward trend is consistent with all metals, resulting in more aggressive extraction processes employing stronger chemicals and greater energy expenditure. Mining is completing the economic colonization of the world. Inside the Arctic Circle, the Soviet exploitation of nickel and apatite, a type of phosphate, has resulted in extreme levels of pollution that continue to increase with the Russian productivist frenzy. Mercury and methylmercury are released with the tailings, and at levels that endanger the health of Inuit populations and threaten several marine species. Even some of the most remote places on Earth are now contaminated, although they have never contributed to this pollution. Since it is not possible to review all the metals, a survey of aluminum might suffice as an illustrative example. While this sector was sometimes presented as clean after 1980 because of the adoption of new pollution controls, the ecological ravages have continued, and have spread internationally. Releases of red mud from alumina production regularly trigger large-scale disasters, including at old sites such as Gardan, which is still contaminating the Kalincs National Park. This is also the case in Hungary, where as a result of the collapse of one of the basins, the Oiko aluminum plant released 1 million cubic meters of red mud in 2010. This plant was established in 1942 by the Nazis, privatized in 1993, and employed 1,100 people at the time of the accident. Dust is another polluting, long-term byproduct of aluminum's production. As is often the case, it is an industry that is becoming more international. Aluminum operations are beginning to be outsourced to poor countries, where the risks are less visible. Aluminum production has grown considerably in Africa, Cameroon, Ghana, Guinea, South America, Brazil, Jamaica, Suriname, India, and China, which, along with Russia, has become a world-leading producer. In 2015, the Rio Doce disaster in Brazil, one of the worst in the history of the country, created a toxic mudslide that spanned 500 kilometers. Tens of thousands of retention ponds where extractive waste was stored threatened to contaminate the environment and destroy the lives of local residents. In the agricultural sector, the cycle of chemical pollutions also continues to spread, leading to accelerated soil degradation and declining yields. The quantity of chemical fertilizers used in the world rose from 30 million metric tons in 1960 to 150 million metric tons in 1990, and 175 million metric tons by 2011. An increase that mainly occurred in Asia, plus 450% between 1970 and 2000, South America, plus 200%, and Africa, plus 100%. Similarly, in countries that were already committed to chemical agriculture, the quantities of pesticides consumed did not decrease between the 1980s and 2010, but rather tended to stagnate or even increased slightly, despite considerable regional fluctuations. In 2007, 2.5 million metric tons of pesticides were consumed worldwide, even though the efficacy of the products used had increased significantly, by a factor of 10 compared with 1945, meaning that in fact 10 times less was needed to produce the same effect, but this was clearly not the case in practice. Europe consumes 3.9 kilograms per hectare, about 3.5 pounds per acre, compared with an average of 1.5 kilograms worldwide. At the beginning of the 21st century, and mainly on the strength of its vineyards, which were a major consumer of herbicides, insecticides, and especially fungicides, France remained the world's third largest pesticide user with about 110,000 metric tons per year, behind only the United States and Japan. Committed to the Green Revolution, many countries in Asia, Africa, and Latin America modernized their agriculture by adopting high-yielding plants that required more fertilizer and pesticides. Between 1972 and 1985, pesticide imports increased by 261% in Asia, 95% in Africa, and 48% in Latin America. Asia was still a small consumer before 1970, but it became an important outlet for large international groups that set up factories with the support of authorities who promised loose regulatory oversight. While some agricultural chemicals were progressively banned, many other substances were introduced during the 1970s and 1980s. Pyrethroids, then atrazine, finally banned in France in 2002, and neonicotinoids,
which affect the central nervous system of insects, gaucho, produced by Bayer, for example, which was partially banned in France in 2009, as well as systemic, or total, herbicides whose active substance is glyphosate. The best-selling glyphosate in the world is Monsanto's Roundup, marketed since 1975, although relicensing of its use is currently under discussion in the European Union. At the same time, new techniques, such as seed coating, allow permitted substances to become increasingly invasive. The situation seems more ambiguous than ever. Pesticide use in France has become much more stringent. Aerial spraying is strictly controlled, and on January 1, 2017, local authorities banned the use of chemical sprays in public spaces. After 2019, pesticide products will no longer be sold to individuals. However, in spite of the progress of organic farming, agriculture at large remains dependent on pesticides whose consumption continues to grow each year, by nearly 6% between 2011 and 2013 and 9% in 2014, according to the official statistics of the Ministry of Agriculture. Demand for fossil fuel energy for transportation has not decreased either. Since the 1970s, modes of transport have steadily multiplied and the global ecological footprint of the automobile continues to grow. In this sector, the question of pollution is still mainly thought of in technical terms. References to clean cars, for example, despite the strong criticisms castigating automobile civilization formulated since the 1970s. In France, the number of cars grew from 24 million in 1985 to 38 million in 2015. Around the world, nearly 100 million vehicles are produced a year, mainly in China, the United States, Japan, and Germany. 1 billion cars were in circulation in 2010. According to a French free newspaper, one mainly subsidized by advertisers, current trends indicate that this number could swell to 1.7 billion by 2035. The article concluded that the car must remain an irreplaceable instrument of freedom of movement and that, made cleaner, smarter, more efficient, and possible to share, it will find new life. Catalytic converters have ensured a reduction in polluting emissions such as carbon monoxide and nitrogen dioxide. Filters on diesel engines have reduced pollution by fine particles. But all these technical improvements are mitigated, counterbalanced, by constant increases in the size of vehicles, their power, the myriad added onboard electronic devices such as GPS and air conditioning, as well as by the greater distances traveled. It is also too often forgotten that the technologies expected to reduce pollution, such as the catalytic converter, rely on the use of precious metals, including palladium and platinum, and that these devices displace pollution more than they remove it. Efforts to develop less polluting engines and fuels make it difficult to seriously rethink whether all of these objects are truly necessary or if we could be using them all in a more frugal manner. Many official reports attempt to assess the health and financial costs of air pollution generated by transportation. They would be $900 billion for the OECD area alone. Since the 1970s, motorization has also been extended to all the middle-class populations of the world, to the great benefit of state affluence and manufacturers, who continue to see the automobile as an indicator of economic prosperity. In India, cars are now one of the main causes of urban pollution in the country. At the end of the 1990s, the transportation sector already accounted for more than 40% of the petroleum products consumed in the country. Pollutions from nitrogen oxide and airborne particles were derived mainly from modes of transport. It was only in 1990 that the first emission standards were adopted in the country. In the last 20 years, India has also become a major car manufacturer, and the Tata company is striving to reinvent Ford's promise of cars for all, in southern countries. Almost non-existent in the 1970s, the Chinese car fleet reached 40 million vehicles in circulation at the beginning of the 21st century. Massive pollution of Chinese metropolitan areas has gone hand in hand with this spectacular increase. Their peaks in pollution are regularly reported by the media. Alongside land vehicles, air transport must also be considered. It was still in its embryonic stages and reserved for a small elite in the 1960s, 110 million passengers. But the number of passengers then doubled every 10 to 15 years to 1 billion in 1987, 1.5 billion in 2003, and up to 3.7 billion people in 2016. It is expected to rise to 7 billion by 2030, which will have significant ecological impacts, particularly in terms of CO2 emissions. As with cars, in the face of such growth,
authorities and manufacturers are relying on the technological leaps that are supposed to inaugurate sustainable aviation. Thanks to better traffic management, the development of more efficient aircraft and engines, and the use of agrofuels, manufacturers are expecting reductions in pollutions from aeronautical travel and transportation. The explosion of greenhouse gas emissions due to widespread mobility and motorization, along with the growing focus on the planet's climate issues, have given new vigor to the nuclear trajectory. Initially, the construction of the first nuclear power plants in the late 1960s met with significant apprehension with regard to radiation. These fears diminished, however, while the number of reactors in the world increased rapidly. After the oil crisis, the Mesmer Plan in France, named after the Prime Minister and adopted in March 1974, prompted a vast, unprecedented, and unparalleled construction program. In the early 1990s, there were about 400 reactors in the world, but then construction stagnated. In 2012, the nuclear sector represented 12.9% of the electricity produced worldwide and 4.4% of the energy consumed. The United States had the largest number of reactors in operation. France ranked first in nuclear power's share of the nation's energy mix, 37% of its energy consumption and 78% of its electricity. Japan has also become a major nuclear country, the third largest in the world, with 54 reactors in operation that produced 29% of its electricity before 2011. The late 1970s, however, marked the beginning of major questions surrounding nuclear safety, after several major accidents, at 3 Mile Island in the United States in 1979, and especially at Chernobyl in the USSR, Ukraine, in 1986 and Fukushima in 2011 in Japan. As early as 1957, the USSR had experienced a nuclear accident in Kyshtym, in the Urals, at the Mayak nuclear complex. An explosion was the source of a large radioactive contamination. The Chernobyl disaster, however, was the critical disaster at a crucial time that likely quelled nuclear power's potential growth. It called into question the cost-benefit merits that nuclear purported to have in its favor. From the meltdown, a radioactive cloud passed over Europe. The effects were felt several thousand kilometers away. Determining a precise balance sheet of the disaster is impossible to evaluate and subject to controversy, but between 25,000 and 125,000 liquidators, required on the site to plug the breach, would have died rather quickly, more than 200,000 would have suffered disability, and between 14,000 and 985,000 people could have died from radioactive contamination. A few years after the fact, the UN and WHO estimated that 10 million people could potentially suffer the consequences of these radioactive pollutions, many of them through blood or thyroid cancers. The area around the plant will remain contaminated for hundreds of years. Pripyat, which at that time had a population of 50,000, has become a ghost town. The Fukushima disaster reactivated the same fears and questions, not least because Japan's safety protocols and measures were amongst the most stringent in the world. Here again, reports caught controversy and many studies are still in progress, but the radioactive pollution is proven, and it continues to spread, especially in the sea, through the plant's cooling water systems, which remain unconfined. Radioactivity levels are higher than initially suspected and continue to raise alarm bells. Faced with these disasters, it is impossible to extricate the issues surrounding nuclear risk from the pollution debate. Many regard nuclear power as a source of green, or clean, energy, because it emits fewer toxic emissions for flora and fauna, the environment, and those living near power stations. In France, this position is embodied, for example, by the engineer Jean-Marc Jancovici. However, nuclear energy does emit CO2 throughout its cycle, during the extraction of uranium and its transformation into fuel and during the construction and dismantling of reactors. There are also numerous insidious radioactive contaminations from mining waste, authorized discharges, or chronic pollution related to waste management and reactor dismantling, which are generally disguised by the establishment of a dose management system. Governments must defend their positions on nuclear power in the face of anti-nuclear criticism in the age of global warming. The issue of radioactive waste remains more relevant than ever. Until 1982, although it was a controversial practice even within the engineering community, 100,000 metric tons of radioactive waste were dumped at sea in concrete containers. 75% of it came from the United Kingdom. The practice was subsequently prohibited by the London International Convention, 1993, but discharges into the sea by pipeline still happen, such as at the nuclear fuel reprocessing facility at La Hague, at the end of the Cotentin Peninsula in France. First rendered operational in 1966, and initially for military use, and attached to a waste storage facility, the plant converted to civil engineering in the 1970s and treats used fuel from Germany, the Netherlands, Switzerland, Belgium, and Japan, to separate out the radioactive elements. The recovered plutonium is then transported to the Marcoule plant to produce MOX, a nuclear fuel from waste reprocessing. In 2014, France had 1,460,000 cubic meters of radioactive waste. Burial projects under thick clay layers at great depth, as on the site of Bure in France, are subject to intense scrutiny and controversy. Justified as the only viable solution for some, it is widely considered a huge threat and a short-sighted strategy that simply delays or postpones the prospect of risk from hazardous contaminations. The construction of impotence. The regulation of pollutions continued to follow the responses, methods, and practices that typified the regimes established in the 19th century. Expertise remained the primary criterion for legitimizing political decisions and new regulations, an inchoate bundle of commands and constraints that did little to diminish contaminations, even though marked progress in measuring instruments and scientific knowledge should have yielded better results. Toxicology, a discipline that explores the risks associated with the exposure of living organisms to foreign substances, particularly at the forefront of alerting people to the dangers of pollution, was often diverted in favor of a public health from on high that tended to dismiss the severity of risks, such as the responsibility for pollution in the explosion of cancer. In addition, manufacturers continued to insist that the importance of industrial secrecy absolved them from having to publicize toxicity studies. As for epidemiology, it was marginalized because it struggled to establish concrete evidence, especially with the immediacy that many toxic hazards required. Also, to produce proven results in epidemiology implied accepting the principle of large-scale human experimentation and the inherent dangers that it entailed. As in the past, the credibility gap between scientists and the public challenged scientific expertise and authority. More and more secular groups challenged the monopoly of the scholarly and administrative expertise that followed in the footsteps of such 19th and 20th century trusts. Yesterday as today, inaction is obviously never absolute. Some toxic products have been banned, either totally or partially, while their uses have been subjected to more and more controls. This is the case with asbestos, banned in 2005 throughout the European Union, in 1993 in Italy, 1994 in Germany, 1997 in France and Belgium, and 1999 in the United Kingdom, even if its legacy of health effects persists and will continue to be felt in the coming decades. In France alone, between 61,000 and 118,000 deaths were attributable to exposure to asbestos between 1955 and 2009, and 75,000 additional victims are expected by 2050. Asbestos use continues to be allowed outside Europe, but it is mainly produced in Russia, China, Kazakhstan, and Brazil, with a volume of over 2.5 million metric tons a year. This figure is, still, steadily rising. Canada, an historic producer and exporter, only slowed production after 2011 and would not cease production until 2018. Another emblematic product is chlorofluorocarbons, CFCs, used in refrigeration and air conditioning equipment, for which the Montreal Protocol on substances that deplete the ozone layer was reached in 1987, and which all countries signed in 2009. Since global production of CFCs was halted in 1994, a drastic planetary reduction in emissions constitutes one of the great success stories in the struggle against global contaminants. A UNEP report estimates that 2 million skin cancers are prevented each year by this ban, and the ozone layer stopped receding in 2016. As ever, however, the task is not yet complete. Among the gases introduced to substitute for CFCs in manufacturing, hydrochlorofluorocarbons, HCFCs, will not be completely banned for decades to come, and hydrofluorocarbons, HFCs, even if they do not contravene the Montreal Protocol by destroying the ozone layer, are potent greenhouse gases. The Kigali Amendment of 2016 was signed in Rwanda as an addition to the Montreal Protocol. Its focus took aim at outlawing harmful CFC substitutes, but without really knowing what to replace them with, even as the use of air conditioning continues to spread. In general, when a toxic product is banned, it is because the market can provide a ready substitute. This was the case with DDT, banned in the agricultural practices of several countries since the 1970s, a ban that the Stockholm Convention, 2001-2004, sought to generalize definitively, but which India ignored. This was also the case for leaded gasoline, which was banned in countries from the 1970s to the present, although some countries still allow it, or the vinyl chloride contained in aerosol sprays, banned in France since 1976. But apart from these few emblematic cases, the continuing proliferation of toxic products and the inadequacy of institutional responses dominate narratives of pollutions. The social and political construction of impotence in the face of pollutions is a major phenomenon of contemporary public policies. It can be explained by the continuity of the historical dynamics described throughout this book, such as industrial lobbying, pressures on the labor force, and a series of structural biases that ensure that any regulatory process does not hinder the bottom line, a devoted and dedicated commitment to economic growth. Most of the data used as a basis for the regulation of toxic substances and radiation are produced by industry itself. In addition, many of the regulators' experts have unclear relationships, open conflicts of interest, but also more subtle connivances with the industry they are supposed to regulate. Powerlessness can also be due to the ever more intimate relationship between industry and research. Some mercenary scientists artificially maintain a level of doubt, while private or public-private funding makes some knowledge difficult to produce. Merchants of doubt and interest lobbies remain active, generating uncertainty, which prevents any effective or ambitious measure. The gap between alarmist speeches and actions favoring business as usual is now emerging as a further obstacle and source of regulatory impotence. The influence enjoyed by the big polluting industries has probably never been so important. Scandals reveal the close links between industry and the scientific community. One example among many. In 2017, Michel Orbier, a renowned French pulmonologist and author of numerous reassuring declarations on the dangers of air pollution from diesel, received a 6-month suspended sentence for lying about his ties with the oil giant Total since the 1990s. Opposition to environmental regulations is not just a matter of interest and lobbying in its classical form, but also a process of building ignorance that is developing in an increasingly subtle and surreptitious way. Establishing uncertainty and ignorance in the stakes of these disputes is of central importance to the merchants of doubt and their industrial employers, as shown for example in the case of glycol ethers. Their invisibilization is eminently political. All the same, the way in which public health problems are framed around pesticides remains rooted within the same confrontation and paradigm of uncertainty that pits a government committed to data and instruments against skeptics determined to undermine what the data actually say. Within this macabre, and all too common, refrain, science's capacity to serve as an asset in ascertaining truth and salubrity is fraught with difficulties. Instead, science has become an instrument of indecision, inaction, and even ignorance. Agnotology, the active construction of ignorance, was already present in the 19th century, but its centrality in toxic debates accelerated after 1945. It remains more decisive than ever in our thinking about contemporary pollutions. Similar findings can be made on the issue of workers' health related to emerging chemicals. Professional risk management systems are designed by and for experts, which makes it very difficult for employee representatives and citizens to take ownership of them. If such controls become, for all intents and purposes, invisible through a lack of knowledge or access to knowledge, the status quo prevails. At the same time, authorities preserve an aura of ignorance surrounding past pollutions by reconverting old industrial sites and giving new meaning to the scars they leave on the landscape. Industrial heritage policies, initiated during the 1970s in Europe and the United States, were designed, basically, to remove traces of old polluted areas. Indeed, the industrial patrimony that transforms remaining sites into glorious monuments comes from a strategy of concealing degraded spaces sacrificed to industry. Following in the hallowed footsteps of the buildings of the rural proto-industry of the early modern period and the metallic structures of the 19th century, it is now possible to witness incipient efforts in the patrimonialization of the contemporary chemical industry. The construction of impotence takes many forms, which explains how contaminations continue to grow in quantity and severity, despite the many devices and laws that have been introduced to attempt to stem the phenomenon. Namely, regulatory devices are legion, and they have evolved away from protecting the polluters the way they did in the 19th century. Environmental law, and pollution law, more specifically, has emerged as a new branch of law that has increasingly come to include the criminal sphere. Notions of environmental crime and even ecocide have become common. Moreover, the recent period has been marked by the burgeoning of environmental administrations and the strengthening of international cooperation, leading to some successes and many disappointments. But a golden rule persists: the law remains ineffective without the political will of the state.
As early as the 1980s, reports and surveys highlighted the great inefficiency of environmental law, a baroque edifice, marked by uncertainty and contradictions. In the case of French establishments classified as industrial, the number of inspectors has remained structurally insufficient, and their numbers grow much less quickly than the factories that require oversight. In 1978, France had 273 inspectors, 515 in 1988, 581 in 1996, before their numbers grew rapidly, to more than 1,000, at the beginning of the 21st century. But even this expansion failed to keep pace with industrial growth. The inspectors were responsible for more than 500,000 classified establishments. In Great Britain, customary law and its pragmatism remain at the heart of regulations and, as in France, inspectors favor negotiations, criminal sanctions remain rare. The increasing complexity of regulations at all levels, local, national, and global, and further institutional entanglements also contribute to making well-intentioned actions ineffective by rendering decisions and initiatives useless. International conventions on the environment, concluded mainly under the auspices of the United Nations or its agencies, wait years before being ratified, if they are at all. Moreover, most conventions are heavily adapted to comply with the interests of, or the pressures exerted by, the major industrial stakeholders. For example, the climate conventions and the fight against greenhouse gases are based on the carbon market, an emissions trading system that the industry has managed to impose, rather than on taxation. As a result, the extensive environmental commodification introduced in the 19th century is allowed to continue, with polluters paying compensation while being allowed to operate their factories. REACH, registration, evaluation and authorization and restriction of chemicals, a recently formed agency for European chemical oversight, constitutes another attempt at regulation at the supranational level that encountered difficulties in its application, not least because of the numerous exemptions and derogations it introduced. Entered into force in 2007 after lengthy negotiations, its objective is to record, evaluate, and better control chemicals manufactured, imported, and placed on the European market. But the central paradox of this regulation came from the fact that new formulations arrived on the market far more quickly than the new policing system could assess their toxicity. Rather than catching up with the delay in evaluating new chemicals, the situation became all the more chaotic and out of control. As a means of managing its sprawling obligations, the regulations were applied only to new or imported substances whose volume exceeded 1 metric ton per year per company. In other words, many molecules escaped attention, especially nanomolecules, those that were very light, or those for which the duration of exposure poses a much more significant threat than the dosage. The proliferation of environmental law and regulations to circumscribe pollution, therefore, changed scale, but its evolution has never been a wholly linear and continuous process. Further, as in the past, the most polluting industries do not cease to create new methods to resist, obfuscate, or soften environmental standards or reduce opposition. While many international and supranational regulatory efforts express a degree of earnest goodwill, many countries have refused to adhere to pollution control policies when they threaten to hinder their economic growth, even when a consensus is slowly being reached that no such economy-environment dichotomy exists. In China, for example, the role of the State Environmental Protection Administration, SEPA, is expanding, with the number of employees doubling between 1985 and 1995 to reach 88,000 civil servants. However, the results are mixed. At the end of the 1990s, only 12 pollutants had been subjected to controls, and only the industrial sector expressed any concern over nitrates and pesticides as major sources of contamination. The authoritarian organization of the Chinese regime and the priority accorded to the rise in production constantly marginalize environmental initiatives. In 1998, a legal assistance center for victims of pollution was launched, on the initiative of academics and environmental activists. The following year, the Communist Party imposed a temporary moratorium on industries in Beijing to limit pollution on the occasion of the celebration of 50 years of the People's Republic. But regular warnings of poor air quality and smogs of unprecedented size and density have led to a veritable airpocalypse. China's continuing dependence on coal is the main cause of this heavy chronic pollution. If Chinese authorities regularly promise, in vain for the moment, ambitious plans of action to convert to a transformative, green, economy, it is legitimate to doubt the success of these half measures that never counter the drive for production. In 2014, according to the OECD, the economic costs of the health effects of Chinese air pollution would have reached $1,400 billion, and $500 billion for India.
The example of China shows that, without really breaking with the past, environmental law and regulations depend very much on the political voluntarism of decision-makers who are caught up in a mesh of factors combining representations, cultures, political power relations, and social equilibriums. For example, when the Mexico City Council decided in 2014 to remove polluting cars from the city to improve the air quality that impaired the health of its millions of inhabitants, it provoked a strong outcry that stalled any action. In the absence of real political will, such achievements are a far cry from stated objectives. In 1975, the French planned to treat and eliminate 80% of effluents before they returned to the environment by 1990, but they never came close to reaching this target. A report published in 1988 noted that 95% of water pollution offenses remained unreported or unaddressed. More recently, the Eco-Phyto Plan, adopted in France in 2008 after the Grenelle Environmental Roundtable, a multi-jurisdictional dialogue on national environmental challenges, targeted a 50% reduction in the use of pesticides over the next 10 years. That goal was a complete failure, since consumption, as previously noted, continued to grow. The fight against pollution remains subordinate to economic and financial interests and priorities, struggles for influence, and the interests of those in power. The polluting industrial complex is increasingly colonizing states and governments to shape regulations to their advantage, when it is unable to organize its efforts to cleverly cheat and circumvent existing standards, as the 2016-2017 Dieselgate case, involving many European car manufacturers, suggested. To make matters worse, many political leaders refuse to treat pollution as a serious problem, and remain ignorant of the issues. During George W. Bush's presidency, 2001-2009, the American administration actively set back the national fight against pollution, downsizing the EPA, freezing industrial waste management programs, dismantling air and water quality laws inherited from the 1970s, and expressly denying climate change and the science behind it. Even though President Barack Obama's administration undeniably paid greater attention to environmental issues, the election of Donald Trump as U.S. President in 2016 reactivated a policy of denial that risks calling into question a large number of international agreements and research and action programs. Powers and asymmetries. In the fight against pollution, history shows in the end how socio-political power relations are fundamental to understanding the motives behind the struggle. Around the 1970s, environmental movements managed to establish a series of environmental concerns on the political agenda. But aside from this brief environmental moment, the historical narrative has witnessed the recurrence of asymmetries between a dominant doxa favorable to industrialism, whether it purports to be a new, green, industrialism or remains orthodox in its polluting practices, and the environmental groups that alert the public and denounce contaminations while being constantly marginalized. The contemporary era appears to have fallen in lockstep with historical continuity, even if local contexts provide some nuance, and despite a new global environmental awareness that seems to be emerging little by little. Environmental failures and the glacial pace of regulation are due to the dominant economic imagination embodied by experts and decision-makers anxious to boost growth by rejecting anything that could hinder it, because of the additional costs that this would impose on companies that must be competitive in the globalized economic system. Multinational corporations, already powerful after the war, have seen their influence increase during the last decades, because they benefit from the acceleration of mobility and the circulation of capital. These conglomerates, with subsidiaries around the world and factories in several countries, are fluid entities, relocating freely to find raw materials and cheap labor. That mobility plays a decisive role in the fate of environmental regulations. While global enterprises were denounced in the 1970s for their predatory actions and their pollutions, intellectuals such as Schumacher and Illich strongly attacked these organizations, whose practices they considered counterproductive. In the 1980s, an intellectual offensive renewed and rehabilitated their public policy standing. The new spirit of capitalism, carried by an aggressive managerial discourse and indoctrinated executives, extolled the figure of the entrepreneur as forward-thinking pioneer, while Marxism was reduced to crisis, its place in social criticism in tatters. In a period that demanded optimism and was typified by a permanent celebration of financial success and consumption, enterprise became an unassailable totem. Numbering 7,000 in the early 1980s, there are now roughly 80,000 multinationals, employing 75 million people and accounting for nearly 70% of global trade flows. While companies in some southern countries are becoming more international, most multinationals are from the north and contribute significantly to the uneven growth of pollution. They are widely denounced for their role in the world's social and ecological crisis. The American linguist Noam Chomsky sees in it private tyrannies and totalitarian institutions that exercise illegitimate power outside of any democratic control. Nevertheless, their growing power and influence has been unyielding. Multinationals embody a new type of empire based on hierarchical social relations, the domination of nature, and legal impunity. The business world boosts itself by stifling its opposition, especially investigative journalism. Thus, to counter the revelations of whistleblowers about their secretive and shameful practices that dodge taxation or the law, the European Parliament approved a directive on business secrecy in April 2016 for the benefit of these large companies. The underground influence of these lobbies helped to block any reform project and any attempt to impose limits on polluting emissions. In this framework, which prioritized a business-as-usual mentality, policies with an environmental objective also had to try hard to preserve competitiveness and the pursuit of profit, thus leading to the tragic legacy of sustainable development rhetoric. The so-called Porter hypothesis, coined in 1991 by a Harvard professor of management, explains that environmental regulations can both reduce pollution and not threaten corporate profits. According to this thesis, good and flexible standards push corporations to innovate to reduce nuisances, which favors productivity gains, and in the long run the expected benefits would be greater than the costs of depollution. In keeping with the long-term dynamics explored in this work, this thesis ultimately continues to protect polluters by creating an ever more favorable framework for the deployment of their activities. While the Porter hypothesis claims to propose means of controlling industry, in the case of global warming the economists who dominate the disciplinary field continue to invoke perfect markets, the rationality of agents, an infinitely generous nature, as well as profuse rhetoric on the legitimization of a carbon market and industrial investment in polluting sectors, offset by other frontline actions. In recent years, ecological modernization, as a new paradigm, has also been emerging. The term refers to new approaches to the relationship between the economy and the environment, based on managerial, rationalist, and technical conceptions. It makes the protection of the environment a condition for future growth and a source of economic opportunity. According to its proponents, the scale of pollution and global environmental imbalances have become such that only complete control of the planet's physical processes would be able to counterbalance their effects. From here, legions of responsible, informed, pragmatic, and optimistic people draw the future's paths and propose their solutions, which are mainly technical. Published in the United States in 2015, the Eco-Modernist Manifesto, signed by 18 scientific leaders, is a striking example of this strategy. For these eco-pragmatists, as they choose to call themselves, pollutions are essentially a problem of innovation and the need for better technical management around the world. Global climate change, the depletion of the stratospheric ozone layer, ocean acidification, air and water pollutions, all could be solved by more innovations to decouple human well-being from environmental destruction, while regreening the earth and retaining the high-tech comfort of the wealthiest. Coal and oil are praised for their ability to preserve forests. Pesticides and tractors are celebrated because they increase yields and avoid further agricultural expansion. Nuclear energy is presented as the best solution available in the face of energy shortages. Political elites, industrialists, and scientists are betting on technological breakthroughs and innovation as a solution to the threats posed by pollutions. In the final agreement from the climate conference held in Paris in December 2015, the words pollution, energy, oil, coal, and ecology are absent. On the other hand, mention of techniques and technologies is omnipresent. The consensus on climate risks does not call into question the materialism of lifestyles but promotes new technologies and vast techno-scientific projects in climate engineering. In this framework, geoengineering constitutes a fountain of youth for technological fervor. It is promoted by multinationals and a few major public institutions as offering techno-scientific solutions by imagining, for example, systems that harness pollutions. Geoengineering advocates artificializing everything to control everything, to the point of injecting massive amounts of sulfur into the atmosphere to compensate for the effect of greenhouse gases, as proposed by Paul Crutzen, recipient of the Nobel Prize in Chemistry. Following 19th century scientific rationale, pollutions conceptually remain a uniquely scientific problem. Many reports intended to guide political choices promise the advent of e-agriculture, which is cleaner and more efficient, thanks to big data and robotics. Oxymorons proliferate. The green economy is rich in such promises of a better, greener, richer future. Eco-design must produce materials designed from the outset to avoid pollutions. The future imaginary will introduce microspheres capable of cleaning the blood of victims of chemical, radioactive, or biological pollutants, or miraculous coatings capable of absorbing dangerous substances, like a cleansing tar that ingests nitrogen molecules, or pollution-eating microbes, capable of cleaning the soil and water. For their part, ecologists and biologists are studying ecological solutions to diffuse pollutions. While full restoration of an ecosystem is impossible, there are more and more natural strategies for decontaminating polluted landscapes. Soil phytoremediation will allow the use of plants and microorganisms to extract, contain, deactivate, and degrade soil contaminants. Many call for the development of eco-technologies and a restorative science to reactivate the technicist paradigm once in existence. The specialists recognize, however, that all these depollution techniques are insufficient because there are limits and thresholds beyond which any repair of the environment becomes illusory. Other prophets announce the advent of new, inexhaustible and clean energy trajectories. Jeremy Rifkin has heralded the advent of a hydrogen economy that would break with the old nuisances of the industrial age. For the past 10 years, there have been countless publications, projects, and investments to promote the development of the hydrogen regime, presented as the only way forward in the fight against air pollution, according to Pierre-Etienne Franck, Vice President of the Advanced Business and Technologies (AB&T) unit with the Air Liquide Group, and an influential lobbyist for the sector in European institutions. Geologists, for their part, champion the infinite potential of natural hydrogen, which would not require any fossil energy in its production, and would thus offer a non-polluting energy, even if the authors recognize that such a promise is still far from proven. The fight against pollution has become an omnipresent marketing and advertising argument for selling new products, obtaining financing, and attracting the interest of public authorities and citizens. The craze for renewable energies, solar, wind, and so on, is sometimes part of this logic. Faced with this steamroller that combines economic realism, optimism vis-a-vis the virtues of the market as well as human ingenuity, and liberal and entrepreneurial ideas, movements that center their approach around the environment and pollution and insist that economic decisions should be constrained by the planet's ecological rhythms are invariably marginalized and ignored. This marginality does not mean that their warnings go unheard, but rather that their influence on regulations is very limited and always on the fringes of decision-making. Indeed, apocalyptic fiction films and documentaries, journalistic investigations, and committed essays rehash the problems with the status quo, condemning in each country the responsibility of industrialists and their connivance with policymakers. In France, journalists such as Hervé Kempf, Fabrice Nicolino, and Marie-Monique Robin, like Jean-Pierre Rogel in Quebec, are amongst the most vocal critics of the enduring status quo. It has become fashionable to consider ecology as a new, widespread doxa of the future, and that resistance to polluting practices could become a central tenet of contemporary life. It is true that anti-pollution militancy has acquired a form of legitimacy, inaugurating hybrid societies, dark green or light green depending on the extent of the movement in each country. At the same time, the institutionalization of organizations and ecological militancy continues along different paths. Everywhere in the world, environmental organizations are emerging, green parties are growing on the political landscape, and international NGOs are extending their fields of action to fight against pollutions and alert public opinion to their dangers. For all that, however, pollution and contamination have not declined over the past 40 years, with some local and product-specific exceptions. Multiple standardization strategies are at work to disqualify political ecology and make pollutions tolerable if they can be controlled. The idealists with a vision of infinite growth and happy globalization, blind to the ecological consequences of their policies, are constantly striving to absorb criticism and succeeding in transforming the radical and apocalyptic discourse into resigned acceptance. More broadly, the question of pollutions is, however, euphemistic in its media framing. The solution entrepreneurs insist on small individual gestures and good practices without ever calling into question the global organization of the world and its productive and consumerist model. While pollutions accentuate inequalities and global injustices, their regulation requires a radical reshaping of power and expertise. The insistence on innovation alone in order to reduce the materialism of the economy and invent clean and inexhaustible energies never permits reimagining socio-political organizations and lifestyles, which would be necessary to live in a world without pollution. In the face of modernizing promises and multiple strategies of depoliticization and dissimulation, other avenues involve considering trajectories of less materialism or energy sobriety as the only methods capable of reducing the ecological footprint of contemporary societies and the quantity of polluting substances released. Recent scenarios demonstrate there are models that inspire hope. They involve rethinking production and consumption structures, like the path proposed by the Negawatt Association, which is paving the way for 100% renewable energy by 2050, provided it is given the freedom to develop. Similarly, Jason Corburn's study of street science shows how Brooklyn's community movements for asthma, air pollution, and lead contamination are promoting the recognition of environmental inequalities and galvanizing a democratization of the construction of the problem of pollutions. Rather than accentuate the techno-scientific artificialization of the world in order to try, at best, to control pollutions that are considered inevitable, new projects involve turning away from the promise of infinite growth in favor of more sober and equitable ways of life. The deleterious effects of human activities on the environment turned from local nuisances into global pollutions. The historical exploration of this mutation has shed light on its sources and implications, giving meaning to a phenomenon that now looks like a runaway race into the abyss. Regarded from the point of view of the social sciences, this diagnosis must be shared with the other sciences: physical, biochemical, ecotoxicological, medical, legal, and economic. The planet is growing warmer, seas are becoming more acidic, species are disappearing, bodies are being altered. Looking at all of this from an historical point of view makes it possible not to sink into a state of stupefaction, or to only envision an inevitable process on which we could not act effectively. Instead, we can understand that pollution is above all a social and political fact that relies on the ideas of progress that must be discussed at the time of mass contaminations. It is true that enduring pollutions, their persistence in synthetic or nuclear molecules, their geographic dispersal to the most isolated areas, from the Arctic to space, and the unprecedented fragmentation of residues pose a particularly difficult problem and make any resolution seem obscure and daunting. It is possible, indeed, important, to hope, however, that a long-term reflection that points out the inflections, the pivotal moments, and the inertia, as well as the means of action and the balance of power, might offer a key to understanding and opening a door to the emergence of new social and political configurations, able to face contemporary environmental challenges by ushering in a more just and less toxic world. Figure 11.2. Project, Plasm, Dancing, Author, Pasha Kass, Curator, Rash X, Photo, Olyar Koto, Location, Temirtau, Kazakhstan, 2016. Displayed on the side of an apartment building in the industrial city of Temirtau in Kazakhstan, this work by street artist Pasha Kass evokes Henri Matisse's famous painting Dance. The image warns of a world that idolizes wealth derived from oil, around which people turn with an illusion of being sated. Meanwhile, in the background, lead pollution from the city's metallurgical plants is 5 times higher than authorized standards. Index. Note. Page numbers followed by N refer to endnotes. Abt Summer Disaster, 311. Académie des Sciences, 55, 69, 72, 75, 77, 79, 132, 195. Academy of Moral and Political Sciences, 121. Acetic acid, 23. Acid rain, 85, 98, 151, 270, 306, 308. Acids. See inorganic acids, specific acids. Adams Soapworks, 171. Advertising. See also propaganda. Chemical industry, 114. Electricity, 225. Mass consumption and 233, 234, 236, 251. Aeronautics industry, 192, 197. See also air transportation. Africa. See also specific countries. Automotive industry in 220. Electricity in 226. Electronics waste management in 305. Energy consumption in 230. See also electricity in subentry. Environmental inequalities and injustices in 308 to 310. Fertilizers, pesticides, and herbicides in 313 to 314. Metallurgical operations in 313. Mining industry in 106, 229,
251. Petroleum industry in 205, 217. Urban areas in 235. Waste and water collection and sanitation in 307, 309. Agent Orange 183 to 184, 198. Age of Progress. See Progress, Age of Progress. Agnotology 321. Agricola, Georgius 42. Agriculture. Agrarian empires and societies 13 to 14. Agrochemical industry transforming 111 to 115, 254 to 259, 302, 313 to 315. Dioxin contamination in 301. 18th century transitions in 13 to 14. Fertilizers and pesticides and 186, 254 to 259, 279 to 280, 313 to 315. Genetically modified organisms in 302. Green Revolution in 254 to 259, 314. Hydroelectricity effects on 227. Inorganic acids effects on 79, 99, 104. Labor practices 285. Organic 258 to 259, 280. Petroleum industry effects on 215. Polluting alchemies effects on 47, 104, 111, 251. Recycling waste in 165 to 167. Textile industry and 21 to 22. Wartime effects on 186, 195, 198. Air Hygiene Foundation 271, 273. Air Liquid Group 328. Air Pollution Act 1955 264, 271. Air pollutions. Anti-pollutions activism against. See Anti-pollutions activism. Artistic and literary representations of 49 to 50, 127.